Hello, in this video, I'll teach you how to build this basketball analysis project from scratch. This project is able to extract a lot of good insights from a basketball game using multiple AI models like YOLO for object detection. This includes the number of passes and interceptions each team made, the ball acquisition percentage of each team, the distance and speed of each player, and even translate the camera view into a tactical top-down view, allowing the system to fully understand what's happening on the court. We'll start by detecting players and balls using YOLO. YOLO is one of the best object detection models right now. We'll also be training it or fine-tuning it to improve the performance of out-of-the-box ready-made models. Then, we'll assign players to teams based on their jersey color using a zero-shot image classifier that identifies the jersey color from the cropped player image and the class labels we provide. Zero-shot classification is a great way to classify images on a specific use case without needing to train a whole model. With just these two models, we can track which player gains possession of the ball, allowing us to calculate each team's ball acquisition percentage. We can also detect passes and interceptions by analyzing changes in the ball possession between players. We'll take it a step further by training our own keypoint detector to identify landmarks on the court in each frame. Then, using those court keypoints, we'll work on perspective transformation that takes in a camera's distorted viewpoint of the 3D world and accurately represent the scene's depth and perspective into a clean top-down tactical map. This mapping translates pixel positions into real-world court coordinates so we know a player's speed and distance covered in meters and not only in pixels. This project will cover a lot of AI and computer vision concepts and deal with real-world problems. So whether you're a beginner or an experienced machine learning engineer, this project will totally make your resume shine. So let's start by getting the videos that we are going to use to develop the project. So you can go to my GitHub account, then the basketball analysis project. I'll leave a link in the description below. And then you can go to input videos. You're going to see 3 videos where each one is covering a specific use case, like passing the ball, intercepting the ball, and running with the ball. And yeah, to download them, just click on the video 1, for example, then press download raw file. You can see that it downloaded, so you can go again to input videos, do the same thing for video 2. It downloaded, and then do the same thing for video 3. Now that we have all three videos downloaded, you don't have to clone this repository. It has a lot of folders and a lot of files. We are going to be developing this together one step at a time. So don't worry about that, and you don't have to clone this project if you're going to follow along with the tutorial. So go to the place that we are going to develop the project in and create a new folder that is going to host the project. Call it basketball analysis, like this, and also have a new folder called input videos. Then open this and go to your downloads folder. Cut your videos that you downloaded and paste them right here. We can now explore those videos and see what's inside. So in video 1, you're going to see a person running with the ball, and this is going to be a good example for measuring distance and measuring speed, and and ball acquisition basically. So in the other video, you're going to see that it's like the team is doing a lot of passes, so it's going to be good while developing the passes logic. And the last one is going to be someone intercepting right there, the ball. So it's going to be good for writing the logic to intercept the ball and test it out. And it also has a pass and 2, and yeah. We are going to be utilizing all 3 to develop the project, and within different features, we are going to be focusing on different videos. So yeah, you're going to see when it unfolds. So basically, right now, we want to open up a Visual Studio Code in this folder. You can open up whatever code editor you want. I am using here Visual Studio Code. And in here, you're going to see that it has the input videos, video 1, 2, and 3, and we are going to be adding other files and folders as well as we go. The first step of this project is to detect where the players are in the frame and where the ball is in the frame. And from here, we can track different metrics that we want, how fast a player is moving, how much he's moving, and how, like, whether they have the ball or not. And all this is because we have the ability to locate different objects within a frame and then say what it is. So like a player's or a ball. So this is what we call basically object detection, and you can see that object detection has the ability to say that this is a person and this is the box that is around the person. So saying what's inside of an image is called image classification or image recognition. And usually in image recognition, you have a predefined list of classes. Right here, for this example, we have apple, orange, pear, and grape. And the model has the ability to produce only one of those 4 classes. So if you give it a watermelon, for example, it will produce also one of those 4 labels, and it doesn't have the ability to say that it's watermelon. Now, this is what image classification is. It just produces a number, an index that indicates whether what type of object it is. For example, 0 is apple, 1 is orange, 3 is grape, and 2 is pear, for example. So this is what we call image classification or image recognition. You can see right here it just says that this is a person. Image localization, on the other hand, produces 4 numbers, and those 4 numbers indicate the rectangle that is being drawn here. So the model itself does not draw a rectangle, rather that it produces 4 numbers that from it we can draw the rectangle. So it produces the position of this rectangle and how big is it. So one of the ways that we can represent this rectangle in 4 numbers, we can say that this is the middle of it. So the middle position of it is going to be an X and Y position. And this X and Y position is going to be relevant to the width of the image, with the width is going to be X and the height is going to be Y. And so this middle of it, and then we can also add a width and a height. So the width of this box and the height of this box. This is one way to represent the this rectangle in 4 numbers. And then we can in the pre-processing function, after we get the output from the model, we can then just draw this bounding box after that. One other way to represent this box, which is the way that we are going to use in this tutorial, which is for me is more intuitive, and the functions of OpenCV takes this notation, which is using 2 main points of this rectangle, which is the top left point and the bottom right point. If you have those 2 points, you know where the rectangle is and how big it is. Now, this has an XY, and this also has an XY position. So this is the final notation. So it's going to be XY and then XY. 2 different points with 2 different XYs. You can call it X1, Y1, X2, Y2, or whatever you want. But basically, it is called XY notation. Now, object detection is basically both. It tells you that this is a person and this is the location of this person inside of this image. Now, object detection goes a step further, where we don't only have one object inside of the image. For example, here we have a player, we have another player, we have a third player, and then we have also a ball. So we can have different classes as well. So we can have different classes like players, balls, referees, like hoops, and everything like that. and each of which will have a bounding box indicating of the position of it. Now, this is going to be a huge building block for us, because when we know the player position, we can say that we can track them over frames and know how fast they're moving, how much distance they covered, whether they have the ball or not, by just seeing like the closest box to the ball box. And we can do a lot of analysis by just having the object detection framework up and running. One of those object detection models that are very good is called YOLO. You only look once. Now, YOLO is a very state-of-the-art model for object detection, and its architecture is able to look at the image once or process the image just once and produce different boxes at the same time. Before YOLO, it was looking at the image multiple times to produce different bounding boxes and in different places. But YOLO made another architecture, a faster way to process it, and this is one of the state-of-the-art models out there. And YOLO actually evolved over time. So we have YOLO v1 through YOLO v11. So we have YOLO v2, 3, 4, 5, till YOLO v11, and every model is trying to improve on top of the other model, and is trying to handle different edge cases, and maybe sometimes it's trying to be faster over the model, not necessarily more accurate, things like that. So we are going to be choosing a YOLO version that is going to be suited for us. Now, one of the most convenient ways to use computer vision models is a library called Ultralytics. So Ultralytics is a library that has a lot of computer vision models, including YOLO models. So it has till YOLO v11, and you can also check out their website. It will have a lot of also documentations and a lot of resources. So yeah, feel free to see them right there. So in here, you can just write Ultralytics pip or pip install like this, Ultralytics, so that we can get the exact command to install Ultralytics. Ultralytics is just a Python library to install. So you can go right here and you can just write pip install Ultralytics, or just copy paste the command from here. So paste it right here, pip install Ultralytics. On my machine, it didn't take a long time because I already have it, but it might take a little bit more time on your end. And to use it, we are going to have like a very simple code base with like 2-3 lines of code that is going to automatically pull in the YOLO model and then utilize it to run it on top of our videos. So create a new file called main.py. From here, you can just, from Ultralytics, import YOLO. So we can just import YOLO right there. And we can just load the model. So YOLO. And from YOLO, we have different models. Like I said, we have like YOLO v1 to YOLO v11. So you can just write here YOLO v8 on GitHub. And this is one of the YOLO models that you can use quite easily. So you can just scroll down, and within the YOLO v8, you have different sizes of the model. Basically, you have a small model, a nano model, a small model, a medium model, a large model, and an X-large model. Basically, those differ in the number of parameters per model. And the number of parameters just means that it's a bigger model with more resources, more computational resources to run. But when you give it more computational resources, it gives you more accuracy. So for example, the MAP, which is, you can consider it as an accuracy level of a model, for the nano is 37, while the biggest one is 53.9. But it requires us to also have more computational resources like RAM, like GPU, like CPU. On my machine, I don't have a GPU, so I only have a CPU with RAM. But my RAM can handle the X-large YOLO model. So I will be utilizing this. So you can just here write YOLO V8 X large. Now this X large model, if it doesn't fit into your machine, you can just go to large, you can go to medium, and yeah, you can go to the size that fits into your machine. After that, to run it on a video, you just have the model.predict, and then you give it the path for the video. So just give it the path of the video, which is going to be input videos, and it's going to be video 1.mp4, like that. Now this is going to run the video, then we are going to make it save equal true, which is going to save the output video of the processed video. And then it also returns back results, which is the bounding boxes and the extracted information from each frame for this video. So I want to show you what's inside of the results as well, because we are going to utilize it later on when analyzing the positions of the users and things like that. So we can just run print results, and then I can also print a line, and then I want to also show you one example box. So we can have 4 box in results of 0. Results of 0 means that this is the 0 frame, the 0th frame, the frame at position 0. And basically, if you don't know already, but basically, if you open up a video consists of frames, 1 frame at a time. So this is a frame, this is another frame, and each frame here is just an image. So this is just an image, an image, an image, an image, and putting them in sequence like that makes a video. If you put on top of it like an audio, then this is video with audio. But right now we don't care about the audio too much. Even if it has audio in the input videos, we just care about the image itself. So frame 0 means this frame, which is the first frame ever. Then this is frame 1, this is frame 2, frame 3, so on and so forth. So I'm getting the frame 0, the results that were processed for frame 0. I'm getting their boxes, and I'm running print box for each one. So I'm getting, let's print the whole box. So I'm printing the whole box for all the boxes that we detected for this frame. So yeah, this is all to it, to basically get a YOLO model, then process it on a whole video. And this is how simple it is, just 2 lines of code. And to produce like the output, I'm just like printing some outputs right there. So those don't count, but it will be good for us to explain the results that we see on that. So to run that, you can just run Python, then main.py, and then write it right there. I wrote Python 3, but you can also write Python. It depends on your machine, so yeah, make sure to play around with it. The first time it runs, it actually goes to the Ultralytics website and fetches the YOLO V8 model. So it gets it, it downloads it, it puts it here. You can see that it's being downloaded. And then when it downloads it, it will predict 1 frame at a time. It will predict the boxes of the input video 1 frame at a time. So you can see here that it's finished. Then this is doing frame 1, frame 2, frame 3. It has 117 frames, and it's running them 1 frame at a time. The model does not see the whole video at once. It just processes each frame 1 at a time, and it takes in the image, gets the output of the boxes, puts it, and then gets in the other image, so on and so forth. And yeah, the results of it is going to be in the results right there, and we are going to print it out, as well as, because we have save equal to true, we are going to have a runs folder that is going to automatically be generated, then a detects, predict, and inside of it you're gonna see the output video right there. This is the output video that we are going to see. So basically right now we can see the output of the results in the boxes, but we are going to go over them a little bit later. This is when it's finished. So you can go here, you can go to runs, detect, predict, and then open up the video. And there we go. This is the output of the YOLO model with the detections of each person. And you can see that it tells that this is a person. This number is the confidence number. How confident is the model that this is actually a person? And you can see that it has lower confidence for people that are blurry, people that are not that clear to be a person. And yeah, so you can see right there, it also has a person, like multiple persons, multiple people being detected. It also sees this as a basketball glove. This is a misclassification right there, but you can also see that it can also, yeah, right there, it also here detected that as a sports ball, which is a correct classification right now. But this is the output of the detection. You can see the whole video, so I'll run it for you. So yeah, this is basically here the whole video. And we have multiple issues with this video, which is basically we are detecting people outside of the court. This is one thing that we don't want to do. We can filter it out later on, but actually it will be more convenient if the model has the ability to know which people are inside of the court or not, and then only choose those people, so that we don't analyze people that are on sitting in the crowd like that, and like those people. Also, you can see that the basketball is not being detected a lot. So you can see right here, it's not being detected, not being detected, not being detected, and now it's being detected as a basketball glove, which is wrong. So we need to also improve the accuracy of this. Now, to do this, we are going to need to fine-tune the YOLO model. Fine-tuning basically means that we get an already trained model and tell it to, hey, this is good output so far, but in order for you to be better, here are some examples that are labeled, and I want you to get me this performance or like this output of it. Now, this type is called transfer learning, where we get a model that is already trained. It knows how to detect objects, it knows how to do a lot of stuff, but it doesn't know how to do my specific task, whether it's an object that it is not basically in its list right now. For example, if you want to detect basically some screws in a machine, in a factory or something like that, and it's too specific, you can have a data set that is labeled and it can learn from it, and you don't have to have it with a lot of data set. We need to have a data set that is going to have this players detected and not the people outside. And we also want to have the basketball detected and have a good detection of this basketball as well. Now let's take a look at what this dataset should look like and what is a labeled dataset that the model learns from. So this is another website called RoboFlow. It's from the same company from Ultralytics, and it helps us to utilize datasets and have labeled datasets. I am going to show you around a little bit more, but for now I want to show you what is a labeled dataset. So basically a labeled dataset, especially for fine-tuning, is going to be like this. So it's going to be an image, just a single image like that, and it's going to have a detection, basically a bounding box on top of the players, like this. And this is a referee. You can see that this is a referee different from player. You can see that here there's a ball, there's a clock, another clock, and the hoop. So basically, we're detecting more stuff that is specific to the basketball and basically this overlay as well. And yeah, and we are not detecting people outside. And if you go through the images, you're going to see that the same thing is consistent. So this is just a data set, is just a list of images that is labeled according to our needs. So different like specific classes or specific use cases like we see here. Now, this is basically a data set that we are going to use, and I am going to also link it in the description below. But yeah, RoboFlow is going to make it really easy for us to label data set, get labeled data sets, and actually retrieve them when we want to write code. So this data set is just 165 images. Actually, more images means better accuracy and more stable performance. But this is the data set that I found right now. So we're going to utilize it, and it's going to have a good performance as well. So this data set has multiple classes like you see here, like the player, like the referee, like the basketball itself, and all of which are good good classes for us to utilize. So we're going to be utilizing this. So you need to basically log into RoboFlow, and it's free, so you can go you can log in and create an account if you need to. Then go to datasets. Then we are going to be utilizing YOLO v5. Now YOLO v5 for sports analytics, what I found is that it's the best model that I played around with, that has more consistent results, especially when fine-tuning. So what I'll do is that I will press on YOLO v5, click on download dataset, then press continue. And what you need to do here is basically show code to download. Basically what we do is that we're going to have a code snippet, then you can just copy it and paste it in the code so it can download it automatically. Just press continue, and here's the code snippet that you want. And yeah, basically training AI models requires a GPU, but I don't have a GPU. So what you do is that you can go to Google Colab, like there, and you can enter it. And basically Google Colab is a Python notebook that gives you the ability to run things on a cloud, on the GPU cloud. So you can have a new notebook like this, and it will require you to log in with your Gmail. That's fine, it's also free, so don't worry about that. And you can call this here like basketball object detection training, for example. And right here in runtime, just press runtime, change runtime type, and you have a CPU, you have a T4 GPU, and you have a V2 like 8 TPU. So those are the free accelerators you have. So you can choose the GPU one, press the T4 GPU, press save, and then it will restart. So what we have right now is that we copied some code from the RoboFlow right there. You can just paste it in. And when you paste it in, you can see that it installs a couple of libraries. So we can just have here a text, which is install libraries. And we can just install libraries first thing that we have. And this exclamation mark runs terminal commands inside of a notebook. So this is just a terminal command, it's not a Python command. And right here, it tells you from, like here it installs RoboFlow so that it can download the dataset. And I will show you right here in the folder structure where it downloads it. And then it has the API key. Make sure to use yours, because I will invalidate mine after the tutorial is done. And you have the project. It gets you the project ID, and if you see here, this is the project ID itself, but it does that all automatically from when you copy the code, and it tells you to download the YOLO v5 structure. So this is basically it. And right now, before we proceed, we just want to pip install also Ultralytics, because YOLO is in the Ultralytics library and we want to retrain YOLO. So right here we can have another text, which is get dataset. Then we have the train YOLO, like that. So let's run this and see how, like what we get. So let's run this and that. So right now it's installing RoboFlow and Ultralytics. You can give it a little bit of time to download it. And then it will get the dataset and stores it right here in your folder structure. So now it's done. I waited a little bit for it to finish. So you can see here that there is basketball 17, and you can open this up. You can have the training dataset, the validation dataset, and the testing dataset. Basically, the training dataset is the dataset that we are going to use to train it. The validation is the dataset that we are going to be measuring the accuracy levels of our model on. And the testing dataset is just a couple of images that we can see the results of. And it also is used sometimes for also validating the dataset right after, like validating the model and seeing the accuracy levels after we train and finish training of it. So you can open the training folder. You can see that it has images. You can open whatever image you want. You can see that it's a court, and it has also players. You can also like scroll around, see multiple ones like this, like that, and yeah. And basically for each frame of those, we have also labels. So you can see now that the labels that we saw here quite conveniently as bounding boxes, I'm going to show you to you again. So that we have here as bounding boxes conveniently, we now have it as the class ID. This is telling you that this is the player or a ball or a hoop or whatever. Then it has 4 numbers, which is the position of the box. And for one frame, we can have multiple objects as well. And we can have multiple like instances of the same object. So we can have multiple players, we can have multiple referees, so on and so forth. So that's basically it. And I want to now close this, so you can just close this again to make room for our code. Now, the idea here is that the code for YOLO v5 requires us to put it in a folder structure that is basketball players like 17, then another folder with the same name, and then put the test, train, and validation. So basically, it's going to have basketball players 17, then test, then another the same thing. So I'm going to show you right here. So write this basketball players 17, and then it requires us to move the test, the train, and the validation inside. So this is what we want to do, but I can do it manually, like dragging and dropping right here. But I want to have my code reproducible, so I'm going to write it in code. So just delete what I did right there, and I'm going to show you how to do it in code. So we can import shuttle, and shuttle lets you cut and copy things from your machine quite easily. So basically we can have shuttle.move, and what we want to move is we want to move the basketball players like this 17. We want to move the train like this. Where do we want to move it? We want to move it to the basketball player 17, and then again basketball player 17, and then train. We want to do the same thing for the validation dataset. So right here valid, and write valid, and this is it. So basically you can just run it right here. You can see that it now processed, and you can just refresh it. Don't forget to refresh it, because this editor does not see changes when, like, most of the changes that is done to this. So if you added a file or something like that, you might not see it and you need to refresh to be able to see it. So right now you can have a basketball player 17 and then train and validation is now inside of it. Now this is specifically for YOLO v5, but if you're going to use other models as well, like, I don't think that this is necessary for YOLO v8, for example. So yeah, make sure that that this step is necessary for the exact model that you're using, but for YOLO v5 it is important. Now for training, it's very easy. So you have to write just YOLO, and this is going to use the YOLO model. Then what to do, the task is going for be to detect, because there are other YOLO models as well for key point detection, for mask segmentation, and I'm going to show you like key point detection later on, but there are other tasks to do other than just detection. But for now, we just want to detection. So the mode is going to be training. So we want to train the model. The model itself is going to be YOLO, and it's going to be v5 and 16 u.pt. Now, if you open YOLO v5 right there, YOLO v5 GitHub as well, like this. If you open YOLO v5 and you scroll down, you're going to see a lot of models right there. You have the nano model, the small, the medium, the large, the X large, the N6, the S6, the M60, whatever. And then the biggest, one of the biggest models is this 16 one that we are going to be using. So yeah, basically we are going to be using the 16U, which is going to be one of the biggest models that we have. Then we are going to have the dataset as the dataset here, data.location. So it's dataset.location, and this dataset right here is referring to this dataset. So this gets a Python value and then adds it to the terminal command. And yeah, we are going to take this location, we are going to add data.yaml, and then we are going to add epochs. The epochs right now is going to be 100 epochs. You're going to think that this is maybe too much, but it's actually not too much because the dataset is very low. And yeah, this is maybe a good amount to have results. So we can then specify the image size as 640 pixels, and plots is equal to true to see the performance of this model in plots. And then we have the batch size is equal to 8. The batch size is the amount of samples that we process concurrently at one time. And the more resources you have, the more batch size that you can have, and the less time that you wait for training. But for collab, I think 8 was pretty good. It doesn't overwhelm the resources, as well as it's optimal for time, like the best thing for time considering our resources. So basically, this is the only line that you need to fine-tune a YOLO model and to have it predict, to have it trained on a custom data set that you have. So you can just run that. You'll have to wait a little bit, but we'll see whether it loads everything and starts training or not. So one small mistake I did is that there's an O, so it's epochs. So you can just rerun it again. And one more thing, that this is an L, so it's large 6. So you can just run it again. Right now it's downloading the model. So yeah, we can also wait a little bit more for it to finish. So right now you can see that it started training. The epochs here is 1 out of 100. You can see the GPU memory, you can see the box loss, the classification loss, which is how much error does each one has. And it will continue training till it finishes. And yeah, all you have to do now is wait for it to finish. Now I already trained the model before, so I don't have to wait for it to finish right now. But if you're training, wait for it to finish. And I provided also the models exactly what I used and what I downloaded from here in the GitHub repo in the README file. So if you want to, you can just use this, or you can wait for yours to finish. So after it finishes, go to runs, go to detect, go to train, then go to weights, and then you have a best PT and the last PT. So right now you can just, after of course it finishes, you can just download this and wait for it to be downloaded. And yeah, this is going to be one of your object detection models. Now you can see that there is a loading circle right there. It's not very visible right now, but it's in blue. It will keep on creating the circle till it downloads. So it might take a little bit of time because it's a couple of I think it's more than 100 megabytes. So it might take a little bit of time. But yeah, just wait for it to download. While it's being downloaded, I want to also mention that for this configuration, I found that this configuration right here with 100 epochs with a batch size of 8 is best to detect players. And I also played around with YOLO V8, YOLO V11, and other YOLOs as well, and found out that YOLO V5 with 100 epochs is best for detecting players. So right here in basketball detection, you can just write here player, right there, player detection training. And if you want to put it into your GitHub repository, like I did in mine, so you can just here download it. So download it as .ipynb. Then go here, go to your project. We create a new folder. Let's call that training notebooks. Now, if you have a GPU on your machine, you can actually run this notebook on your machine. But if you don't, just copy paste it and you can import it actually from here into your Colab. So in here, you can just write file, and then there is something to import. Yeah, upload a notebook right there. So you can upload this notebook and just it will put all the code inside. So in training notebooks, you can go here to your downloads. You can just drag it, put it into your training notebooks, and this is going to be exactly for the player detections. Now, we are going to need to have one that is optimal for also basketball. So you can have a copy of that. Press File, press Save a copy in Drive. Now, there's another one that is going to be utilized. So this is basketball, and we can call it basketball ball training. So we can call it here ball training. Now, for ball training, we are going to keep all the code the same, and it's basically giving me an error because it's telling me you already have a GPU machine running, which is this one. We are going to close it, but right after the best is downloaded. And right here, the best configurations that I found for the ball is going to be the same things, but have a 250 epochs. Now, this sort of behavior is usually eliminated datasets with higher numbers. Those are only a couple of hundred images. I think it's 200 or 300 images. But with more and more images, this becomes way more robust and you can have just one model for both. But right now I had both configurations, and to be honest, I can also, I could have merged both models into one because they're only using v5. But when I'm developing the models, I was utilizing multiple others. I was testing with the YOLO v8, YOLO v5, and multiple others as well. So this was the configurations that actually got me the best results. So this is what I'm showing you right now. So what we are going to do right now, we are going to wait for the best to be downloaded. I'm going to close this one out. I'm going to switch here to train this model and then download its best as well. And then we are going to put it in this in our repo. So yeah, just wait a little bit for the best to finish, and then we're going to continue from here. So now that this is done, you can go to your downloads. You can see that here's the best.pt. So you can cut it and you can go to your folder that has the project and create a new folder called models. And inside of this model, just paste in the best.pt. And inside here, you can call it player detector .pt. Again, you can just give me a minute. I'm going to call it correctly. So this is player detector.pt. Now again, you can just use my models if you want to, or you can train yours. But this is the exact configurations that I used to reach this model. And before downloading it, make sure to refresh it to see the new folders and files. Now, going back to the ball model like this, you can here press runtime, manage sessions, and then press on this terminate session so that the GPU machine is now accessible for other notebooks as well. So here we are going to do the same thing. Install RoboFlow, get the data set, move the training to this folder and move the validation to this folder. And then we are going to run YOLO again, but this time with 250 epochs. And this time with 250 epochs, and this will be optimal for our ball model. So I just ran it, and now we wait. But again, for this model, we are going to only utilize the ball output. And for the other model, we are going to utilize only the player output. Although both are outputting ball and players, but the detections are best for here for the ball, and the other one is for the player. So wait a little bit, and after we wait, we are going to be training this model with 250 epochs, and after it finishes, we download the best model again, and yeah, we paste it in the models folder, this one. So let's wait for that to finish, and yeah, I'll get back to you after it's done. Now again, press on refresh before you do anything else. Wait for the training to finish, and then press on refresh, press on runs right there, press on detect, press on train, and press on weights. You're going to find the best, and the last, just download the best. Wait for it to be downloaded, and then we can continue from here. So after it's downloaded, you can also download this notebook. So press File, and then download IPYNB, and go back here to your downloads. You're going to see that the best and the basketball training is now here. You can cut the basketball training and go back to your training notebooks, paste it right in, go to your downloads folder again, cut the best model, then come here, go to the models folder, and then paste it right in. We are going to call it ball detector model.pt. Now, those are the two main models that we are going to use, and instead of referring to the YOLO VX, YOLO V8X right there, which is going to be a model that is on the Ultralytics cloud, we are going to be pointing to those local models instead. So from here, you can just maybe delete this YOLO V8X, so to delete permanently, like here. And we can start off with the player detector. So just copy its name, paste it right in, and make sure to have the models and then players detector. Just run this. You can just run it by writing, clicking here, or writing Python main here. So click on it. It's now running on the video frame by frame, and then we are going to see the results. Now here it has also the ball detections, but we want to only here focus on the players and whether we suppress the audience or the people that are sitting on the sidelines or not. That's our main goal right there. So now it's done. We can see that the same bounding boxes are being displayed. Again, I'm going to go over them quite soon. And you can go here to the runs, detect, predict 2, which is the second time we ran it. And then we can see the output. So you can see that we have players, we have the referee now, the other people that are inside of the audience are not being detected. We also have the hoop being detected, a clock and the other clock. And yeah, this is basically it, and you don't see anyone in the crowd being detected as a player. So this is huge. This is what we wanted. And you can see that the ball here is also being detected quite as good. So you can see that the ball is being detected a lot. And yeah, but we also want to also show you the ball detector. So for this ball detector, it's going to detect the ball a little bit more, and this is going to make our lives a little bit easier. So that's why we divided the models into 2 models. But you can actually use it in one. But yeah, this is what I decided to do because it has a little bit of a higher accuracy, and I don't care too much about the runtime. So let's now run it. And now it's going to have a predict 3. And yeah, let's wait for it to finish. So now it finished, and we can go over to here, detect, predict 3, and then open this up. You can see that the ball is being detected more and more, even when he is like the player is just putting the ball in the hoop, it's being detected along the way. The other one was like when it came here, it disappeared, but this one is a little bit better at detecting the ball. And yeah, it also has the players and things like that, but again, each one is optimized for a different thing, and you can optimize it actually for your needs. And you can tune it maybe on 500 epochs and get better results than I did. So yeah, feel free to play around with this and let me know. So before moving forward, I want to also show you the results. So basically, you can scroll up, and this is the results basically. So results here is for each frame is going to produce results. And first thing, it has the bounding boxes, which is an object. I'm going to show you the bounding boxes of a frame right after this. And then you have keypoints and masks. And again, I'm going to show you what keypoints and masks are, but it's not needed here. Basically, key point detection, or we can call it pose detection. And pose detection right there is basically going to predict points on a human body that represents their joints, predicts joints and key points. This is his head, shoulders, elbow, wrist, knees and toes, things like that. So this is it. This is what key points are. And you can have also mask detection. Actually, we can call it segmentation mask to show you exactly what it means. So this is another way of like exactly getting where the object is inside of an image and putting a mask on top of it, like this one. And this is another problem other than detection. But you can see here that this might be overkill for our use case, so we stuck by just detection of a bounding box. And since YOLO can actually have models of it for key points and models for it for masks, it chose both, and it chose boxes for the detections. Then it tells you that it has multiple classes that it can output. So it can output player, overlay, ball, clock, hoop, and score card. And then it has the original image. This is the image in pixel values. And yeah, this is it for all the frames that we have. After that, we are presenting the boxes for the frame at position 0. And we can see that it has multiple boxes. So the first box that it has the class of 2. And you can scroll up and see that 2 here is a hoop. So that's how we do the mapping. So the model just predicts a number, and this number is corresponding to a name of a class. Then we have the confidence, which I showed you, and then we have the data, which is basically the bounding box, and then we have the bounding box in different formats. So this is the XY width and height format that I showed you before, and this is the the XYXY format that I showed you before. We are going to be sticking by this XYXY format, and this is going to be the values of this box. Then we have another box right here with a class of 4. You can scroll up, see that 4 is a player. So this is a player box, and this is where it lies. Again, this is something that is 6 which is the scorecard or the scoreboard, then another player, and so on and so forth. Those are the boxes that we can loop over them, and we can store their output and take it from here. Now, before moving forward, I want to explain one more concept before we start with a heavy lift part of coding. Now, you can see here that each player is now detected as just a player, and you can see here just a class number, and then the box position. So for us to have a good analysis, we need to understand that this player is the same as the player in the second frame. And since each frame is being processed individually, we only have some boxes and some IDs, we don't have any way that says that this player in this frame is the same player as this player in the second frame. So you can think of it like as this is the second frame that I am writing in red. This is the frame that comes up next. This is the next frame of the video. But because we only have the XY, so we have the XY, and we also have here XY, and all of those are players. So this is a player and this is a player, which is basically we have 4 and 4. This is its ID. So there is no actual way to say that this person moved here. This is what we are trying to solve. This is what we call tracking, which is one layer on top of object detection. It has the ability to assign and to know that this player right here is exactly the same as this player right here. It can be done in multiple ways. So it can say that right here, this is a box in my current frame, and which box has the most overlap in the previous frame. So you can see that this is the previous frame and this is the red is the current frame. And the one that has the most overlap is this user. So it says that, okay, this user is going to be exactly the same one as this user. Things can be a little bit complicated and things can move a little bit faster, and there might be no overlap at all. And this might be harder for us to analyze. So with this logic, so it can actually also say that which one is the closest box to it, and then we can assign it to the same player. Again, this is a good approach, but it has its own also faults, and there are algorithms out there that we can use out of the box to track the players and the ball if we need to. And this actually predicts where the player is headed. So if the player was here, like here, then here, then it predicts, okay, then the player is predicted to be here. So is there a box that overlaps this position? And some also other detectors or like trackers, sorry, analyze some visual features like what the user is wearing. Is he wearing shorts? What color of shorts? What color of jersey? And then it also assigns the closest thing. So things here can be a little bit more robust, and that's what we are going to be using basically. So instead of predict, we can just run track. Like this. This is going to track the players and give them an ID over the frames, as well as detect them. So it will detect first and then track the players. So you can just save it, clear it, and then we run it. So now it's finished, and you can see there is one more thing that has been added, which is track, which is true. Now this is tracked, and it tells us that this track has an ID. Now each player will now have an ID, and it's going to be the same. It's going to help us identify how the user is actually, which user is which throughout the frames. So you can go to runs, you can go to detect, you can go to track, and then you can go to video 1. And you can see here that now the player has an ID. So even if I jump to the next frame, I know that this player has the ID. So I can compare this player was here, ID number 4, it was there, and in the next frame he is moving right in the next frames he is moving this way, and this is his current position. So right now I can just compare the IDs, see ID 4, which is player 4, for example, see his position here, and then see his position here, and see how much he moved without needing to do any processing, any matching of bounding boxes. And this tracker is going to do this automatically for us. And yeah, this is it. This is basically it. This is what object detection is, and then on top of it, this is what object tracking is. It is tracking the objects across frames and assigning it to the same entity, basically. So I hope that is clear right now, because we are going to write some code for that. And yeah, let's move forward with it. In our code, we are going to be customizing the detection code a little bit, the tracking code a little bit, and we are going to have different annotations. This is clunky bounding boxes right there. because this is a lot of information. When I presented to you the results, I had like an annotation underneath the foot, like a video game annotation of it. So I am going to also be doing that, since the bounding boxes and the players and 0.5 is a lot clunky and there's a lot of information and it's hiding a lot of the frame. So putting this data that we want underneath it, it's going to be a little bit better for us. So yeah, let's get to it. So close this and move back again to Visual Studio Code, and we are going to be writing our code one step at a time. So let's start by first coming here and deleting the runs folder, delete it, and then it will be deleted from here also. What we want to do is we can also delete this code. It was only for demonstration purposes and introducing you to Ultralytics. And then we can create a new folder called utils. And inside of this utils, we want to have some video utils that is going to read the video and output the video. So right here, we can create a new file called video utils.py. And inside of it, we want to read the video. So a good library for us that is going to help us read videos, read images, and process images and videos is called OpenCV. So we'll need to also download that. So you can go here, write pip install OpenCV, and come here, copy it, paste it right in, and then run it. I already have it, so you can just run it on your end and then continue the tutorial from here. So here, just import cv2, and we want to also import OS that is going to help us read files from our local machines, that is going to help us get different directory names, get file names, and things like that. So in here, you can just have define read like this video, and reading the video will take the video path. This is the path of the video that we are going to read. And then what we want to do is we want to have a cap, and this cap is going to open up the video. So it's cv2.video capture, and give it the video path. And then we want to read in the frames one by one. So you can have a list of frames. Then while true, we are going to loop over the basically the frames one by one. So while true, we are going to get the frame from cap.read. Now, basically, this opens up the video, and this reads in the current frame, and it returns the frame, and it returns the whether something is returned or not. So if something is not returned, like this, then this is basically the last frame, and we shouldn't be reading anymore, so we can break. But otherwise, what we want to do is that we want to read the frames, so frames.append of frame. So we just append the frame to the frames list that we have, and at the end of the day, we just want to return the frames. Now, this is it. This is how you read the video. Make sure to write it like read video and not make a spelling mistake like I did. And yeah, basically this is it. For saving the video, let's write code for saving the video as well, and then we can go and test it out. So save video. And for saving the video, we want to take in a couple of frames, the list of frames, basically, and an output path. So what we want to have is that we have output video frames, and this is just a list of frames, and get the path that I am going to be saving in. So output video path, like this. And what I want to do is that I want to check whether the output video path exists, like the folder exists or not, because if it doesn't exist, it might break our code. So if it doesn't exist, I'm going to create this folder path. So if not os dot path exists, so it's telling you that if the path or the folder exists, so os.path.directory name of the output path, like that. If it does not exist, then os.make_dir, which is going to make a directory. We are going to give it the os.path.directory name of the output video frames. Directory name gets the folder name of this directory or for this path basically. And yeah, when we do this, we just want to save the video. So we can like initialize a video writer, and let's have it an xvid format, and then we can have the output of the video, which is going to be cv2.video writer. Give it the output path, give it the video writer, give it the frames per second, which is 24 frames per second, or you can put it as like maybe 30 even, and then you can have the width and the height of the frame. So to do that and not hard code it, you can have the 0 frame and then get the shape of it of 1. This is going to get the shape of the frame, or when you remember when we ran it, the image was just a couple of pixels in a matrix, and this matrix has a width and a height, and basically this is the 1 is going to be the width of it, and 0 is going to be the height. So basically this takes in the width and the height from the output frames that are inputted to the save video function. And yeah, we are now ready to just loop over each frame and write it out. So for frame in output frames, output.write frame, then output.release. This is it, and very simple. We can create a new file called init.py, and this init.py exposes the functions inside of a folder to outside of the folder. So you can think of it as a gateway to access the functionalities inside of this folder to other things as well. So to access anything inside of this folder, put it in the init so that it can be accessed quite easily. So from .video utils, just import read video and save video. This is it. Just save it, go to your main, and here we are going to define a main function. So here, just define main, print hello world, like this. And in here, we just have the if name is equal to main, just run the main. This is the boilerplate code for any main function inside of Python. And for testing purposes, just run it, see if the hello world is there. If it's there, we can just continue on from utils, import read video and save video, like this. So for reading the video, we can have the video frames is equal to read video, and then call the input videos, like this, and take in video 1. That is going to read the video and put it into frames, and then put the frames right here. So you can have also a comment right there called read video. Then we can also have the save video. So save video, we take in the video frames, we put it into output videos and save it here as in whatever folder that we want and in whatever path that we want. I am going to have output video.avi. Make sure to put AVI in your output because this is the basically the output format that we chose. So now that we're all set, you can just run it. So there's an error that came up, and I think it's because here we are just giving the directory name of the list of frames. We should give it the path of it. So just try this output video path and then run it again. So right now it's finished. You can see that the output videos folder has been created, and inside of it there's an output videos AVI. Let's now check it out. So output videos.avi. There's nothing special about it. We just read the video and then saved it again. So yeah, from here we can build on top of that and run the detector and then run the tracker. So let's go back again to main. You can see that there is read video and save video. And let's now create a new folder called trackers. So right now this is going to be our trackers folder. This is going to have the logic for tracking our players and balls. So we can create a new file called ball tracker.py. We can create another file called player tracker.py, and then we can also have the init, of course, file, which is going to expose those classes outside of this folder. So let's now write the code to detect and track players. So we are going to import from Ultralytics, of course, import YOlO. And then we are going to use another library called Supervision. And Supervision is a library that is going to help us track the players after they're being detected. And you can go here to Supervision, and just like I showed you, like pip install Supervision will get you right to this page. You can just copy this, go to your terminal, paste it in, and just run it. And yeah, Supervision will have the tracker that we are going to use to track our players. And yeah, basically what we want to do is we want to create a class called class player tracker. Now, creating a class here is a good best practice for us to encapsulate all the logic inside of one class so that the code can be structured and well maintained. And we are going to also have one for the ball, one for other modules as well. And having it in class will make the code readable and better to produce. Now, you can see that Cody is giving me a suggestion right there. So you can just press tab to utilize it. We are going to be editing it a little bit on the way. But for now, the define init, this is the initialization function of the class, which is the constructor function, which is the constructor function that is called whenever a class is being initialized. So we then initialize the model. So we take the model path, and it's usually going to be one of those models, which is the player detector models. And it's going to initialize the model and put it into the model object. Then we are going to initialize a tracker, and we are going to be utilizing ByteTrack. And ByteTrack is a good tracker for us for this use case, and for other also sports analytics use case that is very convenient to use. Now, some other trackers might perform a little bit better, like Deep Sort and others, but Supervision is quite convenient to use in hands with the Ultralytics library. So up next is going to be a function to detect frames. And so we are going to detect objects inside of the frames. So this is the whole list of frames, and then we are going to specify a batch size so that we can run like 20 frames at one time and be more efficient in our processing time. And yeah, you can also decrease it or increase it based on your computational resources. Then the detections is going to be an empty list for now, but we are going to add it one at a time. And then we are going to loop over each frames from 0 to the length of the frame. And then instead of incrementing 1 by 1, we are going to be incrementing 20 by 20. And after that, we are going to take in the frames starting from I to I plus batch size. And in Python, even if the I plus batch size is more than the length of the frame, this is no problem. It will just stop to the end of the frames. Python is really smart at this, so we don't need to write any edge cases for that here. Right after that, to detect the batches, we can just give it run model.predict and then give it the batches, the batch frames, and then list the minimum confidence. The minimum confidence that we want is 0.5, which is 50%. I think this is quite enough for us to neglect any false detections. And after that, I am just appending this to the detections output list that we have. Now, this is it. This is how we detect frames, but we did not use the tracker just yet. So we'll create another function called getObjectTracks that actually detects the objects inside the frames first, like this. It detects them, and then it then will track them. So we'll have a empty tracks list, just like the detections list that we are going to fill out one at a time. Now, we can then loop over the detections one by one, and here enumerate just returns an index with the detection. So it just returns 0, 1, 2, 3, the index of the current detection. The index right here corresponds one-to-one with the frame number, so I called it frame number. Now, the detections themselves have the names. Now, I'm going to show you right here. So, if you remember, the names of the detections were like this. So, 0 is a person, 1 is a bicycle, 2 is a car, and this is one of the ways to know what is being shown, because in the boxes it's giving us 0 and it's giving us IDs, and it's not giving us basically names. So in order for us to know the names, I can get the names, detections.names, and you can see here that it was called names. So I'm just extracting it, putting this dictionary right there, and then I am getting the inverse of it. So I am going to put person here as the key, and the value of it is going to be 0, and so on and so forth. This is because I want to also look up the values by the name, so that it can be easier for us to look. So, for example, this here is looping over the items one by one, which is this dictionary one by one, and it's returning the key and the value, and it's then saving it as a dictionary where the value is the key and the key is the value. I am going to write it here as a proper for loop, because this is a one-line for loop and it might be confusing for people who are not used to Python. So I'm going to simplify it for you guys here. So this is called key value in cls.items, and items is how you loop over the dictionary in Python. And in order for you to have an output dictionary, you can just have this. Initialize the dictionary like so. This is an empty dictionary, and in here just have cls of key of value is equal to key. So I put the value inside of the key attribute right there and put it as the key as the value. This one-line for loop is exactly doing the same thing. Now, this is basically it. And then I want to run the tracker, and to do that I want to convert the ultralytics output to the supervision output, and from here I can have the supervision detections from ultralytics and give it here. So this is now a in the supervision format, and then I want to run the tracker, and to run the tracker I can have the detections right here with tracks, which is self tracker dot update update with detections. So right now I'm going to run the tracker on my detections, and I'm going to give it the detection supervision like this. Now, now that this is done, now that we have the tracks, I am going for each one of the frames, I am going to have a dictionary, and this dictionary is going to have a key value. Basically, a dictionary is a map, like you see here, and so I am going for each frame number, I am going to have an empty dictionary like this that I am going to fill, where the key is the ID of the player and the value is going to be their bounding boxes. So basically for now I'm going to have for loop for frame detection in detection like this with tracks like that. So I'm going to extract the bounding box, and the bounding box is in the position 0. Then it's an array, it's a numpy array, so I'm going to make it to a list. So this now has the bounding box. We also have the class ID, and the class ID here is just the, again, it's just a number like this, like 0. So you can go here and assign the class ID, which is frame number of 3, and this is the class ID. Then we are going to also extract the track ID, and if you go back here, there is track, and when we used to have the track is equal to true, there was a track ID, and to extract it right there, it's in position number 4 like this. And because now the model has different classes, like a ball, like the referee, like the basketball hoop, like the clock, we want to ignore everything else other than the player. So we just want to keep the player for now. So if CLS of ID is equal to CLS names inverse, and this is where the inverse is good, because instead of just writing the class ID of the player, I can make it more intuitive for us and just here write player, and now it's more readable for us, and it will match it with the player ID and put it right there. So we can have the tracks of frame number. So this tracks right there, I appended an empty dictionary in the frame number position, and I am going to add a key for the dictionary right there. The key here is going to be track ID. This is the ID of the player, and the value of it is going to be the bounding box. I'm going to put it into another dictionary, but you don't have to. I am putting it right there to be more intuitive about what it is inside of this track ID. And it also gives you the ability, because if you want to bundle up different information inside of this object, you can simply add different keys and put it right there. I won't be adding keys, as this is going to be less intuitive for other readers to when reading the code. I will try to utilize the bounding box in other classes as well, so that we don't bundle up a lot of data inside of this. So basically this is it. This is going to be returning the classes, and yeah, this is how it is. This is how we detect players. Now, to proceed forward, we can actually test it out, and then we can write the ball trackers as well. So in the init, you can go here, run from dot player tracker import player tracker. And this is how you import it, and then you can go back to your main, and then we can import it there as well. So from here, right, from trackers import player tracker, like that. So we can now initialize the trackers. Initialize tracker, then write player tracker is equal to player tracker, and then give it the path for the model. The path for the model is going to be models like this, and it's going to be the player detector.pt. So just give it the correct path for the model, and now it initialized the tracker. Now what we want is to also run the tracker as well. So let's call this run trackers. So what we want to do is we call it player tracks. We call it player tracks, and give it the player tracker, get objects, and then give it the list of video frames that we have. Now this is it. This is going to produce the player tracks, but it doesn't actually draw anything on top of the video. So the video is now empty. So before proceeding, we just want to make sure that everything is good. So we can just print the player tracks and see how it is, and then we can proceed from there. So we ran into an error right there. So let's go back to our player trackers, and you can see here that it's detections. Actually, it's detection. So it's the current detection that has the names and not the list that has the names. So just save it, clear this, run it again, and yeah, let's wait for it to finish. Now, while waiting for it to finish, you can notice that running this model on all the frames is a little bit time consuming. So we'll be writing something that is going to be saving those detections, so that every time we run, we can use the saved output and not run it every time. This is going to save us a little bit of time while developing the code. And yeah, this is what we will call stubs. So we'll be developing this next. One other problem, there are too many values to unpack. I apparently wrote this by mistake. So just delete it, save it, and run it again. Now you can see the output right there. So for each frame, we have an ID, which is the tracker ID, and then its bounding box, then a tracker ID, and then a bounding box, and then a track ID, and then a bounding box. And this is how it is right now. So this is very good for us, but again, before proceeding, we want to have the ability to save this output so that we can read it every time we run. Yeah, it's going to speed things up a little bit for us, so that each time when we run, we can use a checkpoint basically, and not run it from scratch. So basically, we call this checkpoint a stub. So we can have a stub path, which is a place where to save the checkpoint. So stub path, and the stub path is going to have a default value of none. which is if it's not there, then basically we run it from scratch. And we are going to also have a read from stub is equal to false. Basically a flag that tells us whether we should read the stub or don't read the stub at all. So we are going to be using a library called Pickle for reading and writing the stubs. And for Pickle right there is a very convenient way to write anything in Python in a file. So you can have pip install Pickle, and you can see Pickle 5. You can just copy it and then paste it right here, and it will start installing. You can start clearing here. And because we are going to be using this stub logic or like checkpoint functions in multiple other places as well, I am going to be adding this into the utils. And let's call this stubs utils.py. Now in this stubs utils.py, we can import again OS because it will help us to determine which is the place that we are going to be saving things in, and we can create also a folder with it if the folder does not exist. And we can also import Pickle. And Pickle here is the library that is going to help us save and load the stub. So define save stub, which is going to be the function. We are going to take in the stub path. This is the place or the path that we are going to save the stub in, and then we are going to take in the object that we are going to save. So first, we check that if the directory name exists or not. If this directory does not exist, then we basically do it. So what we do is we just have this again. So if the directory exists, so if the directory does not exist, we just create it. And this avoids us to, because if we try to write something in a directory that doesn't exist, it might break. So you need to create the folder first, and then you can save the file. So basically, if we are going to make sure that if stub path is not none, so if it's none, then we don't have to save anything. If it is, if it's not none, then we save it. So to save a Pickle file, we can have with open, and then we give it the stub path, and this is the path to open in, and we are going to write bytes. Pickle is going to be in bytes so that we can save anything at all. And then we just run pickle.dump and then give it the object that we are going to save, and then we are going to give it the file that we opened. This is basically it. This is basically what save stub does. It just saves in any object that you give it. We want to also have a read stub. So define read stub. And in this read stub, we want to have read from stub. And we want to have read from stub is going to be a Boolean, which is true or false. And then we are going to also have a stub path. So this stub path right there. And in here, we are going to check if read from stub is equal to true, and if you left it like this, this is actually checking that it's true or not, and stub path is not none, and then we can check that it's there. So if os.path exists, if this path actually exists, then we read it. So if it exists, then we read the stub path, and the way that we read it is that we open it, but right now here we opened it as write bytes. Here we have read bytes, and then we load it and return back the object, basically. So you can have like this, object is equal this, and then return back the object. If the object does not exist, or read stop is equal false, or the stop path is equal to none, I can return none. And here I know that this object does not exist, and I should run the detector and the tracker, and not rely on the stop. And yeah, this is basically what the stop logic is. So you can just save it, open the init here again, and from stub utils, import save stub and read stub, and then go back again to your player tracker, and then we want to import this, the save stub and read stub functions. So from here, we can have something called import sys and sys dot path dot append, and then we go back one folder, so we can go back here and import from utils. So from here, from utils, import read stub and save stub. So basically the sys is going to help us to go back one directory so that we can import the read stub and save stub. Now let's utilize those functions. So before we do any detections or tracking, we can check this. So basically we can have tracks equal read stub like this, and we can give it read from stub and the stop path. And if any, and if those conditions fulfill, the tracks is not going to be none. So if tracks is not none, what we do is that we have another check that says if the length of tracks is going to be equal to the length of frames that we have, then this is the correct stop. So basically what I'm saying is that the number of tracks that we have needs to be equal to the number of frames. And if it's not equal, basically that means that we were running on a video and then now we're running on another video, and now we need to run the detection again and save a new stop. So basically, this is what I'm doing right here. I'm just checking that the frames the length of the frames is the same as the length of the tracks. And if they are not, I am going to be running the tracker and the detection again. But if they are equal, I can return the tracks and then not have to run all this again. And at the end of here, I want to save the stub. So save stub, and I'm going to give it the stop path and the tracks. So this is it. This is how you integrate checkpoints into your code so that when you run it one time or two times or three times, you don't have to wait for the detection to finish again. Now, we are going to run the main again right now, and we are going to wait this time, but the next time the stub will be created so that we don't have to wait again. So in here, we want to have player detections. So for here, read from stub, and read from stub here is equal to true, and stub path. And the stop path, I want to put the stop path into the stubs folder. So stubs, and inside of the stubs folder, I want to have a player track stubs. So player track stubs, and the extension for pickle files is .pkl. And this is it. The first time when it sees this, although the read from stub is equal to true, it will not find the file, so that it will run the detections and then save it in the correct path. So yeah, that is it. So let's now run it and see the output. Again, you can see here that it's basically running one frame at a time, so you need to wait a little bit for it to finish, and then we can see the stubs after it finishes. So now it's finished, and it also produced the same output with printing the player tracks. But if you refreshed here, you can see the stubs, and we have the player track stubs. So right now, if you cleared and if you ran it again, you should have way less time in the, see, it already finished. This is now just read the stubs, and it did not run the tracker again. This is going to help us develop the code a little bit faster. So while that is done right now, we are then saving the video, but we are not saving any annotations for the video. So this annotations right here, this is a plain video of the same input video. So what we want to do is we want to introduce a drawer that draws those annotations for each frame. So let's now have a new folder called drawers, and this is the classes that will draw the output. And of course, we are going to have the init to expose functions and classes to outside of this. We are going to have a utils.py that is going to have utils specifically for the drawers. And then we are going to also have the player tracks drawer.py. So player tracks drawer.py. And inside of here, we can create a class called player tracks drawer.py. So player tracks drawer, like that. So again, we need to have an init function, and this init function is going to be the constructor. And we can just pass it for now. We don't need to define anything here now, but we do need to define a draw function. And this draw function is going to be the same function for all of the drawing. It's going to be the same draw for all of the drawers, and this is for consistency, so that if I open any drawer, I know that it's going to have a draw function, and inside of the draw function is going to be responsible for drawing our annotations. So this draw function basically takes in the self, basically takes in the video frames, which is a list of the current video frames. It takes in the tracks, and yeah, this tracks is going to be the tracks for the players. So to start, we can have an output video frames that is going to be an empty list. Then for frame number and frame enumerate video frames, what I want to do is that I want to annotate one frame at a time. So this is the frame. So what I want to do is I want to copy it, because this frame is copied by reference and it's not copied by value. So you can have a copy of it so that you don't contaminate the video frames that are inputted from here. Then you can get the player dictionary, which is this dictionary of players for each frame, which is going to be the tracks of frame number. So this is the frame number, and then this is the tracks, and I'm getting the player dict. Now, what I want to do is I want to loop over each one of those. So for, I want to draw the player, so draw players detections, actually tracks, like this. So for track ID, which is actually the player ID, and the player in player dict.items. You can remove this. So basically this is the track ID, player ID, and the track ID and the player bounding box, which is this part. And yeah, this is basically it. We want to, if you remember, we want to draw an ellipse, like the gameplay of a PlayStation or something like that, instead of having a clunky bounding box. So what we do is that we want to have a frame is equal to draw ellipse, and this function is not there right now. We are going to write it. That takes in the frame, and it takes in the player bounding box like that, and it takes in a color. So the color that I'm going to choose right now is going to be this one, which is going to be red. Now after that, after we draw it, we can have the output frames like this, dot append, and then we write the frame. So we append the frame on the output video frames, and that is it. So the draw ellipse function is going to be a function that we are going to have in the utils. So you can go back to your utils, and let's import CV2. CV2 is going to help us draw in top of frames, so this is a good library here also. So let's write the function that is draw ellipse. So have the define draw ellipse, and it takes in a frame, it takes in a bounding box, it takes in a color, and it takes in a track ID that has a default of none, because sometimes if we don't want to present track IDs, we have this option basically. So what we want to do is we want to get some statistics from the bounding box, like its width and its center. So we can also add that into the other utils folder. So right here, we can add bbbox utils. And yeah, it's going to have a lot of bounding box functionalities that we might use in other places as well. So bbbox utils .py, and inside of here we want to get center of the bounding box, get center of bbbox, and in here it just takes in the bounding box and it returns back the center of it. So we take in x1, y1, x2, y2 as the bounding box. We just decompress it, and from here we return the x and y coordinates of the center, which is going to be the int of x1 plus x2 over 2 plus and the other number is going to be y1 plus y2 over 2, and this gets exactly the center position of the bounding box. What we want also is we want to get the width of the bounding box, so get define get bbbox width like this, and give it a bbbox as the input, and the width of it is going to be the x2 minus x1, and x2 is going to be more than the x1, so we don't need to put it in absolute value. So this is going to be the bounding box positions. Also, you can have it as bbbox of 2 if you know that this is the second position, minus bbbox of 0. Whatever is more intuitive to you, I am going to leave it like this. Now in the init, from bbbox utils, I want to get center of the bounding box and the get width of the bounding box, and from here I want to also import them But to import them, I want to go back one file. So I'll go back with import sys dot append, and then I go back one folder. And from here, from utils, import get center of the bounding box and get width of the bounding box. And now we are ready to proceed. So basically the y2 of the bounding box is going to be the BB box of 3, which is, this is the maximum y of the bounding box. And we want to have the x center and y center of the bounding box, but instead of calculating them, we can just run get center of the bounding box, and then it has the center. We can also calculate the width of the bounding box. So we can have the width is equal to get box width, and then we want to basically draw an ellipse. An ellipse is just a circle that is not perfectly round. It can have like slight deviations. It can be longer, more than it's like it can be a little bit long or short on width and height. So yeah, I'm going to just draw an ellipse, and I'm going to give it the frame. I am going to give it the center of the ellipse, which is the center of it. The center of it is going to be the x center, like this. But it's not going to be the y center, it's going to be the y2, which is going to be the foot position of the player. It's not going to be the center of it. So right here, it's not going to be used, so I can just have it as an underscore. And then the axis that is going to form how wide or how deep the ellipsis is going to be. The axis of it is going to be defined by the width. So for me, I'm going to make it as int of width, and it's depending on the bounding box width. The ellipse is also going to be the same width. So it's going to be the int width, and the other axis is going to be like 0.35 times width. And to show you a little bit more, you can just write here ellipse. So basically it has two axes, this and this, and it defines it how wide is it is going to be on the y-axis and how wide is it is going to be on the x-axis. This is basically it. So basically I'm giving it the width and 0 times 35 times the width, and this is going to be like a good estimate for us. And another thing that we want to have is that we can have the angle of it to be equal to 0. And the angle will define whether this is like 90% like this, or is it going to be stretched in different angles like diagonally or anything else. So here I'm going to leave it as angle that is going to be equal to 0. The start angle. So basically, if you saw the output position, the output of my previous runs, so I'm going to show you this. So the output right here draws an ellipse but leaves something here as empty. So it starts with 45 degrees angle and ends at 235. And this part is not drawn. So this is what we are going to do. So we are going to have a start angle of negative 45 and an end angle of 235, like this. We are going to define the color as the input color that we got. We are going to define the thickness as going to be 2. That's how thick the line is going to be. And then we are going to have lastly the line type. And it's going to be the CV dot line 4. This is the line type that we chose for this. Now there's a missing bracket right there, so make sure to add it. And here it's going to be CV2, and this is going to be line 4. So this is going to draw the ellipse right there, but you can also see that we also have a ID, which is the track ID that is printed right underneath the ellipse or over it a little bit. So we can define this rectangle position, and then we can have this rectangle position and write the track ID inside. So let's define a rectangle width, which is going to be this rectangle basically. So rectangle width is going to be equal to 40. Rectangle height is going to be equal to 20. And then we are going to define the location of this rectangle, which is x1 rect is going to be x center of this minus rectangle width over 2. And this is going to be integer division. So it just takes the width and divides it by 2 and starts from the center right there and goes here a little bit to the side. Now we are going to do the same thing for x2, but instead of subtracting, we are going to add. So just copy it, come here and add instead of subtract. And this is going to be x2. Then we are going to have y1 rect. The y1 rect is going to start with the y2 minus a little bit of a buffer, which is the rectangle height, over 2 also, because we want to have the half of the height. Then we are going to add a buffer of 15. The same thing we are going to do with y2 rectangle, but instead of subtracting, we add. Then what we want to do is we want to check if track ID is not none. Then if it's not none, then we draw the rectangle, and then afterwards we write the track ID. So CV2 rectangle, we give it the frame right here. We give it the position of the rectangle, which is x1 rect, y1 rect, and then x2 rect, y2 rect. Then we give it the color, and then we say that it's going to be a filled rectangle. This is going to be -1, but we can also specify it in a better way, which is going to be CV2 filled. And this is going to be it. If you highlight it, it's going to be an int, which is going to be -1. It's kind of the same thing, but this is a better readable way of doing it. And just in case that this is not basically an integer and this needs an integer positions, I am going to be casting those two integers, although they should be integers, but I'm just doing this for safety. And then the other thing that I am going to do is I want to put in the text. So basically, if the x1 text, which is the place that I'm going to start writing text in, is going to be the x1 rectangle plus 12, which is a little bit of a buffer. But if the track ID is more than 99, which is like a 3-number, which is basically a 3-number track ID. This usually doesn't happen because we have less tracks than this and less people. So we just subtract 10. And why subtract 10? Because I wanted to start a little bit earlier on x-axis so that we have room for 3 numbers and not go outside of the rectangle. Then afterwards, we just put text, which is we are going to write the track ID. So what I'm going to have is that I'm going to give it the frame, give it the track ID as text, then give it the x1 and y1 rectangle positions, but instead of -15, I'm just going to add, -10, I'm going to add 15. Afterwards, I'm going to specify the font size, the font type as Hershey Simplex. I am going to specify the size to be 0.6. I am also going to specify the color, which is going to be black, which is 000. And then I am going to specify the thickness. Then I'm going to specify the thickness of it, and it's going to be 2. Now, this is it. This is how we draw the ellipse. Now, let's return back the frame. So, in here, return frame. So, we can go back here, and from here, we can write from utils import draw ellipse. Draw ellipse like this. So make sure to put a dot right here to say that it's the utils file inside of this directory. So basically this is how we draw the ellipse in the players. So let's expose the player tracker drawer to outside of this. So we can have the dot player tracks drawer import player tracks drawer, and from go back to your main, and from here from drawers like this, import, and then run player drawer. Now let's draw the output. So before we save the video, we can delete this, and then we can have draw output. And let's first initialize the drawers. So initialize drawers like this, and a player tracks the drawer like that is equal to player tracks drawer, which is initializes the player tracks drawer. Then what we want to do is we want to draw the tracks. So let's draw object tracks, and from here I will have the output video frames as player tracks drawer dot draw. Give it the video frames and then give it the player tracks, and then have this as the output. So the output video frames is what is going to be saved right there. So this is it. So just make sure to save everything and then clear it and run it again. So there's an error right there that is telling us there is an error here in the sys. So here you can just write sys.path.append. Then save it, clear this, and run it again. It says that it doesn't see a BB box in the player. So let's see the problem right there. In order for us to know why is it doing that, so I can here write print player just to know what's inside of the player, and then just run it again. So you can see that it's a box, it's not a BB box, so you can just edit that like this. Delete that. And one more thing, draw ellipse takes in the track ID to actually draw it. It can be left empty, but I want to draw it, so I'm going to also provide it right there. So save it, clear this, run it. And line here, I think it's all capital, so you can go back here, make sure that it's all capital. Line 4, save it, clear, and run again. Now it's done. So you can go back here to your output videos. Again, basketball analysis, output videos, open this. And now you see the annotations that we have, which is the ellipse that is underneath the players, as well as the track IDs. And yeah, everything is looking good. I think the frames are quite choppy. I don't know if it's my I don't know if it's my PC or something like that. So I'm going to close it and see whether we need to edit something in the code, or is it something on my PC. Give me a minute, I'll let you know. So in here, I'm appending a frame for each track, and you know that one track has multiple frames, so you can and has multiple detections. So you can open this up. You can see that 1, 2, 3, 4, 5, 6, 7, 8. I think there are 8 detections right there. So I'm adding 8 frames of the same thing. So that's a problem that I had. So just make this outside of the for loop, and every time it loops here, it adds on top of the frame. So it just draws one ellipse at a time, and then puts it in the frame, and then utilizes the frame again to draw the others. So right here, you can just clear it, run it again. So it finished. You can go here and see. Yeah, so that's now running a lot better. So we now have red ellipses instead of using the same colors as the teams. But yeah, we are going to be adding this later on. Now let's move forward and detect the ball up next, and also write the drawer for the ball so that we can see the output of it. So for the ball tracker, go to the file in the trackers called ball tracker, and then we can create a class called ball tracker. We can define an init file, init function, that is going to be a self. We are going to have a pass. So we're going to be using YOLO as well. So we are going to be using a different YOLO model from the models folder. So we have a player detector and a ball detector. So we're going to be using the ball detector now. And yeah, and we don't need to have like a tracker for the ball, because we only have one ball. So what we want to do is basically we can basically ignore the tracking for this ball. Just use the detections. So from Ultralytics, import YOLO, then self.model is equal to YOLO, and basically it takes in the model path. So model path, and then I write it here. Now, when that has happened, so when that's done, I want to also have the same detect frames as the one that I have in the trackers. So we can just copy this and paste it right there. So this is the detect frames, and then I will have also a get object tracks, and then it will have the same stub logic. So I can just copy paste this, and I know that in the player tracks we have the utils and we have the sys, so we can just copy it as well. Paste it right here in the ball tracks, like that. And right now I've pasted this in the wrong place, so you can just cut it and paste it here in the correct place. And make sure to have the get object tracks in the correct place. And at the end of the day, we want to also save the stubs and return the tracks. So let's do that also here. Now, what's in the middle is going to be a little bit different. So we are going to have the detections, and the detections is going to be equal to self.detect frames, and we are going to give it the frames as well. like that. Now, in some scenarios, there might be a like two balls or something like that in the court, or maybe a misclassification. So we just choose the one with the highest confidence, basically the detection with the highest confidence. So in order for us to do that, and we can keep the same format as we had in the player detections. So we can have the for frame num and detection in enumerate and get the detections, and like this. And inside of the detections, you can have different stuff. So right here, I'm doing the same thing that I'm doing with the player detections, which is I'm looping over each detection. And basically, I am going to be utilizing the detections from here there. Then we have the class names and the class names inversed, and then we can change it to supervision format for ease of use. So right now, let's have the class names and the class names inversed. Make sure that it has the correct indentations. Don't think that they are right now. And for this, we need to also import supervision as SV. And right now we are ready. So for each one, we are going to have the tracker, which is the tracks.append, again an empty dictionary, and then we are going to fill it out, but we are going to only have one ball. So we can say chosen BB box, which is the box that will have the highest confidence. Then we are going to have the max confidence, and this max confidence is going to be 0 for now. Then we are going to loop over each detection and determine whether it's a ball. If it is, then we are going to determine whether this is the maximum till now or not. If it is, then we are going to override the chosen box, and if it's not, then we are just going to skip it. So let's write that basically. So frame detection in detections supervision, and we want to get the bounding box, which is the frame detection of 0.toList. This is the bounding box position. Then we have the class ID as well, and the class ID is going to be in position number 3. Then we are going to have the confidence, and the confidence here is going to be position number 2. And if the class ID is equal class names of inverse of, again, ball. So if it's ball, then we do something. If it's not, then we don't. Then we skip it. If max confidence is less than the confidence, then we got. So we have the chosen BB box like this is equal to the BB box. So the chosen bounding box is equal to the bounding box, the current bounding box that we have. Then we are going to have the maximum confidence is equal to the confidence. This if statement is a standard if statement that can get the maximum while looping. So what it does is that if the maximum confidence is less than the current confidence, it gets and it overrides the maximum confidence with the current confidence, so that anything that is below, it ignores it, and anything that is above, it will enter this if statement again. Then the chosen box is going to be the box that I have right now, which is going to be the maximum box. So in here for the, after we finish, if the chosen box is not none, basically there is a best box. Then we have the tracks of frame number of 1, and 1 here is hard-coded as if it's one ID, one track ID, and the output of it is going to be the BB box of chosen box. So note here that if the ball is not detected, it's going to be an empty dictionary for the frame position. So we are going to have, for each frame, we are going to have a track appended, but if something is not detected or the ball is not detected, it's going to be an empty dictionary at this position. And this is going to be easier for us when pre-processing the frames one by one, so we don't have to do any sort of wizardry to know which frames are skipped or not. So one thing that I noticed is that this is BB box, and I think I misplaced this, so this needs to be also BB box. And for that, we can just delete this pickle file for the player tracks, and also go to the drawers right there and right here BB box. Now this is going to be the player tracks, and for that we want to also export it. So from .player tracker import ball tracker, and for that we want to also import it here. So make sure to import it right there. Then we want to also call it the ball tracker, and for ball tracker right there, we can put it in the initialize tracker and call it ball detector model, the same name that we gave it, like this. And get the ball tracks by having the ball tracker get object tracks video frames, then read from a stub which is equal to true, and then we assign a stub path. So this is now done. Now the last part is to draw basically a pointer to the ball, and I can show you what I mean. And basically the output videos, and you can see that the ball has a pointer, a cream pointer on top of it, instead of having a bounding box. And this is a little bit of a cleaner way to do it. So we can have the same thing right there. So in the drawers, we will have a new file called ball tracks drawer. So call it ball tracks drawer dot py, and inside here have a class of ball tracks drawer, and it will have a init function, of course. And inside of this init function, we can have a color for the pointer for the ball, which is ball pointer color. And for the ball pointer color, it's going to be green, so it's going to be this. And in case you're wondering what are those numbers, those are RGB numbers, or BGR numbers, which is blue, green, and red. And this is 0. Those are numbers from 0 to 255, and those are basically can create most of those colors, most of the colors that we see by combining only those three colors. And here, by making this 0 and this 0 and this to the maximum, this is only going to be green. So you can see RGB colors or RGB colors, and you can understand that each RGB has a different color, and different combinations of them have different colors. So you can play around with them if you want, but it's not essential for us to have like perfect colors or something like that. So define draw self video frames, and inside here you can give it also the tracks. So output, again, output video frames is going to be an empty list. Then I am going to loop over the video frames. So frame number and frame in video frames, enumerate video frames. The first thing that we are going to do, we are going to copy it. So we are going to copy the frame, and then we are going to get the ball dict, and the ball dict is going to be the dictionary at the current frame, which is the ball dict of tracks of frame number. Then we have the track ID. We don't actually need it. It's going to be one for all of them. Then we are going to loop over the ball dict items. We are going to be extracting the bounding box. So the track here might not have actually the bounding box and might be an empty dictionary. So for this, a guardrail for that is to check if bbbox is none, then we continue. We don't draw anything like this. But if it's not none, then we can draw whatever we want. So right here, we are looping over each track, then getting the bounding box, and then what we want to do is that we want to have the output frame, the frame that we copied, and we want to draw a triangle, and this function we are going to write very soon. Then we are going to have the frame, ball, and the BB box of the ball, like that. And we can also give it the BB box right after this. And then we can provide a color, which is the self dot ball pointer color, like that. So the thing that we want to do right now is to write the draw triangle function, and in here we can have the define draw triangle function, and the draw triangle function takes in a frame, a bounding box, and a color, and then what it does is that it extracts the y position of the bounding box, and then it extracts the width of it. Then it's going to extract the center of the bounding box in terms of x position. So right, like we did right there, so we can just copy this, put it here, and we can call it x. And then the triangle points is going to be 3 points, basically indicating the triangle. So triangle points is equal to be a numpy array, and a numpy array should be installed by default when you install OpenCV, but if it's not, then you can just pip install a numpy. So you can import numpy as np, and basically what it does is that you will have the first position is going to be x and y. The second position is going to be x minus 10 and y minus 20. And the third position is going to be x plus 10 and y minus 20. So let me try and explain this to you. So right there, we are going to have the x position and y position like this. Then we are going to move 10 pixels to the left and then 20 pixels up. So it's going to be right there. This is going to be the second position, which is this point. And then this is the same. So move 10 pixels right this and 10 pixels up. This needs to be 20. Sorry about that. This needs to be 20. Let me try and do it again. So yeah, this point, then move this like this, and then this is the last point is going to be plus 10 and then minus 20, and then you can draw a rectangle like this. This is an inverted rectangle that is pointing downwards. So this here is, this here is this position, and this here is that, and this is this. I hope this is like very straightforward, but this is the 3 positions of the rectangle basically. Now, what I want to do to draw the triangle is I'm going to use a function called draw contours that is going to draw the triangle, the inside of the triangle. It's going to fill the inside of the triangle, and it's going to also draw the borders of the triangle. So cv2.draw contours, which is going to draw anything that we want based on a list of edges. And since this is representing a triangle, it's going to draw a triangle. So I'm going to give it the frame. I am going to give it the triangle points. I am going to also give it a contour index of 0. The color to be the same color that I passed in the function. And then I'm going to tell it that this is going to be filled. So this is going to be filled, and then I want to have another one that is going to only have the borders of it. So this is going to be 2, and then return frame. And yeah, this is basically it. So you can go back to your ball drawer, and from here, from utils, import draw triangle, and right now we are going to draw the triangle and return it. So just save it, and note that in the stubs you don't have anything right now, so it's going to take a while to run both models, but after that they should be saved. So let's save everything, and let's now run it. So it can't find the ball detector because I think I missed the .pt extension. So we can go back to the initialization, and from here you can just add the .pt. Save it, clear, and run it again. So it's called ball detector model. So maybe just copy paste the name, save it, clear, run it again. So now it's done, so let's see the output. So you can go back again to your folder, output videos, then see the output right there. And it doesn't have the ball output till now. I think I know why, because we did not have the drawer initialized or actually exported. So from here, run from dot ball tracker, import ball tracker drawer, save it, go back here, import it, then we initialize it. Then after that we want to have the output video frames, which is going to take the output video frames ball tracks, and yeah, that is it. We can then clear, run it. So basically I imported this wrong, so just ball tracker drawer, save it, clear, and run again. It doesn't see the draw triangle from the utils, so just make sure that it's spelled correctly. It is spelled correctly. Go back here. From this util, just write dot utils. So save it, clear, and run again. So it ran and it's finished. So right now you can see that the ball is being detected right here, and the green pointer is being pointed to the ball. So yeah, this is quite good. You can see some misdetections here and there, and we'll take care of this very soon. So one of the things that I found is that this is an all green triangle, and I specified to have it a border. So let's see what happened here. So you can see that it will have, so you can go to the ball tracks drawer, and in the triangle right there in the utils, you can see that, yeah, so basically this is the filling and this is the border of it. The border needs to be in a black color, so I am going to change it to that. So instead of getting the color, I'm going to change it to 0 to 0 to 0. Save it, run it again, and then we can see the results. Make sure to close the video before you run again, because otherwise you can get this error. So if you get it, you just come here, close it, and then run it again. So we can clear it, run, and it shouldn't take a long time because of the stubs. Now it's finished. Open it again, and you now see a better the black border. So you can see that there are multiple misdetections. So this is the ball. You can see that it's in the correct place. Now it's on the head of the guy. That's a problem. And now it's in the knee. So we want to have like the detections that are far away from the previous detections like this to be totally removed. This is like something that is a giveaway that this is a wrong detection. And in any detector model, you can have wrong detections, but yeah, we can just have some logic to deal with this. So right now, we just want to have, based on the distance of the previous detection, remove any detection that is more than a certain threshold. This is what we are going to be doing up next. So yeah. Go back again to your code, go back again to the ball tracker, and you can clean things up a little bit by closing up some tags or tabs like this. You can leave the main.py and you can leave the trackers. And from here, we are going to actually close the drawer as well and open up the ball tracker. We are going to write a function that is going to suppress some detections based on the distance from the previous detection. And yeah, let's do that first. So we can start off by define remove wrong detections like this, have it self, and ball positions like that. And what we are going to do is that we are going to have a maximum allowed distance, which is equal to 25. Then last good frame was index is equal to -1. So what I'm going to do is that I am going to have a maximum allowed distance of travel of 25 pixels, and based on the number of frames that the ball disappeared in, I am going to multiply this by it. So this is the maximum allowed distance between 2 frames, but if the ball disappeared for 3 frames, it's going to be 25 times 3. Basically, if this distance is less, then I'm going to consider this as a detection. If it's any more, then I'm going to suppress this detection, basically. And yeah, this is it. So what I'm going to do is I am going to have the for I in range length of ball positions, and then I am going to get the current bounding box. So you can remove this. So current BB box like this is going to be equal to the ball positions of I, and then get, and it's get 1 because we only have one track, so we can get it. And if the track does not exist, I am returning an empty dictionary. Then if it then we can get the BB box object, and also if it doesn't exist, I can return an empty list. So this is basically the current bounding box position, and it might be not defined, it might not have a current position because of a detection that is not being done or something like that. So if the length of the current bounding box is equal to 0, I am going to continue. I'm not going to evaluate anything. And then if the last good frame index is equal to -1, I am going to get the last good index is equal to I, and I then going to continue. So basically, if this is going to be the first detection of a ball, I am going to just mark it as the last good detection, and then I'm going to continue because I don't have the distance of the before position, because this is the first position. So basically, what I'm going to do is I'm going to have the last good box, and the last good box is going to be the ball positions of the last good frame index, and then I am going to have this get again, this get function like this, and then I am going to have a frame gap, because like I said, this is 25 pixels per frame. So if it disappeared for 3 frames, for example, we can multiply 25 times 3. So I want to know how much is the frame gap. So the frame gap right now is I, which is the frame number. This is the frame number, minus the last good frame. And then I can have the adjusted max distance. And this adjusted max distance is going to have the maximum allowed distance times the frame gap. So you don't have to have this 10. So this is the adjusted distance, and then we can calculate the distance between the last good position and the current position. So we can have calculate the distance between the last good BB box and the current position. So now we just want to calculate the distance between the current box and the last good box. And for that, we are going to use also NumPy here, which is an array or like a matrix library. So in order for us to do that, we can calculate the distance by having the np.lin_nalg like this function dot norm, and what you give it is that you give it a NumPy array of the last good position, last good bounding box of the first two, which is the X and Y position of the first two boxes. Then we can have also the X and Y positions of the current box. So current box of also the x and y, the first x and y positions. And yeah, if this is more than the adjusted distance, then we need to suppress this detection, else we can leave it as is. So we can have the ball positions of I is equal to an empty dictionary. So if it's more than the adjusted maximum distance, we can just ignore it. We can move forward and we can suppress it by just overwriting the bounding box with an empty dictionary, which is basically an empty detection. Else we are going to have the last good frame is equal to the I. So the last good frame is equal to the index of the current frame. Now the output here is going to be the ball positions, and this is it. So we can now go back here, and after the ball tracks has been done, we can just run the remove bad detections. So right here we can have remove wrong ball detections like this, and ball tracks is equal to ball tracker remove wrong detections and give it the ball tracks. This is it. So we can now run it again and see the output. Hopefully we don't see the output with very far away misclassifications. You can see here that if we slowed it down a little bit, the guy's neo is not detected as a ball anymore. Some misclassifications were done here as well. They're also suppressed. But I found the problem is also that all those frames there should be detections in it, and it's being suppressed. So I'm going to trace back Y and let you know the fix. So I understood the problem is that here I'm adding the frame gap. I need to multiply it. So basically multiplying the frame gap. So 25 multiplied by the frame gap, not added. So save it, clear the terminal, and then run it again. Open up the folder again, and then we can see more detections right now. And yeah, everything now is working good. So you can see here that it's being detected. The guy's knee is not being detected as much. Some misclassifications were there, are not also being detected. And yeah, this is way better than we used to have. Now, another problem that we want to fix is that right here, the frame is, for example, the ball is being detected, and those balls are not being detected right there, and then it was detected right here. So the idea is that it was moving in a linear fashion, and it can be basically interpolated. So let's say that it was in position X where X is equal to 20, and now it's and then it appeared a couple of frames later where X is 30, and for example it was 10 frames apart. So basically it increases 1 pixel each and every frame. So this is what interpolation is. It's going to try and estimate the positions of the ball depending on the previous known position of the ball and the current known position of the ball, and the frames in between that the ball disappeared in. It's going to try and divide the distance between it by the number of frames. And yeah, we are going to be doing that next so that we can have more detections of the ball, and when it disappears, it just have some estimations of the positions of it. So we are going to be using pandas for that because it's one of the most convenient ways to interpolate data. And pandas is just a data frame manipulation library where you can just import CSVs, Excels, and things like that and make all sorts of operations. We won't need to do this right now, but we will use one function that it has, which is the interpolate function. So I'll show you also how we can do that. So I'm going to have a temporary notebook. I am then going to choose my environment, and I am going to choose pandas right there. So import pandas as PD, and then what we want to do is we want to be able to see what is the interpolate function and how it functions. So we can have a data frame of data. So this data is going to be, let's say, BB box, which is the bounding box, and it's going to be X, Y, and so this is going to be X position, which is X1 position, and then we are going to have the Y1 position. We are then going to have the X2 and Y2. So like this, X2 and Y2. The idea right there is that, let's say that X is moving 1, 2, 3, and then it was null. So for order for us to put null, we just have import numpy as np and np.nan like this. So we can have basically 2 nans or maybe 3 nans, and then 5, 6, 7, and then 8, 9, for example. So the correct interpolation is here is that 1, 2, 3, and then it's going to be like 5, 6, 7, and then 8. This is the correct interpolation of it, and I am going to fill in the rest as the same thing, but it can be different numbers so that it can interpolate it as is. So it can also have, for example, multiple nans following one another, or it can just be one. So we can also see both and see how it's treating this data. So we can have a df, which is a data frame, and this data frame is going to be this data, and you can see this data by just having calling the head function, which displays the first 5 rows. Now you can also specify the first 10 rows like this, and this is the data right there. Now, in order for us to interpolate this data, we can just run interpolate like this and just see the results. So you can see like 1, and then there was a nan. It is now filled with 2 because it interpolated 1 and 3 and says that the in-between number is 2. Now, we also has like 4, 5, and 6 were disappeared. Now, 4, 5, and 6 have numbers, which is 5, 6, and 7, which is actually the correct numbers if you put it like this. Now, this interpolation assumes that the ball is moving in a linear fashion, and we are going to interpolating the ball as such. Sudden movements is going to not be handled here, or if the ball switches directions in the middle of an interpolation, this can actually happen, but I would take this margin of error for more ball detection over than having it totally disappear. So yeah, this is basically what pandas data frame is. And yeah, before we continue, if you don't have pandas, just pip install pandas. Sorry, I am telling you this late, but yeah, better late than sorry. You can pip install it quite easily like this, and you can just delete your notebook that you did. Now let's create a function that interpolates using pandas. So first let's import pandas as PD. Then we can come here, and then we have a function called define interpolate ball positions. and itself, and it takes in the ball positions as well. First, what we want to do is we want to convert this ball positions into a pandas data frame. So what we want to do is we want to get it into a list. So ball positions like this, and we are going to do a one-line for loop. So for x in ball positions, and this is going to have the dictionary of it, and this dictionary is going to be get one, which is going to be one, which is the one index that we have, and then we can get the bounding box of it, and if the bounding box does not exist, we put an empty list. Then let's convert it to a data frame. So df ball positions data frame, which is going to be pd.dataframe, and it's going to take in the ball positions, and let's give it the columns as x, like this, as going to be x1, y1, x2, and then y2. This is the data frame. Next is going to be the interpolation function that I showed you before. Interpolate missing values, and in order for us to interpolate, so we can just have the ball positions of interpolate functions, and sometimes the basically the first detection is not there, so I can backfill it with the most recent detection. So I can have if the ball detections of the first frame does not appear, I can just backfill it. So this is one way to backfill. Also, you can have this backfill function like this. And yeah, basically this is it. So before returning back the results, I want to return it back to the same format that it was sent by. So ball positions is going to be equal to a one-line for loop, which is for x in this, in the df ball positions dot to numpy. This is going to make it to a numpy array. Then to list, we are going to then switch it to a list like this. And right after that, we are going to put one and then a BB box and the x of it. And this is it. This is going to return it back to the same format that it was sent in. Now, yeah, let's now test it out. So we can go here, and right after the removing of the false detections, we can then add the interpolation. So interpolate ball tracks, and you can have the ball tracks is equal to the ball tracker, interpolate ball positions, and then give it the ball tracks. Just save it, run it, and now it's done. So you can open it up again, and you can see here that the ball is now more detected, and it's always there. You can see that here, this is basically, those are interpolations where it's quite close to the ball, but it's not that specific. But it's better for us to know an estimated position of the ball instead of having it totally disappear. And yeah, this is basically it. And we can now close this out. And now we have the players and the balls detected and tracked and drawn. So the next thing here is going to be assigning each player a team based on their jersey colors. So Right here, I'm going to see the jersey color of the player and determine whether they are in team 1 or team 2. Right now, I'm not detecting any jersey colors, but we will do so in the next part. So the next step is to identify which team each player belongs to. And yeah, we are going to be having different colors for annotations, a blue one for the blue team and a white one for the white team, basically. And yeah, identifying the teams of the player is going to help us understand whether the ball has been passed from one teammate to another or it was intercepted. And we can also identify the team ball acquisition in the play. So we'll be doing that next. So our task is to take in a player crop like this one inside of the bounding box, like that, and be able to identify whether this guy is wearing a blue t-shirt or a white t-shirt, for example, in this case. So you can save this image so that I can show you a good example of this. And the idea right now is that in previous videos, I used a color segmentation technique to segment the colors. But in here, the jerseys are doesn't have any sleeves, and it's harder for us to segment. So we want to have a neural network that is able to see this image and be able to identify whether whether the guy is wearing a white jersey or a blue jersey, for example. Now, for a neural network to do this, it needs to have an input image, and then the outputs needs to be one of a predefined list of classes. So, for example, this is a pear, and it is able to identify either apple, oranges, pears, or grapes. This is how an image classification model, a normal image classification model, behaves. It does not have the ability to have infinity number of classes, and this defined list is from a training set. So basically, let's say that it was trained on 10,000 images. So 2,000 images were apples, 2,000 images were oranges, 2,000 images were pears and grapes. So we had this label data where each image has the corresponding label, and then we trained this whole data set to have this proper image classifier. But in our case, things are a little bit harder because we don't have this data set, and segmenting the colors and having a model that extracts colors out of the box is hard and is not readily available. Now we are going to use another approach for this. It also uses neural networks, but it uses a very smart way to identify whether this is a class or not. Now, one other way to have a classifier without any data is something called zero-shot classifiers. Now, zero-shot classifiers basically takes in the image itself and the class name. Here it's called like apples, pears, oranges, or the object name if you want to call it that. So basically it takes in the dog and it takes in the object name, which is the cat. Basically this is called the hypothesis and this is called the premise, but we don't have to worry about that. And the idea is that this neural network is not going to produce an infinity number of labels. It just produces 3. Whether this is entailment, whether the dog and the hypothesis is actually corresponding to each other, whether this is a contradiction, totally opposite, or neutral, which means that the hypothesis does not have much relation with the premise or the input image. So by having the class name as input with the image itself, we were able to basically say that this class name corresponds to this or not. So I can give it actually right now the guy with the blue image. So let me drag in this image right there. So I can give it I can give the zero shot classifier the guy wearing a blue t-shirt, and I say that this is a dark blue t-shirt. like this, and it will tell me whether this is true, false, or in between. Basically, if it's true, then this is wearing a blue t-shirt. If it's not, then this guy is wearing a white t-shirt. Now, this is a very smart way of having a classifier without any data. Now, if we have data, it's better for us to train a full neural network that has better accuracy. But if we don't, this is the best solution that we can do. And and for this like a simple task of having like white versus blue t-shirt, a zero-shot classifier can function good. So we are going to be sticking with that, and just know that a zero-shot classifier can help you like do a classifier, or at the very least the very first iteration of a classifier, without data and without training a new model. So for utilizing those models, I am going to be utilizing something called Huggingface. Huggingface is a library that has a lot of models and makes it really easy for us to utilize a lot of models. And it has also a model hub, so it has a lot of pre-trained models already out of the box. And it was first a natural language processing library that has a lot of processing tasks like text classification, zero-shot classification, summarization, text generation, and much more. It's a very interesting library that makes it really easy for us to use LLMs and other models as well. But it also expanded to computer vision, and one of the computer vision problems that we want to solve, or use cases, is the zero-shot image classification. This one. You can see here that there are multiple image classification, zero-shot image classification models. Some of them are from OpenAI, some of them are from Google. But one of the things that actually performed quite good for this is called the fashion clip model, which is this one. I am going to leave a link in the description below, so you don't have to memorize it. So this fashion clip basically looks at what the user is wearing, so it focuses mainly on what the user is wearing. So I got the best accuracy that I can get from this model. And you can try it out by just using this GUI on the left and the right. So you can just click here, choose the image that you have cropped and desktop, like this guy. And you can say that this is a dark blue shirt, and it is, you can specify multiple classes. So I specify dark blue shirt or white shirt. So it's an either or because the other team is wearing white. So I pressed compute, and then we can wait a little bit because it's going to load the model and then use it. So I'm going to show you the output of that, and then we can proceed. So the online GUI is taking a long time, but it shouldn't take a long time in reality. I think the GUI is here broken a little bit. So in another model, but we are not going to use this model in our code, just I want to show you the output of it. So basically a dark blue shirt, you give it the image, you give it two class names or multiple other class names if you want. But you can see that the dark blue shirt right there has a 93% possibility, while the white shirt has a 0.66 possibility. So basically right here from what you see is that the one with the higher score, which is the dark blue shirt, is the class name. So this guy is wearing a dark blue shirt. So we're going to be utilizing the same concepts here. So here in this OpenAI model, you have a code snippet that can help you out. So this is a clip model with a clip preprocessor. So basically, you load in the model with the Huggingface library. It's called transformers. So when we pip install it, we pip install transformers. I'm going to show you in a bit. And then we pre-process the image so that it can fit to the model, and it has the same pre-processing like the same pre-processing that was done in training. We do it so that it can have the same results. And afterwards, to run the model, this is how we load it, and this is how we load the preprocessor. To call the preprocessor, basically we give it the text, which is the class names that we want, and we give it the images that we loaded, and return tensors. This returns back PyTorch tensors, and PyTorch is a library that is for deep learning and machine learning models. So it is able to, it's like TensorFlow basically, which it's a library that is used to build out models. We are not going to be interacting with it a lot, as we are going to be interacting through transformers. Now, to call the model, we just have the model, and then you give it the inputs from the preprocessor, and we get the output of the model. Now, the output of the model is not going to be like 0.93 or 0.66. It's going to be a number that is that is more free-floating than that. It's not between 0 and 1. So to make it between 0 and 1, we apply a function called a softmax function. And after the softmax function, you can get that this is 0.93 and this is 0.66. So basically, we will take the one with the maximum score. So if we get 2 scores based on the 2 classes that we gave, we just take in the one with the highest score. Now, let's try and pip install transformers. And transformers is just the library name for Huggingface. So you can see the Huggingface logo right there. So just copy it, go back to your terminal, paste it in, and run it. It will install also PyTorch with it, but if it didn't, then make sure to install it as well. And to create this model and to create this module, we can just create another folder called team assigner, like this. And inside of the team assigner, we are going to have the usual, which is the init to expose functions and classes to outside of this folder. And then we are going to have a team assigner.py. And inside of this team assigner.py, we are going to have a class called team assigner. Class team assigner, like this. Now it's going to have an init function, of course, and this init function is the constructor, like the ones that we did before. What we want to do is that we want to have from, actually, like we can go back to your OpenAI one. Actually, like we are going to use this fashion clip, but this fashion clip does not have any basically code base that we can copy paste. But yeah, it's going to be very similar. So because it's like a zero-shot classifier as well. So you can just copy it and paste it in. And we are going to be using also PIL, which is an image processing library, just like OpenCV. And make sure to also install it. It's because that PyTorch models usually use this PIL format with convenience, so we're going to use it like the same thing. So for this team assigner in the init function, we are going to be taking 2 colors. So team 1 class name is going to be white shirt, and team 2 is going to be the dark blue shirt. So the same 2 classes that we written, but we are going to be writing them down here. And in here, we are going to have the self.team1 class name is equal to the team1 class name that we provided. Then we are going to have the same thing for team 2. The same thing for team 2. After that, we are going to have a function to load the model. So define load model, and it takes in the self. And right here, we have like the function that actually loads in the model and loads in the preprocessor. So let's just copy paste it. And for your sake, like where like if you're wondering where I'm copy pasting the code, it's for the clip vt large patch 14. So yeah, it's kind of the same logic. So you can put it in the self. So self.model and self.preprocessor. And instead of taking the OpenAI model, let's take the fashion clip model. So just copy it from here. This is how you can copy a model ID. So just copy it, paste it right in like this, and this is how we load a model. Up next, let's take in a frame and let's try and classify. Actually, first let's segment out the. Let's segment out the player. So we are going to be segmenting out this player like this, and have an image like this, and then provide this image to the model so that it can classify whether it's blue or white. So we can have just one frame, define get player color, and this takes in the self, this takes in one frame, and this takes in a bounding box. And this bounding box is going to help us segment out the player from a full frame. So the image is going to be the frame, and the frame is going to be, we are going to take in from bounding box 1, which is the y1. Then we are going to take in till y2. So again, if you remember that the bounding box is actually x1, y1, x2, y2. So basically what I'm saying is that this is going to be from y1 till y2, and then we are going to take in from x1 till x2, like this. So this is the cropped image of a player. And then because the PyTorch models takes in a specific format for an image, which is a PIL image, and also it's an RGB image. So basically an image consists of 3 channels, the red channel, the green channel, and the blue channel, and combining different like mixes or like of green, red, and blue, and you can formulate a lot of colors. And the way that OpenCV is representing an image, it's representing blue, then green, then red. And the way that PIL is doing it, it's representing it in red, green, then blue. So it's BGR to, and then the other one is RGB. So we want to convert the this BGR image to an RGB image. And we are going to do it with OpenCV. So just import CV2 like this. We can just convert this image. So you can have the CVT color, then image, then call it from BGR to RGB. Now the image is an RGB image, but it's still an OpenCV like format. So we want to convert it to a PIL image, because again, PyTorch is expecting this format. And from this, we want to also have the image dot from array, and we give it the RGB image. Now, this is the PIL image, and the way that we are going to do it is that if you opened up here, you're gonna see actually this OpenAI, you're gonna see that it opened the image using PIL, then it ran the preprocessor, and then it has the output of it. So we can just copy all that, put it here, and then we can just have this. So we can have like classes, and classes is going to be equal to self.team1 class name and then team2 class name. And from the preprocessor, we can give it the text, which is equal to the classes, and this is going to be the white and then the blue. We are going to also give it the image. We are going to tell it to return a PyTorch, and if necessary, we pad, because we pad the image with some zeros around it, if the model is expecting to have a certain shape. So this is just going to help us not run into errors if the shape of the image is not as expected. Now, to run the model, we can just have this run the preprocessor. Then we run the model of it like this, self.model, then give it the inputs. We have the logits. We can just remove that. And then we want to have it as a percentage. So we make it as, we create the softmax function to have the probabilities for each class. Now, again, what we have right now is that we have two scores, and we just want to get the class with the high score. So we want to return dark blue if it's going to be the one that is with the highest score. So to know the highest score, we are going to have probabilities, and we are going to have the argmax. Argmax returns the indices, like the index with the highest possibility. So basically, this is the index 0, and this is the index 1. It's going to return 0 because 0 has the higher number. So we're going to say that this is going to be a dimension of 1. And then the argmax is going to return a list of lists. So we can just have the 0 index of it. Now, when we have that, now we know that index 0 is the highest possibility, or like index 1 even. It's depending on what this function returns. We can just map it to the class name by just saying that classes of this index is going to be the return class name. So we can just have this like this, class name, which is equal to that. And yeah, this is it. This is how you can take in a frame and a bounding box and know exactly whether the t-shirt is white or blue. Now that this is the function that runs in the actual model, we can create another function that is just going to be a helper function for us that is going to return 1 or 2, which is a more convenient number for us, so that we know whether this is like team 1 or team 2 and not have the class name. We of course can do it here and save a little bit of code, but I found it to be more intuitive to put it in another function. So we can have the get player team like this, and this is going to get, and this is going to take in the self, the frame, the player bounding box, and the player ID. So right now what we do is that we get the player color like this, just by calling this function that we have, get player color. We give it the frame, and then we give it the player bounding box. Then we can say that something very easy. We can say that this is by default team ID is equal to 2, and if the player color is going to be equal to the self.team1 class name, we can have the team ID is equal to 1. And at the end of the day, we return back the team ID. Now this is it. This is just returns 2 or 1 based on the color that we have. But I want to also add an optimization technique. When we run this model for a specific player ID, I don't want to run it again. I don't want to run this neural network again, because the person is not going to change jerseys in the middle of the game. So he's not going to change the color of the jersey in the middle of the game. So the idea is now I want to check if this player is already processed. I can have a cache, and then I can return this cache, and if it's not processed, then I can process it. So I will have the cache as a dictionary. So I will have the self.player_team dictionary as an empty dictionary right now. And right after I know the team ID, I can have the self.player_team dictionary. I'm going to add the player ID and put the team ID in. Now I cached it, but the next time I'm going to call it, I want to check before running anything. So if the player ID is going to be in the player team dict, if it's going to be in it, I am going to just return the team ID that I stored in the dictionary. Now this is a good, efficient way to run it, and yeah, it won't run this model again to the players that it already ran before. Now, the last thing that I want to do is I want to get the full number of frames, the full list of frames, and the full player tracks, and then I call this function on it so that I can have the player color for each frame. So define get player teams across frames like this, and I am going to take in the video frames, all the video frames that I have. I am going to take in the player tracks. I am also going to take in the stubs. So I don't want to run this model again and again and again. I'd rather read it from stubs, whether I have it, like if I have it. So the same thing that we had in the trackers, if you remember, which is read from stub like this, and read from stub is going to be equal to have a default of false, and then the stub path is going to have a default of none. Now, just like we did with the trackers, we are going to handle stubs at the very end. So let's handle the logic first, and then we can handle the stubs at the end. So the first thing that we want to do is we want to load the model. So we just call load model, and this is now loaded. And we then want to loop over the frames or the player tracks one by one. So frame number, player track, in enumerate, and enumerate again is returning back the indices. So we can just write here player tracks. From here is what I want to do is that I want to loop over each player in this frame. So for player ID and track in player track dot items like this. And if I have this, then team is equal to self.get, again, get player team like this. And get player team is going to take in a video frame. So video frames of video frame. And then it's going to take in the track, but it takes in actually the bounding box. So make sure to put in here the BB box. And then it takes in the player ID. So this is how we, this is how I get the team 2 or team 1. And yeah, this is it. So let's have an object that puts this data and stores this data for each frame. So player assignment is going to be an empty list. And with each frame, I am going to be adding a empty dictionary. So each frame number is going to have a dictionary which is corresponding to the player ID, and the value is going to be either team 1 or team 2. And here we are going to make it player assignment of frame number of player ID is going to be equal to team. Now, this is the player assignment, and it's going to be saving the team. And at the end of the day, what we want is that we want to return back the player assignment per frame. Now we are almost there. This actually gets the player team, and if the player is already processed, we don't have to process it again. Now, just one more thing to do is that sometimes there can be misclassifications that happen, and there might be an overlap of the players very close to each other, so the model can make mistakes. So in order for us to not have this mistake go through to the whole video, I am going to make this cache empty every 50 frames. So every 50 frames, it has the opportunity to correct itself. So I'm going to have, if the frame number is going to be divisible by 50, which is equal to 0, I am going to make this self.playerdict is going to be an empty dictionary, so that it won't find it in the dictionary right there, and it will have to process it again. This is going to be also efficient. We've saved we are now, right now 50 times faster than processing each and every frame. But this just handles the possibility of a misclassification that might happen and correcting itself later on. The last thing to do is that we want to also save the stub and read the stub before finalizing this class. So we can have import sys.path.append, and then we can go back one folder. Like this. Again, we are here, so we want to go back to the utils right there. And then we can say from utils, import read stub and save stub. And in here, after we finish everything, we can have a save stub, and we give it the player assignment and the stub path. And let's put the stub path first, because this is how the function was done. So we put the stub path first, and then we put the object that we want to save. And then here, before even loading the model, if we have the stub, we don't need to load the model. So we can have player assignment is equal to read stub, and read stub is going to take in the read from stub right there, and is going to take in the stub path as well, like this. Now, if the player assignment is going to is not none, then it found something, and it actually can be the stub. But we have also one more check to do, is that we want to make sure that the length of the stub is going to be equal to the length of the video frames. And if so, I return back the player assignment. Now, this is it. So let's expose this team assigner to outside of this folder. So from team assigner, import team assigner. Then we can go back to main, and then we can import it from here. So from team assigner, import team assigner. And after we interpolate the data right there, we can then write assign player teams, and in here we have we initialize the team assigner. Then we can write we can have the team assigner get player teams across frames. We give it the video frames, we give it the player tracks, and then we can make it read from stub is equal to true, like this. And we can give it also a stub path. So let's have a stub path, and inside of the stub path, let's put in stubs like this, and make it player assignment like this, stub.pkl. And again, pkl is the extension for pickle files. And right after we do it, we just want to print it out, make sure that it's working good. And if so, we can just add it in the drawers so that we can draw the like the annotations with the correct color. So just save it and run it basically. So now it's finished, and you can see that every frame has a player ID and its team. So this is team 2, 25 is team 1, 12 is team 2, so on and so forth. So this is the player team. So everything is apparently working correctly for now. So let's now add this team assigner to the drawers, and then we can see the results in the video. So in the player tracks, we want to also add the player assignment. So let's here call it player assignment, like this. We just copy it and add it right there. You can have it in different lines like so for readability. And now we added another parameter in the draw function that we need to handle. So we can come here, we can also make it player assignment, and let's define two colors in the drawer. So in the drawer we can have a team 1 color, and this is the color that we are going to use to draw team 1. So in this color we are going to make it like a white color, and the other one is going to be like a blue color. So in here, like the white color is going to be 255, 245, and then 238. This is the team 1 color. Team 2 color is going to be 128.0.0. Again, this is BGR, which is the initial value is a B, which is blue, so it made it a blue color. So self dot team 1 color is going to be team 1 color. Then self dot team 2 color is going to be team 2 color. If something goes wrong and if we don't get any teams, we want to have a default player for the want to have a default team for the player. So self dot default player team ID is going to be equal 1. So if something goes wrong and we don't have the team ID or the player's team, we just use the default player team color. Now in here in the player tracks we are giving the color red, but we are going to be changing that right now. So we can have the player assignment for frame, and the player assignment here assignment is going to have a frame number because it's a list. So we are now going to take in the player assignment for this specific frame, and then we extract for the track ID, which is the player ID. So the team ID is going to be equal to the player assignment for a frame. We are going to get the track ID if it exists. If it doesn't exist, we just add the default player team ID. And yeah, so basically we then choose a color. So if team ID is equal to 1, then the color that we want to choose is going to be self.team1 color, else the color is going to be self.team2 color. And instead of hard coding the red color, just pass in the color that we got from here. Now this is it basically. So just save it, go back to your main, make sure that you're not printing anything like this. So to make your terminal clean, clear your terminal and run it again. And then we should see the results. It should take a little bit less time because it's going to utilize the stubs as it did. And then we can see the results. So you can see here right now is that the blue guys have blue annotations while the white team is having the white annotations. And you can see that this guy, for example, had an overlap with the one before, so this one. And it made the model a little bit confused, but if you go 50 frames, it will change itself. So you can see that it changed the color after like a couple of 50 frames or something like that. And yeah, so we are now able to identify the team that a user is in or the player is in. And we now have the player's positions and the ball positions. And now we can do a lot of good stuff without any further models. So what we can do is that we can now measure the ball acquisition, how much a team is controlling the ball. And then we can also measure if someone has the ball or not, like see if someone has the ball or like the ball is with this player or this player and see how it goes. And then we can also measure and know how if a person passed the ball to a teammate or the ball was intercepted by another team, like the opponent. And yeah, we can do a lot of good stuff from here without needing any more models, and we'll build on top of that. And the next part here is going to be able to identify which player has the ball right now. So we know the X and Y coordinates right here for the ball, and we know the X and Y coordinates for the players, but which player has the ball right now? This is going to be our next topic to discuss. Now let's discuss the logic behind of writing some code for ball acquisition and knowing which player has the ball right now. So in here you can have, I am going to be explaining it right there. So this is the bounding box for a person and this is the bounding box for the ball. So first off, sometimes the ball is very close to a person. It's inside of the bounding box of the person. So if that happens, so like we can have it like this, yeah. So if that happens like this frame right there, or maybe even a couple of frames back where the ball is, for example, here. And if we have something like that, you can see that here the bounding box is going to end, so I'm going to show it to you guys while drawing it. So this is the bounding box for the person, and it ends right here while his left hand is. So this is his left hand, and then this is the bounding box for the ball. So you can see right now that there is an overlap between the two boxes, and if this overlap is more than 80% of the ball's area, then we can consider that this player is acquiring the ball. So this is one way that we can know that this player actually acquired the ball, and it's based on the overlap between the bounding box for the ball and the bounding box for the player. Another way that we can know is that, for example, right there, the ball is not going to be inside of any bounding boxes. So you can see right there, this is the bounding box for the player, and this is the bounding box for the ball. Actually, there is no overlap at all, and yet the ball is still acquired by this player, because mainly this player is dribbling it, and we cannot consider, or we cannot factor in that this is going to be inside of the player's bounding box 100% of the time. So what we can do is that we can just measure the distance between this and the player and see which player of those other players as well like this player and this player and this player, which player is the closest, and if this distance between the player and the ball is less than a threshold, then this player is actually acquiring the ball. And if the ball is, for example, right there, like here, this is going to be very far away, that we cannot consider that this is going to be acquired the ball. So let me summarize the other way of doing it. Right now I have the bounding box for the person right there, another bounding box for a person, another bounding box for a person, and another bounding box for a person. And also those, but those are very far away from the ball, so I won't care too much about drawing them. And yeah, I will also draw a bounding box for the ball, like this. And what I'll do is that I'll see which player is closest to the ball. So it's going to be player number 28. And if this player is going to be, if this player is closest to the ball, I'm just going to see it if it's just like less than 50 pixels. If it's less than 50 pixels, then it's close enough so that I can consider it as an acquisition. If it's more than 50 pixels and it's here, for example, then this ball is outside the jurisdiction of this player. So we can consider this as the ball is not acquired by anyone at all. So this is basically the logic behind the ball acquisition. And yeah, just one more thing to add on top of this. So I'm going to show you the example that the other thing in another video. But for example, right there, you can see something that happens that is very interesting, because we detect the players and the ball in 2D. You can see that this player right here, again, before I actually do anything, let's see the video. This player has the ball went up, and then it is here. And because we are having it in 2D, here the ball is actually not close at all to the person in white t-shirt or the person in the red t-shirt and the back, because there is a depth factor to it. But this depth factor, we do not see it in detection. So let me try and explain it better. So this is the rectangle for the player, this is the rectangle for the other player, and you can see that the rectangle for the ball is right there. So there's 100% overlap for the player in white. And there is like maybe 50% overlap for the player in red. Although this is an overlap, those are very far away. And actually there is no robust way to handle this using 2D object detection. So we can try to mitigate this by saying we officially assign a ball to a player when the player acquires the ball for example 15 frames. And this will handle such scenarios where the ball is just up or down, and it's going to overlap with other players as well. But hopefully it's not going to overlap for 15 or 20 frames, so that it's going to make it more robust. So it's going to ignore the acquisition for both players like this. So unless the ball is acquired and is still acquired for 15 frames, I am not going to consider this as a ball acquisition. Now that we know the logic that is based on the overlap and it's based on the distance, we can now write this code. So we can simply write another folder which is called ball acquisition. Inside of it we will have the usual, the init.py, and we also have another file called ball acquisition detector.py. So inside of here we can create the class ball acquisition detector, like this. We will have an init function that takes in self, and we are going to define a couple of thresholds, which is going to be the self dot possessions threshold, which is the like the maximum distance allowed that we can actually consider that someone has the ball or not, and this is going to be 50 pixels. We are going to have a minimum number of frames, so a ball can needs to be 11 frames, a minimum of 11 frames to a player, so that we can call it as someone acquiring the ball. We can also have a containment threshold, and this containment is the basically the bounding box overlap. And this threshold is going to be equal to 80%. So if the ball is overlapping with the player by 80%, then we can consider this as someone acquiring the ball. Now, yeah, so one last detail to discuss here is that in here, let's open up the other video. In here, in order for us to measure distance between the ball and the player, we need to determine which 2 points to consider to actually have to compare and see the distance. So right now, what we want to do is we want to choose a couple of points. So for the person, we'll choose this point because it might be on the top, it might be dribbling on the bottom, it might be here if the player is moving this way. We can also put a point there. We can also put a point here if it's in the middle. We can also put a point here, put a point there, and there. So those are the points that we want to basically compare and measure the distance from this to the middle of the ball. Now, those are good bounding box positions, and if it's inside of the bounding box, then it's going to be handled by the containment logic, and it's not going to be handled by the distance logic. So this is good for now, but the other thing that I want to do is that I want to put in the same x, like the same y position. So I want to have the same y position if it's within the bounding box like this. I want to compare this point to this point because this is the shortest distance. So I'll put the point of the bounding box if it's in the bounding box. I'll put in the same y, but I will take in the maximum x. And if the ball is here, I will also put in the same y of the ball, but I will take the minimum x if it's in this part, if the user is running this way. Also, if the user is running this way or this way, I am going, like this part, if it's going to be this position of the ball, I am going to take in this x position and the maximum or the minimum y. And if it's in here, I am going to take in the y position or the x position of the ball, but I am going to take in the maximum y of the player. So those are all the points that I am going to use to determine whether which player is closer to the ball and the distance between the player and the ball at the end. So yeah, this is the overall logic that I'm going to do. And let's create now a function to get us those points, get us those list of points. So define get key basketball player assignment points, and this is going to take in a self, and it's going to take in a player bounding box as well, and it's going to take in one ball center. So it's going to take in the ball center of the ball position of it. So we are going to have the ball center x, and the ball center x is going to be 0, and then we are going to have the ball center y, and this ball center y is going to be equal the position of 1. Now let's also see the player positions. So in player position, we are going to have x1, y1, x2, y2. And for this, we are going to decompress the player bounding box into 4 numbers. And from here, we can measure the width, which is going to be equal to the x2 minus x1. We are going to measure the height as well, which is going to be y2 minus y1. And right now, we are going to see whether the ball is within the y coordinates of the bounding box or the x coordinates of the bounding box. So, for example, if you remember, this is you can imagine that this is a player bounding box and this is a ball's bounding box. So if the ball's bounding box is within this y, I am going to take in this position, this y position, and take in the maximum x, and take in these the same y position and take in the minimum x as well. So those are 2 things that I am going to do. It's going to help us get the closest distance. So let's have the output points as an empty list, and let's say if ball center y is greater than y1 and ball center y is less than y2, so it's going to be within limits of the bounding box of the player. And if so, I am going to append 2 things. I am going to append the minimum and the maximum x's. So output points dot append, and I am going to append x1 and ball center y, and this is going to be in a tuple, and I'm going to also add the x2, which is the maximum, and the ball center y. I am also going to do the same thing for the x's. So if ball center x is greater than x1 and it's going to be also less than x2. If so, then I'm going to take in the x with the minimum y and the maximum y as well. Now, this is going to be for the 4 points that is going to be the closest to the ball, but let's also put in the corners of the ball, the corners of the players and the different parts of the other players as well. So I can have the output points, and I can add on top of that a couple of other points as well. So we can have the x1 position, which is the minimum, minimum x, then maximum, minimum x and minimum y, and this is going to be the top left corner. This is the top right corner, which is going to be the maximum x with the minimum y, and then we are going to have the bottom left corner and then the bottom right corner, and after that we are going to get the middle points of the bounding box. So let me try and explain it a little bit more. So right here we got, let me have a different color. We got this, we got this, we got this, and we got this. What we now want to do is we want to get this, 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 and this. So this is basically going to be the maximum x, but the y is going to be the half of the y. So it's going to be, this is going to be y1, y2. This is going to be like the y1 plus the height like this over 2. This is going to be the height over 2. So let's now do that, and it's going to be the same thing, don't forget, for the x. So it's going to be the minimum y. So it's going to be the minimum y, y1, but it's going to have the x1 plus half of the width. So it's width over 2 to get this part. And this part is easy. This is just the same thing as this, but instead of x1, instead of y1, I'm going to have y2. And this is instead of the x2, I'm going to have the x1 position. I hope it's clear, but if it's not, then take basically a paper and a pen and just draw it out. I know that you can figure it out. So let's have the top center point, and in this top center point, we are going to have the x1 again plus the width over 2, and let's have over, which is integer division, because if it has any decimal points, it's going to not be a pixel position. So this is going to be the top center. This is going to be the bottom center. This is going to be the left corner, actually the left center, and this is going to be the right center. So right here, we already have the points, and then what we want to do is that we want to measure the distance between any 2 points, basically. So in order for us to measure distance, we can also add this functionality to the bounding box utils, as we might utilize it in other places as well. So you can go to utils, and then we can add a function called measure distance. And in this measure distance is going to take 0.1 and 0.2, and this is going to be an xy coordinate and then another xy coordinate. And we are going to measure the distance between any 2 points, like so. So it's going to be like the 0.1 on the x's power 2, and then it's going to be the y's power 2, then we get the square root of it. Now this is the function to get the distance between any 2 points, and this is based on the Pythagorean theorem. So if you open the Pythagorean theorem, you can see that the distance here, the distance in this, we can call it y power 2 plus b, which is the distance in x, power 2. Then we get the root value is going to be this distance, which is the straight line distance between this point and this point, basically. So I can also show you a little bit. So this is the point, the first point, and this is the second point. And basically what we do is that we measure the distance between the 2 points in x-axis, and then we measure the distance in y, and then we have a and b, and now it's just a Pythagorean theorem, which is a squared plus b squared, and then we get the root of this. It will get you this distance. So if you're just wondering what is this equation, so you just understood it, and yeah, now you know. And you can go to the init in the utils, and we can also add the measure distance function, and then we can go to the ball acquisition. We can also import sys. We can have the sys.path.append, and then we go back one folder, and from utils we can also get the measure distance. And yeah, this is how we measure distances between the current like any two points that we want. So let's now write a function to find the minimal distance. So define find minimum distance to ball. We can have the self, we can get the ball center, and we can take a player bounding box. And in here we can have the key points the key points that we are going to compare, which is the ones that we already calculated. We can have the get key basketball players. So we can get this basketball player assignment points, and we are going to give it the player bounding box, and we are going to also give it the ball center like this. And now we have the points to compare with the ball center. So to measure the distance, we just loop over them one by one. So for key point in key points, what we want to do is we want to measure distance of between the ball center and the key point, and this is going to be the distance. And then we want to also get the minimum. So you can actually calculate the minimum by this. You can have like minimum like that, and if minimum is greater than distance, then distance is going to be, actually minimum is going to be distance. Minimum is going to be distance. So minimum is going to be distance like this. Now this calculates the minimal distance and returns it back. So return back the minimum. So this is the actual logic of it. It's simple. We just measure the distance and then we get the minimal distance of it. This is not a very Pythonista way of doing things. So I'm going to show you a little bit an advanced way of a one-line for loop that does this. So you can just keep it the same if you're confused. If you're not confused and if you want to learn a little bit more, then follow along. So for basically key point like this in key points, and this is going to be like the looping in one line. And while looping, I am going to put here whatever I want with doing with key points. So what I want to do is I want to measure the distance, and what I want to do is I want to give it the ball center and the key point that I have right there. Now this will return back a list, but I don't care, to be honest, about the list, so I just care about the minimum. So you have a minimum function in Python that we can utilize, and then we just can return it. So return back this minimum. Then you can delete all this. So you can see in just one line you have the minimum calculated. Again, this is kind of hard to read, so if you want to stick with the other for loop, that's good as well. It's doing the same thing, so don't worry about anything. I just wanted to show you a different way of writing the same function. Now the last helper function that we are going to utilize is the containment. So basically we want to see the overlap between the player box and the bounding box for the ball. And doing this containment ratio, we just want to have a helper function that does that, so that we can now write the main code that utilizes those helper functions, which gets the minimum distance or gets the containment ratio and knows which player is having the ball. So in here we can have the define calculate ball containment ratio. So self and then player BB box, and then having a ball box as well, and it's going to be a bounding box. So from here I'm going to decompress the player bounding box and the ball bounding boxes. So player x1, player y1, player x2, player y2, and it's going to have the player bounding boxes, and the same for the ball bounding boxes. And this is the code that was generated from my Copilot. So it's calculating the ball area. Now the ball area is just the width times the height, which is bx2 minus bx1, which is getting the width, times the difference in y's, which is the height. This is the ball area. And it also calculates the intersection area, but it's calculating it in one line. So I want to decompress that for you guys and show you what it's doing. So right now we have a ball area right there. So we have a ball area right there. So let's get the intersection of x1, and here we are going to get the maximum of either px1 or bx1, which is either the ball or the player. We are going to also have the intersection of y1. So let's have x1, y1, and it's going to be the maximum between py1 and by1. We are going to also have the intersection of x2 and y2. And yeah, this is now going to be the minimums. I'm going to show you what I'm doing right now. And let's have this bounding box and this bounding box. So the idea is that the intersection of x1, I'm going to change the colors so that I can show you guys. The intersection of x1 is the maximum of px1 and bx1. And this is the x1 position right there, and this is the x1 position right there. So it's taking this one. It's taking this one. So again, for the y1s, it will see this position, and it will see this position, and it will take in the maximum, which is going to be still this one. Now, the same for the minimums. So we have the minimums, it's going to be for the y2 and x2, so this position and this position. So it's going to be, again, it's going to take in this x position, so this part, but instead of taking the one that was with a higher y, it will take the one with the lower y. So it will take in this position. So let me take in another color, let's say orange. So those are the points right there that were taken. So basically, this is going to take in this box right there. This is the intersection box. So now you know what these maximum and minimum are doing. You can also trace it. You can draw it on a piece of paper and know exactly how it behaves. But basically, by defining the x, y positions based on this minimum and maximum logic, you will be able to get this part that is the intersection part of the two bounding boxes. Now, this is it. And you can now calculate the intersection area. So it's just the same as the ball area. And it's going to be the width times the height. And right now, we can calculate the ratio. And the containment ratio is going to be the intersection area over the ball area. And then we return back the containment ratio. Now, this was our last helper function, and then we can use it to get the best candidate, have the logic that actually uses those functions together and gets the best candidate for each frame, and then we can use the best candidate for each frame to run on all frames. So have another function called find best candidate for position, and we are going to take in the ball center. We are going to take in the player tracks for one frame only, and then we are going to also take in the ball bounding box. So ball bounding box. Now we want to have a list of players that are basically are within the containment ratio, that have a high containment ratio, or that are very close to the ball. So we are just going to have a list, and then from this list we are going to filter out and see which one we should choose. Because in multiple, In multiple scenarios where players are fighting for the ball, multiple players might be very close to the ball or might have a high containment ratio. We are just going to choose the one with the highest containment ratio or the minimal distance to the ball. So high containment players, regular distance players. So we are going to prioritize containment over distance, and yeah, that's why they are in two different lists. For player ID and player info in player tracks for frame dot items. And what we want to do after this, we want to get the player bounding box. So the player bounding box is going to be equal to the player info dot get, and we are going to get the bounding box. Hopefully all of them have the bounding boxes, but if some doesn't, we can return an empty list. And if it's not the player bounding box, if this is an empty list, or if it's none, or if something like that, we can just continue. We can skip this player and not calculate it. So we can get the containment, which is going to be equal to the self.calculate ball containment ratio, which is this one. It takes in the player bounding box and the ball bounding box. We also want to get the distance between the player and the ball. So the minimum distance of this between the player and the ball is going to be minimum distance. Self.find distance to ball, and then we give it the ball center, and we also give it the player box. And right now we want to see if containment is better, like if it's actually containing the player is containing the ball, then we add this player to the containment. If not, we are going to use the distance. But if the distance is too far as well, we can just not add this user at all. So if right here, if containment is greater than self.containment threshold, then we have the high containment players dot append, and we want to append two things. We want to append the player ID and we want to append the containment. So right there, we just want to add the containment right there, and else we are going to have the regular distance players, and we are going to also add the player ID. We are going to be adding the minimum distance, like there. Again, so the first priority is going to be the high containment players. So I am going to see if high containment players actually is filled with anything. If so, then I'm going to get the best candidate. Again, I am measuring here the containment and the minimum distance for all other players in this frame. And then I'm going to see which is the best candidate. If there are any containments, I'm going to get the maximum containment. So I'm going to get the maximum of the high containment players, where key and key is something that we are going to use to sort the data with. So I'm going to, because it has like two attributes, which is the player ID and the containment ID, I am going to choose one, which is the containment. And yeah, I am going to get the maximum based on this containment and have this best candidate of 0. And of 0 here means that it will return the player ID and not the containment ID. And yeah, that is it. And if it's the second priority, if it's in the second, priority to regular distance, what I want to do is that if I have people in the regular distance players, like this. I want to get the best candidate as well. And the best candidate here is going to be the minimum of the regular distance players. And I am going to also be sorting it by the minimum distance. And instead of returning it, because I already have an if statement in the containment that checks whether the containment is more than the containment threshold, I want to have the same thing in the distance. I can also have it here, but I will have it here for now. And for here, I'm going to make sure that the best candidate of 1, which is the minimum distance, is going to be less than self dot possession threshold. And if so, I am going to return back the player ID, which is best candidate of 0. Now, this is it. This is how we do it. And if it doesn't go through any of those, I am going to return -1. So return -1. And this will indicate that no one has the ball right now. And this can happen because the ball might be shot, or the ball might go far away from all players. That happens in normal plays. And yeah, sometimes no one has the ball, so that's fine. Now, the last piece of the equation is to have a function that takes in all the player frames and then uses this function to get the best candidate, and make sure that this best candidate acquired the ball for a minimum of 11 frames before assigning this ball to this player. So this is the last function, so hang on tight here. And afterwards, everything should be a little bit faster for us to develop. So yeah, so let's do this. So define detect ball possession. And it takes in self player tracks. It takes in ball tracks. After that, we are going to initialize a list of all -1s so that by default no one has the ball, and only if we have a best candidate we can then reassign this frame to this player ID. So for example, we can have the number of frames like this is equal to the length of ball tracks, and then we can have a possession list of all -1s, and it's all -1s, and it's going to be like the number of frames, all of them are going to be -1s, so no one has the ball. And for actually like seeing the consecutive frames where someone has the ball, I will need to have a counter here. So consecutive possession count, I am going to make it a dictionary so that I can have a player ID as well as the number of frames that the user or the player acquired the ball in. And then I will loop over each frame, so frame number in range number of frames. I will get the ball info, make sure that the ball is actually detected, so player tracks dot of frame number dot get, and we are going to have 1, and this one is going to be the only one track ID for the ball. And if actually if there's not any balls detected, so if the ball info is not detected, I can just continue. No one has the ball because the model does not see the ball. And then I can get the bounding box of the ball. So if it exists, I can just get the bounding box of this ball, and ball info. It wrote a lot of code. I just wanted to finish the line. So get, and I want to have a bounding box, and I want to have a default of an empty list. So if it's not if there's no bounding box or if it's an empty list, I am going to also continue because I have no bounding box for the ball, and thus no one can have the ball actually. If I have the bounding box, I want to calculate the center. So ball center is going to be equal to the is going to be equal to the bounding box of the ball. Now the ball center is going to be the center of the x over and the center of the y, which is basically x2 minus x1 over 2 and y2 minus y1 over 2. And I am going to be adding this also in the utils function, in the utils file, where I can go here, define get center of BB box, and the BB box right there, I am going to have x1, y1, x2, y2, and I'm going to just get the middle of the x's and the middle of the y's and just return it. And let's also expose this here. So get BB box, actually it's not height, it is center. Get center of BB box, like this. And from here, I want to also import it, like that. And here I will utilize this function by giving it the ball bounding box. So now that we have the ball center and the ball bounding box, what we can do is that we can use the function that we already have to get the best candidate for the ball. So we can have the best player ID, which is equal to self. We can give it the ball center. So here we will need to have the ball center. Then we can have the player tracks of the frame number, and then we can have the ball box. So this is basically our getting the best player ID. So if the player ID, best player ID is not equal to -1, because it might be -1, so in that case we don't do anything. But if it is, if it's not -1, we want to increase the number of consecutive frames owned by the player. And I just noticed here this is range that is written incorrectly, so please fix it. And here number of consecutive frames, and here I am going to use this get player ID, which is the best player ID, and I am going to return 0 if it is the first time that the user is acquiring the ball, and I'm going to add 1 afterwards. So I'm just incrementing the number of frames that the user had. Now when that's done, I want to update the dictionary. So I'm going to have like a dictionary of the best player ID, and I'm going to have the number of consecutive frames. If the consecutive frames right now is more than the minimum number, so if it's more than 11, so if the consecutive frames of the, maybe you can have this, of the best player ID is more than the minimum frames, what we can do is that we can have the position list of frame number, and then all of them are right now -1s, so I'm going to override the -1 with the player ID. And if the ball player ID is -1, we want to zero out the counter for the consecutive possession count. So we can have this as an empty dictionary again. Now I have an extra T here, so I'm going to fix it real quick, like this. And I am going to have it here, here, and here. So hopefully I didn't miss one, and everything now is going to work good. So let's expose this outside of the folder. Ball acquisition detector, and I am going to expose the class. Make sure that it has the correct spelling, like that. go back here, and then we want to import it. So from ball acquisition, we import ball acquisition detector. And we can scroll down after the assignment, and then we can add ball acquisition and have a ball acquisition detector. So ball acquisition detector right there, we initialize it, then we detect the ball possession, we give it the player tracks, and then we give it also the ball tracks, and we have at the end the ball acquisition. Now, before proceeding further and utilizing it into drawers and things like that, we can print out the results, make sure that it's working good, and right afterwards we can utilize it in the drawers. So just save it and run it again. So I received an error, so I'll go trace it and let you know. So in ball acquisition detector, I forgot to put a couple of commas right there. So put commas to indicate that this is a list. So put it right there, right here. And the last one, we don't have to put it, but you can also. So just save it and run it again. So there's a lot of negative ones, but you can see after a while that this guy has the ball, and then number 2 has the ball, and yeah, this is going to be it. So we can actually like move forward and try and draw this so that we can see whether it's performing good or not. Right now, those are just numbers, and it's going to be hard for us to map each frame with each one that we have on our video. So let's draw something that indicate which user has the ball, and yeah, from there we can trace and see whether it's doing good or not. So we can go back again to our main, and in the player drawer, right under the player assignment, we can also give it the ball acquisition. So in here we have the ball acquisition, and we'll be able to now draw it. So what I have in mind right now is just we draw a red triangle on top of the user that has the ball. So let's do that. So first off, we can add this ball possession right there, and we can call it ball acquisition to make it consistent. And right here, after the assignment, we can get the player ID that has the ball, and we can have the ball acquisition of frame number. And you can see each frame just has one number, so we can just have the ID that has the ball. And if, like here, so if the track ID is equal to the player ID that has the ball, which is the current player that we are drawing their annotations, what we want to do is we want to just have a draw triangle. So we can have the frame and draw triangle. We might need to import it. So from here we can have draw triangle, copy it, paste it right in so that we can utilize it. And then we give it the frame, we give it the player bounding box, and again this triangle we already used it to annotate the box, to annotate the ball. And then we can give it the color, and then we can give it a hard-coded color of red basically. So 0, 0, and then 255. So this is it. This is who has the ball right now, and we can save it. Let's run it again and see the output. So everything worked without crashing. So let's see the output and see if it's actually good or not. So go to the output videos, and right now, so this is completely the wrong person that has the ball, and I think I think the person that has the ball was never detected as having the ball, but this is the annotations that we should see, which is the red triangle on top of the player. And yeah, I assume that this is like 2, and we have here 2s, so it's not a drawing error, it's going to be a player acquisition error. So let me go back and trace what happened, but I do think that it might be a small mistake. So let me go back and trace what happened. In ball acquisition, I forgot one line, which is if x2 is less than x1 or y2 is less than y1, this indicates that the boxes are not overlapping at all. So I need to handle this edge case and return back 0. So I can write if the intersection of x2 is less than x1 or y2 is less than y1, what I do is I return back 0. So just save it, clear the output and run it again. You can now see that the player 28 is the only player that has the ball. And yeah, you can just save it, go back here and maybe delete your printing of the ball acquisition. We don't need it anymore. And then open up the output. And you can see here that this player had the ball and acquired it. And it took it a while. It took a minimum of 11 frames to actually know that this person actually has the ball. And after it had it, then he shot the ball, and the ball is now not in his acquisition anymore. So you can see here that this ball is not in anyone's acquisition, and this is indicated by the last -1s that you see here. And yeah, from the ball acquisition, we can now understand if the ball was passed, if it was intersected, and the ball acquisition percentage for each team. So let's write the drawer that prints out the team ball control percentage of the play. So you can go here, create a new file called team ball control drawer.py, and inside of here we can have a class called team ball control drawer, and it's going to have an init, and we are going to pass the init for now. And then we are going to have the draw function. So every drawer has a draw function. So this draw function is going to get the self. It's going to have the video frames, player assignment, which is the whether the person is in team 1 or team 2, and the ball acquisition that we just made. So you can see here that the ball acquisition is just a number per frame. So what we want to do is that we want to measure what is the percentage of the ball acquisition for each team. So for example, this has, for example, team 1. So what we want to do is, for example, starting from this, we want to have 1 frame over all those number of frames, so that it indicates the percentage of the times that this team actually acquired the ball versus the other team. So the other team here will be 0 because only the player number 28 had the ball. But yeah, what I want to do is I want to have a function that just counts me every frame. What is this percentage? So at frame number 0, at frame number 1, 2, 3, 4, and etc. So what I'll have is that I will loop over them. So for player assignment frame and ball acquisition of a frame, and I'm going to loop over them simultaneously. And to loop over them simultaneously, we use the zip function so that I can get the 2 values. And what I want to have is that I want to get the team ball control, and this is going to be a value for each frame. And for here, I am going to see if the ball acquisition frame right there is going to be equal to -1. What I'm going to do is that I'm going to have the team ball control dot append -1. So no one has the ball. And if the ball acquisition frame is not in the player assignment, so maybe an error happened or something like that, that shouldn't be the case. But if it is not in the player assignment frame, then this user right there, or this player, is either not in the frame or is not assigned a team. So in this case, I will also give it a -1 and just continue and not do anything else. But if the player assignment frame of ball acquisition frame is equal to 1, what I'm going to do is that I am going to add 1, else here I am going to be adding 2, which is like team 2. And at the end of the day, I want this to be a NumPy array so that it can be easily processed. So what I'll do is that I will have the team ball control is equal to np.array and have the team ball control and import NumPy at the top. NumPy as np at the top. Now, this is it. This is how we can get the team ball control for each frame. And I am either appending 1 or appending 2 for each frame, or -1. And the idea here is that making it as a NumPy array, I can simply filter how many times was it 1 and how many times was it 2, and I can see the percentage and measure the percentage very easily. So in order for us to proceed, let's put this into a different function, and let's call this define get team ball control, and it takes in self, and it takes in player assignment and ball acquisition. And in here, I'm just going to cut it, paste it here, and return back the return team ball control. Now let's fix those indentations, and those are now done. Let's also fix the spelling, and yeah. So for actually drawing it, so we can just delete the return and have the team ball control is equal to self dot get team ball control, give it the player assignment and give it the ball acquisition, and it will return back the team ball control in a NumPy array. So the output, now let's write the output video frames. So output video frames, and for frame number and frame in enumerate, and give it the video frames. And from here, if frame number is equal to 0, just continue. And let's now have a helper function that draws in those statistics for us. So frame drawn is equal to self dot draw frame, give it the frame number, and also we give it the team ball control. Now this is the frame drawn. We are going to append it in the output video frames, and then we are going to return it. And of course the draw frame is not there yet, so we are going to develop it. So let me first show you what I want to do so that you can understand what I'm trying to draw. So this is what I'm trying to do. I'm trying to put a rectangle right there that tells team ball control and then gives us the percentage. This triangle or rectangle, sorry, is going to be white, and it's going to be a little bit translucent. And yeah, just going to have a little bit of text for team 1 and team 2 ball control. So let's open back the code again, have the draw frame function, give it the self, give it the frame number, and give it the team ball control. So first we are going to just copy the frame, and we are going to call it overlay. Then we are going to have a font scale which is equal to 0.7. This is how big the font is. Then we are going to have the font thickness, and this is how thick the font is, and it's going to be 2. You can play around with different numbers to see how this actually affects the text and how it looks. Then we are going to define the overlay position, which is this part, this white rectangle part. And in here we can have the overlay position is going to have the frame height and frame width. And in here we are going to have the overlay dot shape of 0, and we are going to have the rectangle of 1 of x1. We are going to define x1, y1, x2, and y2. So int frame width is going to be 0.6. So it's going to be like 60% of the width. For x2, we are going to put it as 75, and this is just the positions, guys, so don't get like intimidated by those numbers. You can just do it by trial and error. Just put some numbers, it will show up in the screen. Then just keep editing those numbers till you get the exact position that I have, or if you want to have it in a different position, that's totally fine too. So in the y1, sorry about that, so if it's in y1, this is going to be the height, and for the width is going to be till 99, and for y2, so this is y1, this is y2, and for y2 this is going to be 90. And this is the overlay position. This is the rectangle position. The other position that we want to have is the text position. And it's going to be text x. And the x is going to be the frame width. And it's going to start from 0.63. So this started where 0.6. But this is 0.63 because we want to have a little bit of a padding on the left, like you see here. And then we are going to have the text for y. Again, we are going to have a padding from the top. So int frame height, and then we multiply it by 0.80. Again, there's a 5 padding right there. And then we are going to have a little bit of a padding then for text 2. So text of y2. And this is the second line that we have, and it's going to be frame height, but times 88 this time. Now that we have the positions ready, we can just draw the things that we see, and we can start off with the rectangle that we have. So it's going to be cv2.rectangle like this, and in this rectangle, we give it the overlay, which is just the frame, and we give it the positions, which is rectangle 1 and rectangle x1, y1, x2, y2, and then we give it the color of white, which is 255 in all RGBs. And then we mention that it is filled by adding here -1. And you can go up and import CV2 so that we don't forget. And then for making it a little bit transparent, we add something called alpha. So alpha is just the transparency factor, and it's going to be 80%. And we have cv2.add weighted. And what we do is that we add the overlay with the alpha, which is going to be 0.8, to the frame. So we add them together and have a little bit of transparency. And we also specify 1 minus alpha to specify how transparent the frame is. And then we also give it 0 and tell it to write it in the frame. So we're going to write this overlay, which is the white box right there, basically in the frame. Now that this is done, the last two lines we are going to write it from scratch. Now first we want to calculate the team ball control in percentage, and now let's do that right there. So team ball control till frame, and NumPy makes it really easy for us to do all sorts of manipulations on the array. So the team ball control right there, we have this, so we can just say take all the elements till the frame number, and we can take frame number plus 1. So then we want to know how much of the time did team 1 had the ball. So we can have the team 1 number of frames, and what we can do is that we can have this team ball control, which is equal to 1, and this is how we filter out NumPy basically. It's very easy to do. It's just comparing the elements to 1, and if it is, it's just going to return the elements. And to know the length of a NumPy array, we just have the shape, and of 0 is going to get us the length. We are going to do the same thing for team 2. So team 2 is going to compare it to 2, and we are also going to get the shape. Now for team 1 percentage, what we are going to do is that we are going to take in this and divide it by the team ball control till frame of shape of 0. This is the number of frames basically that we have, and this is the number of frames that team 1 had the ball, and putting this over this will get us the percentage. We are going to do the same thing for 2, and then we are going to write down the statistics. So right here we are going to have team 1, let's have ball control like this, and let's delete in the second one, and I am going to multiply it by 100, and I'm going to make it only 2 decimal points. I am going to start with the text x, and then text x and text y1, which is the top part right there. And then I am going to specify a font family, which is Hershey Simplex. I am going to specify a font scale, and I am going to specify a color of black, which is all zeros. And then I am going to specify the font thickness. Right after this, I am going to have the same thing for team 2. So team 2 is having the same things and is going to write in position 2 right there. And yeah, this is basically it. And at the end of the day, I want to return back the frame. Now this is it, and you can see that I am returning here the frames drawn. I actually want to return the full list, and yeah, that is it. We can go back here and we can expose back the function. So let's have this team ball control like this, import, and then copy paste the class name like that, copy paste it and go back to the main and have the team ball control drawer imported. We can also initialize it right there. So it's team ball control. And we can also have here draw team ball control. And we are going to have the output frames, team ball control to draw output frames, then give it the player assignment and ball acquisition. You can have it in different lines like this. And yeah, hopefully when we run it, everything will work good. And you can now save it. Make sure to save all your files and just run it again. So there was an error here where shape of 0 is actually only returning the height. We want to return both the height and the width, so we removed the of 0 part. So go back again here, and in here just remove the of 0. Save it, clear the results, run it again. Sorry about that, the same issue happened because shape has actually three dimensions, which is it's because of it has RGB. So we just take in the first 2 dimensions, which is the height and the width. So this is how you take the first 2 parameters. So just save it, clear the results, and run it again. Now it's finished. So we can go back again here and see if the team ball control is doing good. So we can see that the rectangle is there, but the text is not. So let's see why. So the problem is that we are writing on the overlay and we are now utilizing the frame. The overlay was just to make the transparent rectangle. So just put the frame instead of the overlay and everything should be good. So just save it, run it again. It's done now. We can also see the results. So you can see right now that the team ball control is incrementing for team 2, which is the blue team, as soon as the ball acquisition detected that the player 28 has the ball. And you can see that team 1 did not acquire the ball at all. And yeah, this is it. The only thing that is left is that I did not add a percentage sign in the text. So you can just add this percentage sign right there. If you want to see it, just run it again and see the output. So you can go back here, see the output. This is the percentage sign. So everything now is working perfectly. So up next, we'll be detecting passes and interceptions. It's going to be easy because we already have the ball acquisition data. I am going to go through the logic first and then we can code it together. So we can open this and then we can just explain what we are going to do. So basically, this is going to be the person that has the ball right now. And you can imagine that this is the like the red triangle that we already have, which is going to be this one. Give me a minute. It's going to show up. Yeah, that one. And basically what we are going to do, this is the ball acquisition. It's in player number 28, which is this player. The idea is that if this ID switches from one player to another, then we can determine that it has been passed or intercepted. The way that we see that it's passed or intercepted is through the color of the jersey, like the player assignment that we have. This is blue and this is blue. So if it switched from 28 to another teammate with the same color, then same jersey color, then this is going to be a pass. If it went from 28 to 4, which is another team color, then this is going to be an interception. So this is basically it. We're just going to see the ball acquisition data and check when it switches from one player to another. And if it switches, we just check that if it's the same team, if it's the same like team jersey or not. If it is, then it's a pass. If it's not, then it's an interception. This is basically the logic behind that, and we can start coding that. So in here, create a new folder, call it pass and interceptions, pass and interception detector dot. Actually, this is a folder, so you can leave it like this. We will have the usual init file. We will also have the pass and interception detector dot py, and inside of here we are going to have a class called pass and interception detector, and of course we are going to have an init, and we are going to have a two helper functions, one for detecting passes and one for detecting interceptions. And we are going to have two functions, one that detects passes and one that detects interceptions. And let's do them right now. So let's start off with the passes. So define detect passes, and we only need the ball acquisition data and the player assignment so that we can have like where is the ball, which player has the ball right now, and then what team do they belong to. So we can have the ball acquisition player assignment like this. So we took both the ball acquisition and the player assignment, and we can start off by having a passes list, and it's going to be -1 for all the frames, so the length of ball acquisition. So for each frame, we are going to detect whether this is a pass or this is an interception. And right now we are only detecting passes, so it's going to be -1 if it's not passed. But once it's passed, we are going to detect that this is the start frame of a pass or an end frame of a pass. So in order for us to have that, we can just have a previous holder, and this previous holder is going to be equal to -1 at the beginning, and a previous frame, and this is going to be like the last frame that a player had the ball. And then we are going to loop, so for frame in range length ball acquisition, we are just looping over the frames. So basically we can have a current holder, which is equal to the ball acquisition of frame. This is the current holder of the ball. And then we also have a we want to compare it with the previous holder. So the previous holder here is that if the ball acquisition of frame -1 is not equal to -1, so did anyone has the ball before that? If so, we are going to have the previous holder update its previous holder ball acquisition, and we are going to also put the frame. So basically this overrides the -1 only if the ball acquisition is actually acquired by either team 1 or team 2. And yeah, we now have the previous holder and the current holder, and then we can compare them together. And since we are detecting the the previous frame, we can just have here start from 1. And if we started from 0, just the 0 will break. So we can start from 1 and then we can move on from there. And we can say just if the previous holder is not equal -1 and current holder is not equal -1 and the previous holder is not equal to the current holder, because it might be that like the previous holder is the current holder because the player did not let go of the ball yet. And if they did not let go of the ball, then this is basically someone running with the ball. So we don't detect it as either a pass or an interception. So if this happens, if it actually, like, the ball was acquired before and the ball is acquired now, and the previous is not equal to the current holder, that means that it either was intercepted or it was passed. And the way that we are going to do that is we are going to use the team colors. So we can have the previous team, which is equal to the player assignment, which is the one that we already got from the inputs, and got here the previous frame, which is the one that we stored right here, and we can get which is the previous holder. And if it's actually, like, if it's not there, and it might not, but those are edge cases that it doesn't show up, it can be -1. It will be -1 if this player does not have a team yet. That shouldn't happen, but it's just good practice to handle those stuff. And the current holder, whoops. So the current holder is going to be equal to the same thing, player assignment, but instead of previous frame, this is going to be frame, and instead of previous holder, is going to be current holder, and this is going to be the current team, like that. And then if previous team is equal to the current team, and we can check that it's not both -1. So if previous team is not equal to -1, and if that happens, you can also add the current team is not equal to -1, but basically I'm checking that they are both equal, and previous team is not -1, so it automatically handles that current team is not also equal to -1. And I think I mispronounced, like I misspelled current team, so just copy the correct spelling, paste it in, and now we are done. And then the passes of frame is going to be equal to the previous team. Now, this is it. This is all what's to it. This is how we detect frames. We just loop over each frame, detect, like, know which one is holding the ball, and then we detect the colors of the team or the player assignment of the team together. Now, this is going to be exactly the same logic for the interceptions, but instead of checking if the previous team is equal to the current team, we're just checking that they are different. So you can just copy paste it and have this as interceptions. And in this passes, have it as interceptions as well, like that. Copy paste it and put it here and put it here. Now all this is good, but in this if statement we are going to edit it a little bit. So if the previous team is not going to be equal to, so they are different than the current team, and the previous team is not equal to -1, and the current team also is not equal to -1. And if that happens, we are going to give the interception to the current team because they are the one that stole the ball, basically. So here we didn't care about putting the previous team or the current team because both of them are equal. Both of them are the same team. Here we just care because it's going to detect who stole the ball from who. So here the current team stole it from the previous team. So we just save it. Then we go to init, and then we expose it, passes and interceptions, import passes and interceptions detections. Make sure to spell everything correctly so that we don't run into issues. From here, you can go up. We can also import it from passes and interceptions detector, import passes and interceptions detector. And then we can simply add this logic after the ball acquisition part. And right here we can have the detect passes and interceptions. And here we can initialize the passes and interceptions class. Then we detect passes, and then we detect interceptions. Now, this is all good. We just don't print out this anywhere here. So we can just print it out, and then we can draw it after we make sure that it's working good. So we can have the print passes, print interceptions, and then let's put a line between them. And let's run it and see the results. Basically, the video that we are running doesn't have any passes or interceptions. I think there is some misspellings here, so let me go and try to fix it. So there's an S here that you need to put to interceptions. So just save it, go back again to your main and run it. Now it's working good, so everything here is -1. The video that we have right now doesn't actually have any passes or interceptions, but the other two videos has. So let's try it out from the other two videos. So to run another video, you can go up, and here we have video 2 and video 3. You can find them in the input videos. We have video 2 and video 3. So just run 2, and note that it's not gonna find the stubs for video 2, so it's going to run it. And yeah, it's going to take a little bit of time, but afterwards it should be working. So we just make sure that the interceptions and the passes are working good, and then we can proceed to drawing them. So now it's finished, and the passes and interceptions are now detected. And the video 2 only has passes, so you can see here that it's mostly -1 because a lot of them is not going to be a pass frame. But you can see that sometimes it will have a pass right there, and yeah, and you can detect I think 3 to 4 passes in this object. So you can just delete it, and then we will draw the output. But you can also check the output video. Here it is. So this person, the white team, has the ball. It was passed to another teammate, and when it was passed, it was automatically detected as a switch right there. Then there's another one, and here it will be detected as someone acquiring the ball. And this is the third pass, and here's the fourth pass. And you can see that also as a bonus, like the team ball control looks good, and the other team did not acquire the ball at all. So everything here is looking good. So let's just draw, like have the same rectangle right there for the team ball control, and have it the same for the passes and interceptions. So I can show you how it would look like after we finish. And here it is. Video 2. So basically this is what we are going to have, which is team 1 passes equals 0, interceptions equals 0, and then when a pass happens, I automatically increment the passes right there, and it also goes pass 2, pass 3, and then the interception counts also increment. So this is what we are going to do, and note that we are just have 1 or 2 or like the frame. So just know that we already have the output per frame, and to know how much passes, we can just sum up the number of occurrences of ones and sum up the number of occurrences of 2. And yeah, this is it. So let's add a drawer to that. So in the drawers, create a new file called pass and interceptions drawer. So pass and interceptions drawer.py. Inside of here, just create a class called pass interception drawer, and inside of here just create a new init. Of course, the same thing. Then we will create the same draw functions that we have for other drawers. So draw, and it takes in the video frames, it takes in the passes, and it takes in the interceptions as well. We also have the normal output videos, output video frames, and we are going to loop over frame number, frame in enumerate video frames. Then we can have a function that draws the frame. So just like what we have with ball acquisition, we are going to have also a helper function that draws one frame. So self dot draw frame, and give it the frame, give it the frame number, and then give it the interceptions and passes. So passes and interceptions. And then we append it to the output video frames list, and then we return it back. So let's now create the draw frame function, and for that we are going to be using the same function that we had with the ball acquisition. So you can open up the ball acquisition or the ball control, copy paste the draw function right here, and it will have the same, like a lot of the same logic. So I just copy paste it so that we can save up some time. Import CV2, and is there anything else to import? I don't think so. So the first thing that we have is that we copy, then we have a font scale, font thickness, and then we have an overlay, and this is the positions of the overlay for the ball control, but we wanted to shift it a little bit to the left so that we can have two rectangles next to each other. And the way that we are going to do that is that we're going to shift the x axis a little bit and leave the y axis the same. So for the x-axis, just shift it to 16, and then x2 shift it to 55, and for the x here, put it as 19. And this should automatically create another rectangle that has the same color, and it has the same transparency level. And yeah, after that we have the put text, and I think this one will need a little bit of some new code. We would need to first pre-process this data to make sure that we are counting the number of passes and the number of interceptions, and then we can just print it out as text. So let's delete that, and then we can have the passes till frame, passes and frame number +1, and make sure to take in the passes and interceptions in the parameters instead of the ball control. And now we have the passes till frame. We want to also have the interceptions till frame. And instead of using NumPy this time, I am going to show you how you can just loop over this list and count them individually, so that you have two different ways of counting things. So the NumPy one is like saves a little bit of code, and it saves and it's like for the people that are more familiar with NumPy, it's going to be very straightforward. But for the people that are not familiar with NumPy, it might be a little bit confusing. So I'm going to show you a different way to do it, but you can do it in those two ways. So you can have a function called get stats, and this will take in the passes till frame and interceptions till frame. So I will have it as passes and interceptions, and I will have a list for team 1 passes, and it's going to be a list, Then I will have a team 2 passes, then team 1 interceptions, and team 2 interceptions. And then what I will do is that I will count each and every one. So I will loop over the frames one by one, and then if the passes is going to be equal 1, I will add it to the team1 passes.append this frame number basically. I am going to add the same thing for the passes for team 2. Then I will have the same two things for interceptions. And at the end of the day, I want to return the number of passes and number of interceptions. And that would be the length of those lists. And it's not going to be the list themselves. So this is it basically. So you can just we can just utilize this to get the number of passes and number of interceptions for each team. So we can have team 1 passes, then team 2 passes. Then we want to have also team 1 interceptions, team 2 interceptions, and then we get the stats, and then we return it back. And once those are returned, I want to have another put text. So team 1 passes is going to be, so it's team 1, then I have a dash like this, passes, and then interceptions, I have the interceptions like this. And I will put the team 1 passes and team interceptions, and then I will give it the text X and text Y, which is the positions, give it a font family, then give it a font scale, then give it a color, and then give it a thickness. This is basically it. We can make it a little bit more viewable by putting it in different lines like that. And yeah, this should be it for us. So we now finished, I think, the drawer, so we can just test it out and see if it works. Let me just fix those indentations out. And yeah, everything now is looking good. So we can just import it in main, and then we can use it to draw it. So from here, we import, we need to expose it first from the inits. So in here, go to your init from dot passes and interceptions, import passes and interceptions, then go back here, add this passes and interceptions drawer, and in here we initialize it. So let's initialize the passes and interceptions drawer, and then let's draw the passes and interceptions. So in here we can have a draw passes and interceptions. It takes the output video frames, passes and the interceptions, and it returns back the output video frames. Everything now is looking good. Save it. I removed the prints for the passes and interceptions that made those lines here. So I can clear it and can run it again. So it's now finished, so we can go and see the results. Go to your output videos, open it up, and then we can see that here is the first pass. It was detected, it's incremented quite good. Then here's the second one, pass 2, then pass 3 right there, then pass 4, and yeah, everything now is working good. The ball control is also working good. Team 2 didn't also touch the ball, so everything is awesome. And for just testing purposes, we can also run it for video 3 and to see the results. It will take a little bit of time because it doesn't have the stubs, but yeah, just wait for it, and it's good for us to test it and make sure that everything is good before moving forward. So let's check the output. So if you opened it, so this user has the ball, and I automatically see there is something wrong, which is all the users right now are marked as white. All the players are marked as white except this guy right there. Maybe it's because of the background with the blue people. And I think it's because we did not change the color of the users. So we used to have white and blue, now it's white and red. So just go ahead to your team assigner. Where is it? Where's the team assigner? Yeah, the team assigner right there. Open it up and make it as a dark red t-shirt. And just save it, and we can run it again. But before running it again, it will find the stub and then like use it instead of running it again. So make sure to remove the player assignment stub. So delete permanently, and yeah, run it again. So it now finished, so let's check the results. You can go here and you can see that the players have different rings, color rings like below them. Now the colors are hard-coded, so it will not reflect the jersey color, but it shows you that those are different teams, which is quite good. We have the white and we have the blue colors, and yeah, they seem to be working good. So let's open this up, and you can see that this red teammate had the ball. It was then thrown up, and right there it marked as an interception. I think this is a bug because I don't see the red marker that shows me where exactly who exactly has the ball. But we can move forward and see like this person has the ball right now. And yeah, and when it marked as this person has the ball, it marked it as a pass. So this is a bug, I think. And then this is a pass. It was marked as a pass. That's good. And this is another pass, which is 3 passes. So everything now is looking good, except for the first interception. So I'll be digging deep into this and see if I can solve the issue. So you can see the problem right there is that this player right there, player 14, was marked as having a ball for 1 second, and I think it's because the ball was overlapping with this guy's bounding box. So I'll be seeing how we can deal with that. Maybe I'll stretch out the detection like the detection threshold a little bit and see how we can deal with it. Okay, so I did 3 edits to fix this. So in height, I made a small mistake. Instead of writing Y1, I wrote 21. So make sure to fix that. And this is going to be equal to the height. So just save it. And the minimum frames, I changed it from 11 to 13. And just one more edit in the drawers. So you can go to the team ball control. And I was skipping the frame number is equal to 0. I think it's because I thought that it would break something in here, but it shouldn't. So you just remove it as well, like this, and run again. So everything now finished. You can see the output. So again, this user has the ball, which is a red team. And then right now, till now, the interception was not detected. And right here, it was detected, and it was marked down there. And then this is a pass, so you can see that pass 1 is detected. Then this is another pass, and then right at the end, it was detected as a pass. It's because we have the 13 frame delay, so that's why it's taking a little bit of time to be confident of whether this is a pass or not. And yeah, you can see also the ball control is looking good. So you can close that, and now we are done with doing the passes and the interceptions. The next step is to identify where the user is in accordance to the court. So basically we have the X and Y positions according to the frame, but we don't have their relative position to the court. And this is going to help us to understand how much they covered in meters and how fast are they moving, and basically having like the location based on the court. And for that, we need to detect things that will tell us this is the edges of the court. For example, this user is this close to this edge or the other edges that are not on the screen, basically those edges. So we want something to tell us or to detect that those users are closer to which edges and by how far are they. And for that, we are going to know something called keypoint detection. And keypoint detection is basically is a neural network, and instead of, for example, a classification neural network where it outputs the class, it here outputs some numbers relative to the frame. So it will output the edges of this tennis court, for example, 1, 2, 3, 4. You can see that if you have the position of this player, you can almost see that it's on top of this key point. And we know that this key point is this exact place, so we can then try and understand where the user is and is moving in the court itself. And we can do the same thing with the basketball courts, and we will have other key points like this, and this, and I can show you the final output of that. So we can go here, and you can see that I am detecting here the key points 15, 14, 13. Those are key points that I am detecting, and from here I can understand where they are. So you can look at the tactical view, and I can know that they are in this specific place of the court and moving, and if someone moved from here to here, I know exactly what distance they moved in, and since I have the frame numbers, I know how much time it took them to cover this basically distance. So I can measure speed as well. So this is basically it. This is our next project, and our next task is basically we are going to utilize a model called a pose model, and we are going to use a pose model just as our base computer vision model that we will fine tune. Instead of putting those points, which is the joints of the joints of a person, we will ask it to get those points, which is the points that are on the court. So basically, you can see that this data frame right there, I will leave a link in the description below. This is a RoboFlow dataset, and you can see that there are like 56 images. It's not a lot, but it's going to help us to also develop this. It's not going to be that robust, but again, it's what we have, and it will be good enough for our use case. So we have this point, this point, this point, this point, and this point. We also have those points. And if you go on deeper, we have the midpoints. And again, we have like the exact same points on the other side as well. So this is basically the data set that we are going to use. And we are going to use a base model of a pose model. And this is because the pose models are very accessible for us, and they are abundant on the internet, and they are also on Ultralytics. So we can conveniently use this key point detection to make the model understand how to extract basketball key points for us. Now, the same thing that we did with the object detection, we will do here with the key point detection as well. So you can go back again to your Colab and maybe copy paste the training of the ball or training of the player. Now, this is the player detection notebook that we had. It had the get dataset, it had the shuttle move, it has the training command. So we can just make a copy of it. So you can have save, copy, and drive. we can call it basketball court detection, court key point detection training. Now we can also download it when we finish, but in here we are going to get a different data set, which is this one. So go to data set, go here, press on download data set again, and show the code to download the data set. This is it. So copy it, go back again to your Colab, and paste it in. Now I am going to be using here YOLO V8, so no need to do this shuttle, and you can delete it. And in here we are not going to be detecting anymore. We are going to use the pose. We are going to train, and then we can remove that. Have the batch size is equal to 16. Epochs is equal to 500. And the image size is equal to 640. And everything here now looks good. I think this is model. And in the model, we want to have YOLO V8 and specify that this is a pose model. So it's YOLO V8X pose.pt. And if you go to Ultralytics, you'll have like a list of models that you can use, so you can copy paste whatever you want. But this is the one that I utilized. And yeah, basically this is YOLO. Let's again make sure that everything is good. So it's YOLO task of pose. The mode is equal to training. The YOLO, the model right there, it's called model YOLO V8X, pose-pt, then the dataset is the dataset location, and the batch size is going to be 16, which is correct, and then epochs is 500, and the image size is equal to 640. Everything looks good, so we can now make sure that the runtime is T4 GPU. Open this up and basically run all of them. And you can just run it by pressing Shift and Enter, or you can press the run command right there, or the run button. So we'll wait a little bit for it to finish, and then when we do, we'll have also the weights right there, and we can download it and then use it from here. So you can leave it when it's totally done, but after it finishes, and make sure that it finishes, mine is still training, but after it finishes, you can go to runs, pose, train, and then weights, and then you can download the best.pt. So just press download. I downloaded the wrong one, so just make sure to download the best. And yeah, after it downloads, we can go on and proceed. So go to your downloads, locate the best, and then just cut it and go back again to your basketball analysis repo and go to models and paste it in. And let's rename it to court keypoint detector.pt. Now we have the third model and we can use it to predict on the frames. And before we do that, we can just also download this. So if you want to download it, you can download it as a .ipynb. Go back here and there are training notebooks. So go back to your downloads, cut it, and paste it right in. Now you have all the 3 training notebooks readily available, and you can import them in Colab whenever you want. And if you have a GPU, then you don't need to import them in Colab at all. So let's now create another folder called court keypoint detector. So come here, create a new folder called court keypoint detector, and also have an init.py. Also, we are going to have a court keypoint detector.py, And you can now close all of those files, make sure that we stay like minimal so that we don't do a lot of scrolling. And yeah, now we have the main and the court key point detector. From here, we can create a class called court key point detector, like this. And we are going to have an init, and we are also going to import YOLO. So from Ultralytics import YOLO, and then we can load the model. So self model is equal to YOLO, and then we can have a model path. So in here, model path, like this, just copy paste it right there. And in here, we can have a define get court key points, and we can put self frames read from stub. We are going to have the same stub logic. Stub path is equal to none, and read from stub has a default of false. And of course, because we are going to read from stub and save stub, we are going to need to import those. So import sys. Then I'm going faster here because we already did this like multiple times. So I will be sure to explain the key points part. And we can also import the read video and save video. And in here, we will have the read stub and save stub logic, but like every time, we are going to make the logic first and then encapsulate it with a save stub and a read stub logic. So we are going to specify a batch size of 20. We are going to have court key points as a list, and then for I in range 0 till length of frames, and then we will jump with the batch size. And yeah, basically we are looping here, but instead of 1 by 1, it's 20 by 20. Then I am going to get the detections batch, just the list of frames that I want to detect on. So I'm going to have the self.model.predict. Again, it's very similar to the detection logic, and I'll give it from frames of I to frames of I plus batch size. And this is not going to break if it exceeds the length. And the confidence is going to be 0.5. And at the end of the day, I want to append this to the court key points. So I'm going to loop over them. So for detection, and this is going to be the detection for one frame in detection batch, like this. And in here, for each one of them, I am going to append it. So come here, so court key points dot append, and append the detection. And at the end of the day, we return it. So this is how we use the basically the pose model. Again, it's very similar to our detections model. So yeah, it's going to have the dot predict, and at the end of the day, the output is not going to be bounding boxes. It's just going to be a list of key points, basically. And let's now add the stubs logic. So if read, if actually you can have the court key points is equal to read stub, and read stub is going to be, it's going to get the read from stub and stub path. So read from stub like this, and stub path, and this is going to be read stub and save stub. Then if the court key points is not none, and if the length of the court key points is equal to the length of the frames. Then I return back the court key points, else I just process this. And in here, I'm going to save the stub. So I'll give it the stub path first, and then the court key points. So make sure to add this correctly. And yeah, this is it. And from here, it's, I think I misspelled the detector wrong. So it's detector. And just copy this. And from here, from dot court key point detector, import court key point detector. And we can come here in the frames where in the main file, sorry, and we can also import it. We can then initialize the court key point detector here if we want. So it's initialize court key point detector, and inside of here court key point detector, and we are going to give it the path of it. So it's models.courtKeyPointDetector.pt, and let's just copy paste the name so that we make sure that we got it correctly. So there we go. So after that, we will just want to utilize this court key point detector. So right after we detected the tracks, we can detect the court key points. So get court key points, and what we are going to do, have the court key points detector, and then we can call get court key points, then give it the video frames, then give it the read from stub, and give it the stub path, which is going to be stubs.court key point stubs, and I am going to call it court underscore points like this, and this is it. And for now, I can just print it, and if everything is good, I can then proceed to the drawer. So just run it. So now it's finished, and you can see the output here is per frame, and you can see that the key points now is not none. If you remember at the beginning of the video, we had the detections where the key points is like the masks was like none, but right now it has an object, and those object is going to have a list of key points, which is basically XY positions. So it's going to have multiple XY positions for different key points. So what's next that we are going to do is that we are going to draw them to see the output of this model. So you can go back to drawers right there. You can create a new file. Let's call it court key points drawer.py. And in here, we can have a class court key point, let's have it like key points drawer. And inside of here, we are going to also use supervision to help us like plot out those key points. So import supervision as SV. And then we are going to also have a define init, the normal stuff. And we are going to also have a draw. So for the init, I want to define the color that we are going to use. So key point color. And if you know that we can like define a color with RGB, but we can also define it like so with the hex representation of it. So it's FF 2C, and this is going to be just a color, like a red color. And we are going to, of course, have the draw function, and the draw function is going to take in the frames and the key points. So it takes in the frames and the court key points. We can now delete this and also delete this. What we want to do is we want to like label some like the vertices. It's called like the key points is called vertices in supervision. So we can have the vertex annotator, which is equal to sv dot vertex. So vertex annotator, and we can give it the a color. So let's have a color first, and the color here is going to be equal to sv dot color like this from hex, and give it the self dot key point color. And then we just want to define the radius of it. So let's have a radius of 8. Like that. Now we also want to have like the key point number. So each key point has a number, and if you saw the final output that I have, I can show you right now that this key point is 15, this key point is 14, 13, 16, 17, so on and so forth. And in the other court, it's 0, 1, 2, 3, 4. So each key point has a specific number that tells us where exactly this key point is in the court. So in here, we just want to also output the number and not just output a dot. And in here, we can have a vertex label annotator, and this vertex label annotator is going to have the vertex like this, and it has the label annotator, and I am going to give it the a color, the same color from the hex, and this is it. I am also going to give it a text color. And the text color here is going to be white. So sv dot color dot white. I am going to give a text scale of 0.5. This is how big the text is. I'm then going to give a thickness of 1, and I can then delete this for now. And what I want to do is that I want to loop over each frame. So like what we had in other drawers, I'm going to have output frames, which is equal to an empty list. I'm going to loop over each frame. So in enumerate and give it the frames, and annotate frame is equal to frame.copy. Then I can have the key points, and the key points is going to be equal to the court key points, and I will give it the index. So this is the court key points of that. And then I'm going to have the vertex annotator to annotate me the frame. So I'll give it the annotated frame, which is the copy of the frame, and then I'll give it the key points, and then I will have the label annotator do its thing. So vertex label annotator dot annotate, give it the annotated frame also, then give it the key points, and at the end of the day, I want to append those to the output frames, and I will return at the end the output frames. So this is it. This is our key point detector, and then we can start to expose this and use it. So of course, in the drawers, open up here, and from key point detector drawer, I think there's an extra P right there, so make sure to have the correct spelling. So like this, and copy it, paste it right here. Make sure to get rid of the PY. And yeah, I think if we did everything correctly, we can now run it. So from drawers, so we have the drawers up here, so we can just paste this in. And in the drawers, we can initialize it. And then we can draw the key points. So right there, we can have a draw key points. draw code key points. We have the output video frames. We give the output video frames, and we give the code key points. So everything here looks good. We can clear this. If we have any prints, remove it like that, and then we can have another run. So there is an error here, so go back to the drawer. I think the Copilot that I'm using added this by mistake, so just remove it, and then we can run it again. So in here, we have to have, instead of frame, it's called the scene. And the key points here needs to be a NumPy array. So let's have this as well. So right there, we can have key points NumPy, which is equal to this key points right there, and .cpu .numpy, and we can also pass it here. Now that this is done, I think it should work. So let's run it again and see how it goes. I think this one is also scene, not frame. So just fix this as scene and run it again. The last thing is that I think this is called key_points. So make sure to spell it correctly, like I did right now. And then we can save it and run it again. The last thing, I think I saved the stubs wrong, so go back here, and inside of here, the detection needs to be detections.keypoints. So let's only save the key points for now. Let's clear it. Make sure to go to the stubs and remove the code key point stubs like this, delete it, and run it again. So now it's done. Let's go back again to our output and see the results. So you can see here that it's 15, 14, 13. The detections is working good. And yeah, everything now is working good. Everything is working as expected. I think this 12 is wrong, but we'll handle it later. You can see that this is 7. Again, 8, 0, 1, 2, everything looks good. So the detections right now looks good. So we can proceed from here. So the next part of that is that the camera angle and the camera tilt are not giving us the best one-to-one correlation with the exact view of the court. So let me show you like what I mean. So right now, if you looked at this and you opened up your measuring tape or anything like that, you can see that from here, from the initial, like the far end of the court till half of the court, this is approximately half of the court. And right here, the Y is going to be around 300 pixels. So this is half of the court and it's going to be like 300 pixels. And if you actually measure the other half of the court, it's going to be around 450 pixels. So that means that it's not a one-to-one correlation. Basically, the people that are moving pixels, like if one pixel was moved right here, if a player moved one pixel here, then it will correspond to almost 1.5 pixels here. So this user needs to move 1.5 pixels to actually move the same distance that this guy did. And right here, it's also like it has different camera angles. So basically, I think this camera angle is maybe the worst. So let's also measure it here. So right now, this has also 300, but even here, if we measured starting from the court, starting from half of the court till we finish, this is almost 600 because even the last part of the court is not in the frame. So this is 600 pixels, which is almost twice. So the person that moved here 2 pixels is equivalent to the person that moved in this half 2 pixels is equivalent to the person who moved here 1 pixel. Now you can go this a little bit further, and you can also like divide it into quarters, divide it into 1/8, and try and estimate this. But again, as you saw, the camera angle is always moving, and it would be good for us to have an algorithm that can map this and understand the camera angles to the actual court positions. So what we will do next is what we call like perspective transformation or homography. You can call it whatever you want. And right there, the idea is that like this part of the court right here, which is almost half of the like the court in pixels. This is, let's say that this is the full court, this is the full half court right there. And having this small part of the court, which should be, if we are having like the one-to-one correlations, it should be like this. So this part right there, if we have like one-to-one correlations, it should only have the quarter of the court, but we want to have an algorithm that says, okay, this is actually based on a reality, like real meters, it is going to be half of the court. And here, the other half of the court, which I will do in orange, for example, it should be like almost twice as big, but I will also give it the same size. So this is what perspective transformation is. It is trying to actually get the actual court size in meters and not relative to the pixels. Now, we can do this based on a perspective transformation algorithm, and all it needs is that it needs those points in, it needs those points here from the model, so those court key points, and it actually also needs that the actual distance. So it needs the actual distance. So the actual distance is 0.9 meters, for example, and it needs the actual distance here, it needs the actual distance here and there as well. So it needs the actual meter distance and regulate those pixel positions to actual court positions. So this is what we are going to do next. Again, we are going to be using OpenCV for this function, so we don't need to actually implement this mapping by hand, but we will be utilizing the functions that we already have from OpenCV. So we can close this out, and from here we can do another module called tactical view converter, and we'll have this tactical view converter right now. So let's close out those folders. Again, we create a new folder called tactical view converter. And this tactical view converter will have, of course, the init. And we also want to have a tactical view converter file. .py. And inside of here, we can have a class of tactical view converter. It has the init, and we can just remove this, make it as pass for now, and then we'll be able to fill it from here. So the first thing that we want to do is that we have a couple of images in the ball detection, the ball analysis GitHub repository. So if you opened up the images, you're gonna find like 3 images. So download them. One of them will have the basketball court. This is what we are going to be drawing on the top left part. So download it. And then there is a basketball reference sheet that tells this like the distances. So this is 0.9 meters. this is 5.7 meters. It's also good to have a reference for that. And the reference for the images you'll find in this text file. You'll find some links. And yeah, in here you can make a new folder called images. And go to your downloads and cut those out. Come here and paste them. And let's open up the one that is in meters. Now, we want to have a full list of key points with their actual meter positions. First, let's have the image, this image imported, and we can actually overlay it on top of the frame. And based on that, we can also specify the different actual meter positions of it. So we can have a self.court image path, and this is going to be the court image path. Let's also have it from here. Then we are going to specify a width in pixels, which is 300 pixels. We are going to specify the height also, so that we can have the height of it as 161 pixels. And what we have is that we know that the actual distance, like the actual width in meters is 28, while the actual height is 15 meters. So we can also put those. So self.actual width in meters, which is going to be 28. Then self.actual height in meters now. And it's going to be 15. Now we can have a tactical view drawer. So let's also open this up. And before proceeding, let's also expose it in the init. So from tactical view converter, import tactical view converter. And in the drawer, we can make a tactical view drawer.py. And inside of here, we can have a class with a tactical view drawer. And inside of here, we will have the init. And for now, let's leave the init as empty. Then we are going to have the draw function. And the draw function is going to have the video frames for sure. So it's all the video frames that we have. Then it will have the court image path. And this is the path of the image that we are going to overlay, which is basically this one. Like this one. We are going to put it in the top left corner. And then we want to have the width in pixels and height in pixels. I am also going to have a self.startX and end x, like the start x, which is the x position that I should put the image in, and the y position that I want to put the my image in. So start y, and it's going to be 40. And yeah, so this we can then read the image, we can overlay it on top of the frame, and then we can export it back. So have the court image, let's read it, and we can read it with CV2, and let's import CV2. And right now we can import it, image read, and then give it the image path, and then we resize it based on the width and the height that we got. And then we can have the output video frames, and we can loop over each frame. So frame index and frame in enumerate video frames. And the first thing that we want to do is we want to copy the frame so that we don't contaminate the input frames. So frame.copy. Then we want to specify the x and y positions of the image. So let's have the y1 is equal to self.start y, and x1 is going to be self.start x, then y2 is going to be start y plus height, and then x2 is going to be x1 plus width. I am then going to add an alpha. So alpha is going to be responsible for a little bit of transparency. So add the alpha right now of 0.8 or make it 0.6. And now we want to have an overlay just like we did with the previous rectangle, like the white rectangle that has the statistics. We want to have something like this here also. So overlay is going to be the frame, and it's starting from y1 till y2, and it's also from x1 till x2. And what we want to do is we want to copy it, and this is square brackets and not like the normal brackets, like this. Then we use cv2.addWeighted. We take in the court image first. Then we take the alpha. Then we take the overlay, and then we take in 1 minus alpha, 1 minus, and delete this, and then we specify that this is 0, and then we can also specify the frame position like that. Now we can add the output video frames.append frame, and then we can return back the frames. So for now, everything here looks good. We can open up the init for the drawers, import it, copy it, go back to your main, import the drawer, then import the tactical view converter. And we can have the tactical view converter after we detect the passes and the interceptions. So right there, we can add the tactical view. And in here, we can have the tactical view converter. And we are going to give it the court image path. Court image path, and the court image path is going to be images, and it's going to be the basketball image. So it's going to be the basketball court image right there. So just copy it, paste it in, make sure to add the tactical view converter, and then we can add the drawer. So in here, add the drawer. And after we add the key points, add the drawer right there. So tactical view converter, output frames. And inside of here, instead of hard coding those, we can have the tactical view converter dot key, like the court key points, and then have the width and the height as well. Now this is it. If we did everything good, we should find the court image at the top left corner of the video. So I think I misspelled converter. So in here, you can see that I've misspelled it. So make sure to spell it correctly, and save it, clear, run again. Awesome. Now we can open the video up. So go ahead to your output videos, open this up. And you can see on the top left is the tactical view one. And right now what we want to do is we want to define the points that actually represent the meters. So right here we want to define this point, then this point, this point, this point, and this point. And we also want to define this point, and those are the points that we detect already. You can see 16, 17, 7, and 8, and 7, 7, and 6 are right there. And we also have here, 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 and here, and here. So I think this is this is 0, 1, 2, 3, and 4, and 5. Then this is 6, and this is 7, and then this is 8, and this is 9, this is 10, 11, 12, 13, 14, and 15. This is 16, and this is 17 right there. So right now you know the key points and where are they located, and we want to map those key points, for example 16, to this position right there. And this is going to be relevant to the actual meters. So and we'll be giving it this coord positions in these pixels, but know that it is one-to-one correlated with meters, so we'll be able to judge how much a user is moving and know exactly where they are in the coord. So let's now define those exact positions in the pixels inside of this basically frame. So in order for us to do that, we can just utilize the actual meter positions, and it's going to make it easier for us to know the exact locations of those key points. So open up the images, open up this image right there. And you can see here that this is 0.9, and we can start off with that. So this is 0, 0 position, and this is going to be after it by 0.9 meters. So open this up, go back again to your tactical view converter, and in here we are going to define the key points positions relevant to the meters. So self.keypoints. And in here, the first key point is going to be 0 and 0. So it's 0 and 0. So this one is 0, 0, and the next one is 0.9 meters away. And the idea is that we know that it's 0.9 meters away, and we know the actual height in meters, and we know the height in pixels. So what we are going to do is just simple cross multiplication. We are going to say that 0.9 is in meters, which is going to be relevant to the actual height in meters, which is this one, which is actually 15. And then we know that we don't know the position of it in meters right there, but we know the pixel position or the pixel height is 161. So what we are going to do is that like cross multiplication is just 161 times 0.9 over the actual height in meters. So you can do that easily like this. So it's 0, no problems there, but the other one is 0.9 meters away, which is going to be 0.9, and it's going to be 0.91. Self, it's actually like more accurate to be 0.91, so I used another reference. I think you can find this reference in here. Just copy it, paste it right in. Right there, and right there it's telling you that it's 0.91, and it's going to be the actual height in meters then over self.height. This is the position of it inside of the video. So you can go back again to your video, which is the output videos, and right here this is the actual position that we calculated right there. Now the other position, now the other point is like this is 0.9 meters. Now the other point is around 5.8 meters away. So this point right there, oh, sorry about this point right there is 5.1 meters away. So we can just have the same thing, but do it like 5.1 meters. So this, and in here we write 5.1 sorry about that, 5.18 meters. And then we can have another one which is 10 meters away. Then we can have another one which is 14.1 meters away. Now, what I did is that this is 14.1 meters away because there are only 0.9 meters left, and it is 15 meters. And this is going to be the previous one is 10 meters away. The previous one is 15.8 meters away. You can actually go and refer back and forth to this, like see the numbers and how they are related. And the last one is going to be int.self, which is equal to the height, which is the full height, and this is going to be this position right there. So it's 0 in x-axis, but in y-axis it is the full height, which is the 15 meters away. Now this is the first line right there. This is the first line here. I'm going to do the same thing here, going to do the same thing here, going to do the same thing here. Instead of just writing some numbers, you can just go to the repo, go to the tactical view converter again, and you can just copy paste the key points. And again, if you want to calculate them, feel free to do so. You have the reference and you can just add in the meters like this, and it should work good. So that's it. And now let's go to draw the key points on top of this overlay right there. So we can go to the drawer, and after the height, we can add another parameter that is called the tactical view key points. So in here, add another parameter called tactical court key points. And then we can display them one by one. So in here, after we add the overlay, just for loop on top, like over the key points one by one. So key point index, and then key point in enumerate tactical court key points. So it's going to be tactical court key points. And then we are going to get the X and Y positions of the key point. And then we are going to be adding the start position. So remember that we have a buffer right there. So let's add the start X and the start Y. And we can then add a circle. So in here, add a circle, give it the frame, give it the XY positions, give it the radius, which is going to be equal to 5, give it a color, which is going to be equal red, and tell it that it's going to be filled. Then we want to add some text, which tells us which key point is that, and we can just add here the key point index, then give it the X and Y coordinates, give it the font type, give it the size, give it a color, and then give it a thickness. And let's make the color green. Now this is done. We can save it, and yeah, before we run it, make sure to pass the tactical court key points. So inside of main, inside here, and add the court key points right there. So it looks good. Save it, run it, and let's see how it goes. It's done now, so let's see the results. So you can see here that it has points 0, 1, 2, and we can add, and we also added the numbers on top of that to know which one is which. But you can see that 15 is corresponding to 15, 14 is corresponding to 14, 13, 12, and yeah, 12 right there has a misdetection that we will need to handle later on. So up next, let's try to remove any misdetections of the key points like this one, like the 12 one, because 12 needs to be here and it's here right now. So we can do that quite easily by saying that the distance between 13 to 14 needs to be proportional to 13 to 14. And for example, the distance between 13 to 16 needs to be proportional to this distance as well, to this smaller distance that we have in the tactical view. So if anything that is not proportional, so that 12, for example, is not proportional to 13, actually this is very far away and this is close, we can just then remove it. We can just say that the 12, that this like key point 12 is not detected at all. Now this is what we are going to do, and we are going to be looping over one key point at a time, measuring its distance between it and two other key points, and seeing whether they are proportional or not. And then we can give it some slack, maybe like 50% or 80%, something like that, because of the camera angle and things like that. But yeah, this is the logic overall. So it might seem a little bit intimidating, but it's very straightforward, and it's just checking the proportions between the 13 to 14 is the same as this one. It's also similar to other key points as well. So it's just measuring proportions. So for example, let's take 13 to 14 and 13 to 12. So for example, the 13 to 14 right there is around 500 pixels, and it might be here like 50 pixels. So the proportion here is 500 over 50, which is 10. This is the proportion. Now, the proportion here from 13 to 12 is around 1000 pixels. And the 13 to 12, let's say that it is only 40 pixels. So let me try to explain this a little bit better. So in a notepad, we can see that 13 to 14 right there, we can give it an example pixel distance. So 13 to 14 in the court is going to be, for example, 500 pixels, while 13, let's write it to 14 in the tactical view. So tactical view is going to be 50 pixels. So if you measure proportions here, it's going to be 500 over 50, which is going to be 10. Now let's have the same thing for the 13 to 12. Now 13 to 12, like 13 to 12, this is going to be, let's say, 1000 pixels. So this is a lot. And 13 to 12 right there is around 40 pixels. Now, if you measure the proportions right now, it's going to be equal to 25. So now you know that 13 to 12 should also produce 10 or produce something similar or very close to 10. But it's not. It's actually producing 25, which is 2.5 times greater than that. So actually, that shows to you that 12 is placed in a position that is 2.5 times away than its natural position. So this is a way that we can automatically detect that 12 is wrong, and we can just suppress it. And again, it just produces a proportion between the court and the tactical view. It gets the actual proportion, and then it measures the proportion in question, which is the 12 one. And if it's close to the proportion that we calculated earlier, then that's good. If it's not and it's very far away, then it's bad. And we are going to calculate like around 80% margin of error. And this 25 for your information is like 250% margin of error. So we can create like between 50 to 80% margin of error because of the camera angles and whatnot. So we can give it a little bit of slack, but otherwise this should like the 50 to 80% should be working good for other key points as well. So let's close it and let's open the code again, and let's write now the code to suppress any bad key points. So go to your tactical view converter, go here, and then have the define, validate, self, and then get the key point list, key points list like this. Then we can copy the key point list so that we don't contaminate what's the input. So key point list like this is going to be equal deep copy key point list, and we need to import deep copy. So from copy import deep copy, then we can go back here again and continue. So let's loop over each key point, one key point at a time. So for frame index and frame key points in enumerate key point list. What we want to do is we want to get the frame key points. So frame key points, and it's going to be equal to the frame key points right there, dot xy dot to list, and take the 0th element because it will have, like the 0th element will have all the key points. And then we want to also see the detected key points. So if you open this up again, you'll notice that some detected key points are not in, like some key points are not in the frame. So for example, key points 0, 1, 2 are not in the frame, and this is not a mistake, this is just the camera angle. So when you come here, 0, 1, 2 will appear, but it's not appearing here. So any key point that is not appearing, we don't want to compare it. So we can have the detected indices, and this is going to be a for loop, so it's a one-line for loop. So for I and key point in enumerate frame key points, and if a key point is not detected, it has a position of 0 and 0. So if the key point of 0 is greater than 0 and key point of 1 is greater than also 0, then this is a valid key point, and I will have it right there. So this is the indices of all valid key points. So the valid key points again are the key points that have other indices than 0 and 0. And if length of the detected indices is less than 3, then we want to continue. Basically, we don't have enough key points to say that this key point is valid or not, because we need at least 3 key points, because we compared 13 to 14 and then 13 to 12 to validate a key point. From those detected key points, we can have an invalid key points list, and we can loop over the indices in detected indices. Like first thing, we can skip like key points that have 0 and 0 like this, and we already filtered it out here, but we are going to maybe override some key points, so it's better to also check that it's not this anymore. So if frame.keypoints of I of 0 is equal to 0, and frame keypoints of I of 1 is equal to 0, what we do is that we want to skip it, so we want to continue. Then we want to take any two key points at random. So in our example, we used here 14 and 12. So we were validating 12, so we took 13 and 14. So we want to also take two indices and start comparing. So we can have this as other indices that are actually valid, and in here we can have the index, and for index in detected indices, if the index is not equal to I, which is this I basically, and we want to also make sure that it's not in the invalid indices. So and index is not in, you can move the is, it's not in the invalid indices. Again, we need at least 3 points to make this check. So if the length of other indices is less than 3, actually 2, because right now we have 1, which is the indices. So if it's less than 2, we can just continue. And if it's greater than 2, then we can take any 2 points. Let's call them j and k, and it is the other indices of 0 and another one which is other indices of 1. So basically I took the first 2, but you can take whatever 2 you want. And then we want to measure the distance between again the key point that we have, and between it with j and between it with k. So we want to measure this distance in reality, like in this key point output, and then we want to measure it in the tactical view as well. So right here we want to use, in the utils we have something called measure distance. We want to use this. So in here import sys.path.append and append the previous folder. From utils import measure distance, and from here we can have we can start measuring the distances. So let's call this the actual distance between the points, which is the detected key points. So the detected I and j, which is the distance between I and j of the detected key points, we are going to measure distance, give it the frame key points of I, and then give it the frame key points of j. Now this is it. We want to also have it for the k. Like this, and we want to also have those two for the tactical view part. So instead of the detections, we are going to use the tactical, and instead of the frame key points, we are going to have the self.key point, and make sure to have the correct spelling like this. Just copy, paste it here, and paste it here. And now basically we have the distances that we can use to calculate the proportions. So if the t, I, and j is greater than 0, and t, I, and k is also greater than 0, what we want to do, actually this is I and k, so let me fix that. So proportion, the proportion of the detected is going to be equal to, for the dij over dik And we just want to make sure that since we are dividing by 0, if the dik, sorry about that, if the dik is greater than 0, else we put a float and infinity. So this is the proportion of the detected, and if you remember that this is the proportion right there, 13 over 14, and then we can also have the same proportion for the proportion for the tactical view. And it's going to be Tij over Tik when Tik is greater than 0. And yeah, and right now we can measure the error of it. So let me, if you remember, we had like 10 and 25. The error of it is going to be 25 over 10, which is going to be equal to 2.5, which is equal to 250%. And we are going to measure that right now. So just by dividing those two together, we can get the error of it. So here we can get the error is going to be equal to prop detected over prop tactical, and then it's going to be we can then have the prop detected minus prop tactical over proportion of tactical. And this here is because we didn't divide the 25 at one time. We divided it like this, minus 10, and this is 150%. And this is because if it's 10 minus 10, then like this over 10, I want it to be equal to 0 and not equal to 1, which is 100%. So I just wanted to have the error margin and not just the proportion of both together. Both of them can work good. So if you are not confused by this, you can use it. Make sure to adapt the error threshold. I am going to use this notation for now, as it's more intuitive for me. And the error at the end is going to be the absolute error of the error. So if it's negative, we want to also have it positive because we don't care whether it's more or less. We just care that it's an error. And if the error is greater than 0.8, then this is actually a miss detection. So we can have the key point list of frame index dot xy of 0 of I, and remember that if we have a key point that is not detected, it's being 0 and 0. So that is what I'm doing right now. I'm just going to overwrite it with 0 and 0, and that would tell me that this key point is not detected. So it's xy and xyn. I'm going to make them both zeros, and then invalid key points dot append, and I will append I. And at the end of the day, I'm going to return back the key points, which I deep copied and overwrote the results of when I found the error. Now that is it, and we can now run this on the main. So you can go here, and after you make the tactical points converter, we can have the validate key points, and we can give it the key points. So basically, I just want to make sure that I called it correctly. It's validate key points. Just copy it, come here, paste it in, give it the quote key points, and then assign it to the quote key points. That is it. We are now validating, and if something that doesn't look good, something is weird, we overwrite it with 0 and 0, and thus claiming this key point is not detected at all. So we can save it, run it again, and see the output. So there seems to be an error here with validate keypoints is not a function. So I went back and saw that there is a misindentation. So make sure to have the correct indentation to be inside of the class and not a function outside of the class. Save it, go back again to your main and run it. So now it's done, and let's see the output. So you can now see that 12 is not being detected at all. It's disappeared, and that is absolutely fine, because when we move from this view to the tactical view, all we need is like 3 to 4 points so that we can put the player positions here. So all that the algorithm needs is at least 3 to 4 points, and if we have those, then it's good. We can remove other points that we are not confident of. Now, the last part here is that we want to now take those positions of the players and plot them right there. And this is going to be using a perspective transformation, and we are going to use a ready-made for this in OpenCV. It's going to be very smart, so we don't have to do things like seeing the half of the court and measuring the other half and things like that. It will automatically see the court key points, and it will just try to fit it in this place and try and take its shape. So yeah, this is what we are going to do next. So open up your code editor, go back to your tactical view converter, and inside here we are going to start writing the code that takes in those player positions and gets us the positions in the tactical view. So to do that, we need another helper class that does this transformation for us. And it just takes in the 2 key points list, which is the key points that we have in the tactical view and the detected key points. And then it just transforms the player's points based on those. So this is what we call homography.py. We can have a class called homography like this, and we will need to have import numpy as np, and we also need to have the import cv2, and inside of here we will need to have the init, of course, and we will need to have 2 things in the init. We will need to have the source key points, so this is the source key points, and target key points as well. Now, in this, the source and the target needs to be exactly the same shape, and we can make them as numpy arrays for now. So it will be easier for us to process those as numpy arrays. So it's called nd array. And this is how you define a type in a function. And if source dot shape is not equal to the target dot shape, then we raise an error. Then we just want to make sure that the homography needs at least 2 key points. So we need to make sure that the source has those 2 key points. And if not, then we are not going to run the homography. So in the few cases where we do not detect at least more than 2 key points, then basically what we want to do is we want to ignore moving this to homography, because we don't have enough data and key points to move this like player view, the camera view, to a tactical view. Then we also want to make sure that the source is actually having like 2 dimensions, which is x and y. So let's make sure that. So source dot shape of 1 is not going to be equal to 2. If it's not going to be equal to 2, then this is not going to be a 2D array. and we need to also raise an error. So let's have the source is equal to source as type, and then give it like float 32, and same for the target. We can then define a homography model. So self.model, and the homography model is going to be cv2.find homography, and give it the source and target. This is how easy it is. So we just have the source key points and the target key points, and we just give it to the find homography, and that is it. So if the self.m failed or gave a bug or anything, we just raise an error, but otherwise it should work good. So right now we just want to have a transform points takes in self, takes in points, and then if points dot size is equal 0, then we return back the points, because there is basically nothing to process. If points dot shape of 1 is not equal to 2, so this is not a 2D input. Also, we remove it because x and y are 2D inputs. And then if everything is good, we just give it to the homography model, which is perspective transformation model. And right here, we just want to make it into a format that the homography model can take. And this is points dot reshape and -1, -1, 1, and 2, and as type, and give it here the let me write it correctly, as type float 32. This is the shape that perspective transformation is expecting. So you can now have the CV2 perspective transformation, give it the points, give it the model, and you will have the transformed points. And the transformed points, we return it back to the 2D shape that we want, which is -1 and 2, which is basically a 2D array. And then we can have it as type, and then np float also 32. Now, this is the homography transformation. You can see that it's very easy. The points here are the player points, and all what we have to do is that we gave it the source points of the detections, the target points that are the points in the tactical view, and it initialized the model. Then it used the model to transform the positions of the players to positions in the tactical view. So go back again to your tactical view converter. We create another function right now. We can call it define transform players to tactical view. Give it the self, give it the key point list, then give it the player tracks, and then here have the tactical player positions. Then this is going to be the positions of the tactical players that are converted by the homography model. Then let's look over the frame key points and the tracks, which is the player tracks as well. So for frame index, and then the frame key points, and then frame tracks, in enumerate, and zip, which is the key point list, and the player tracks. And we are going to loop over them one frame at a time. So just like the player tracks, the tactical view positions is also going to be a dictionary, and it's going to have a player ID and the position of the player. So tactical positions of this only frame, but it will have multiple players, so that's why it's a dictionary. So it's going to have the frame key points, and it's going to be the frame key points right there, dot x y dot to list, and then give it the 0th position. And then if the frame key points is actually not detected or something like failed or something like that, then we can just skip the tactical view all over. So if frame key points is none, or length of frame key points is equal to 0, what we want to do is we want to add this tactical player positions dot append, and then we add an empty list right there, or empty dictionary, and then we continue. We continue and skip the rest of the loop. Otherwise, we have the detected key points, which is equal to the frame key points, like this. And then we have the valid indices that are going to be the non-zero indices. So basically it's going to be I, and for I key point in enumerate detected key points, and it's going to be if the key point of 0 is greater than 0 and key point of 1 is greater than 1. Then the homography needs at least 4 points to work. So if the length of the valid indices is going to be less than 4, then what we want to do is we want to also add an empty dictionary like this, and then continue the loop without, and then like skip the loop without continuing. And yeah, if all this happens and if we have enough indices, we can then simply have the source points, the key points, and then have the homography to transform each and every player. So we can get the source points. So source points is going to be equal to the numpy array, and I think we need to import numpy. So import numpy as np. Then go back again here. Then we get the source key points of all the valid indices. And we can specify also a data type of float32. So it's a numpy.float32. So it's the type of numpy of float32. We are going to have the same thing for the target key points. So for the target key points, instead of using the detected key points right there, we are going to have the self.key points. Now this is it. Now we have the source and target. We can just initialize the homography and then use it to transform each point of the player. So we can try like this. Homography, and we can have an except, then it takes in the value error, it takes in CV2 error, like this. As E, we also need to import CV2. So import CV2, go back down, and now it has the value error, the CV2 error, and we can pass it. Just pass if anything goes wrong. So we can import the homography. So for in here, just from dot homography, import homography. Go back down, let's initialize it, and when we initialize it, we give it the source points and we also give it the target points, and now we have them initialized. Now let's loop over each player ID, and player data in frame tracks dot items like this, and we have the bounding box data is going to be equal to player data of BB box. Then to get the position, we need to get the foot position of it. So from utils, we need to add a function to get the foot position. So define get foot position, and it takes in the bounding box. And basically, the foot position is going to be the middle of the x and the maximum y. So we can make sure that we are also exporting that, going back to the homography, actually the tactical view, make sure that we also import it, going back down, and the position of the player is going to be the player foot position. So position is going to be equal to np.array, and then get foot position of the bounding box. So yeah, that's it. So now we can just get the tactical position by calling the homography.transform points and give it the player position. And then we can fill out the tactical positions. So tactical positions of player ID, which is equal to tactical positions of 0 dot to list. And yeah, that is it. And at the end, in the for loop right there, we just want to append the tactical player position and then return it back. Now, this is it. This is the transform players to a tactical view. And then we can go back to main and actually call it. So go back to your main here in the tactical view. We can have a tactical player positions, which is going to be equal tactical player positions dot transform players to tactical view, give it the coord keypoints, give it the player tracks. Now, the last thing to do is that we want to draw those tactical keypoints. So we can go back again to the drawer, the tactical view drawer, and then add this logic. So in the tactical view drawer, you can just take in the tactical player positions, and we can have the player assignment as well, like this, assignment. And this is to when we just are putting the dots in the positions in the tactical view, we can put it as in blue or white. So we can have a none as default. We can also have the ball acquisition so that we can also indicate which player has the ball by having a red maybe circle on top of the player position. So we can have the frame positions right there. So frame positions, and in the frame positions is going to be the tactical player positions of frame index. And this is the tactical frame positions that we have here. So just copy and paste it. This is the frame position of the of all the players in this frame. We can also have the frame assignment and the player assignment of frame index. And then we can also have the player with ball is equal to ball acquisition, and this is going to be the ball acquisition like this. So copy it, add it right there, ball acquisition of frame index as well. Now from here we are going to loop over the players. So player ID position in frame positions positions dot items, like that, and we can get the team ID, which is equal to the frame assignment dot get player ID, and if there is none, then we can just put one as default. Then we can have the color, which is going to be equal to self dot team one color, like that. If team ID is equal to 1, else it's team 2 color. I don't think that we specified the team colors yet, so we can go up self dot team 1 color, team 2 color, and from here we can also have it as inputs to the init. So team 1 color is going to be equal to 255, 245, 238, which is a white color, and then team 2 color is going to be equal to a blue color, which is going to be 128, 0 and 0. And right here we want to put the team 1 color, so team 1 color, and then here we put team 2 color. Now we can go back down and have the team 1 color, else we put the team 2 color. Everything here looks good. We then specify the X and Y positions. So X, Y is going to be equal to the position of 0 plus self.start X, and put this as an int just to make sure. We want to have the same thing for the Y's. Now we are going to represent players as dots, so the dot is going to need a radius, so radius of 8, and I am going to have the CV circle, give it the frame, give it the XY coordinates, give it the player radius, and then give it the color, and then tell it that it is -1 for filled. And right now, if the person has the ball, then we can have another radius outside of this circle that is red, that indicates that this player has the ball. So if player ID is equal player with ball, then what we do is that we can have a circle, cv2.circle, frame, xy coordinates. The radius is going to be radius plus 3 to have a surrounding red like aura around it. So it's 0, 0, and 255 for red. And then instead of having it filled, we will just have the edges drawn. And yeah, that is it. We want to now give it the tactical player positions, player assignment, and ball acquisition in the main. So go back here again, and in here, create a comma and have the player positions. So player positions, we need to copy it from up. So this is the player positions right there. For the tactical, like for the player assignment, we have it right there. And for the ball acquisition, here it is. So don't rely on your Copilot on everything. It might make mistakes like this one. So just save it, clear, and clear it, and run it again. I think I misspelled list here, so I spelled it T before the S. So let's go back here and try to fix it. So go back to your converter. So right here it is list. Save it, and yeah, run it again. This is now done. Now we can go here and see the output. So here you can see that the players are being represented here correctly. So you can see that this user is here. this user is here, this white player, this white team player is here, this blue player is here. So everyone is here working good. And you notice that when this turned red, this is also turned red. So everything now is working good. And since we have the tactical player positions, we can now calculate speed and distance. And this is our next module. This is going to be our also final module. So yeah, hang in tight. We are almost done. And yeah, just close it. Go back again to your code base. Clear everything. Save everything and close it to make way for the speed and distance. Close this, close this, close this. And yeah, from here you can close all the folders on the left, and then we can create a new folder. Let's call it speed and distance calculator. And this is going to be a folder. Of course, we are going to have the init, and then we are going to have the class file, speed and distance calculator.py. We are, of course, going to have the class, calculator. We are going to have the init, and the init is going to take in the tactical view, like the tactical view thing. So we are going to have this right there. This tactical view, we are going to give it the width in pixels and the width in meters, so that it can calculate the distance and meters as we want. So in here we can give it the width in pixels, then height in pixels, width in meters, height in meters, and then we can specify it in the self. So self width in pixels, height in pixels, width in meters, and height in meters. You can delete the last two. Since we are going to be using distances and measuring distances, we have a function ready-made for us in the utils. So we can import sys.path.append, go back one folder, then from utils.bbboxutils, we want only measure distance. So just have this. And yeah, from here we can have the calculate distance function. So from here we can have the define calculate distance. It takes in self, it takes in the tactical player positions. Then what we want to do is we want to have output distances. It's going to be a list, and we are going to and we want to have also previous positions of the players, so that we can like measure the distance between two consecutive frames, or like the last known frame and the current frame. So the previous players positions, and this is going to be a dictionary. And yeah, so for frame number tactical player position for frame in enumerate. So in enumerate, and give it the tactical positions that we got from the input. So now we are going to loop over each player. So for player ID and current player position in tactical players dot items, tactical player positions frame dot items. Then If the player ID is in the previous players, we then measure the distance, else we just put it in the previous player's player ID like this. Now, this is all good, but this is now measuring the distance in pixels, which is the current player positions with the previous player position. So yeah, we want to make this measure the distance, but in meters, so that we can measure the distance and the speed. And before we proceed, I will want to have this as a slightly different format. So it's going to be also a dictionary, and it's going to have the of frame number and then of player ID. Then it's going to have the distance as the value. So right here, everything should be good, and we should return back the distances. But the last thing is that we want this to be basically meter distance and not pixel distance. So define calculate meter distance, and this basically takes in the self and the previous pixel position and the current pixel position. So we can now separate it into x and y's. So previous pixel x and a previous pixel y is going to be equal to the previous pixel positions. We will have the same things for the current positions, so the current right there, and current pixel x, current pixel y, and yeah. Right now, we just want to convert this pixel position to a distance position, actual meter position. So previous meter x is going to be equal to let's accept this line, which is going to be the previous pixel x times the width in meters over the width in pixels. And this is normal cross multiplications. And we are going to do the same thing for previous y positions as well. Previous meter y, and then current meter y and current meter x. So let's do that. So previous meter y is going to be equal to the height over the height in pixels. The current meter y is going to be the same thing. Then meter distance is going to be equal to measure distance and give it the previous meter x, previous meter y, then current meter x, current meter y. And at the end of the day, the meter is going to be a little bit overestimated, so we can penalize it. So meter distance, we can just penalize it a little bit and make it 0.4 because it's going to be a little bit overestimated. So that's why we are penalizing it, and then we can return it back. Now that's done. Now this is done, so we can just here utilize it. So self dot calculate meter distance, and now we are done. So this calculates the meter distance, and for each frame it will have their player IDs and their distance that they covered in this exact frame. Now that this is done and we have the distances, it's going to be a little bit easier for us to calculate the speed, as the speed is going to be the distance over the time, and the time here is going to be just the number of frames. And if we know that this is 30 frames per second, then we know that every 30 frames a second passes, so we can calculate it based on that. So let's define the calculate speed, and here we can have the calculate speed, give it the self, give it distance, give it the FPS is equal to 30, which is frames per second. Speed is going to be an empty dictionary. Window size, because we are now going to measure speed over the last, for example, 5 frames, so that we can have a good like distance covered, so that we can define how much they covered and how fast they were going. So for frame index in for frame index in range length of distances, speed dot append, and we are going to append an empty dictionary as well. And the distances here are not defined, so just make sure to add it up there. Then we are going to loop over the player, so player ID in distances of frame index of keys. Then we can define a start frame based on the window size and an end frame. So the start frame is going to be the maximum between 0 and frame index minus window size times 3. We are going to move 15 pixels, and if they are basically 15 frames, and if we have like 5 frames detected in those 15 frames, then we can calculate the speed. So basically +1, and we can have the total distance is equal to 0, frames present is equal to 0, and last frame present is equal to none. We will know how we are going to use it. This is the total frame, basically the total distance that the player covered, the frames that it took it to cover this distance. So what we want to do is we want to loop over those for I in range, basically the start frame till the frame index, and we are going to calculate the distance basically. Then if the player ID is in the distances of I basically, and if the last frame present is not none, because we want to have at least one frame that is already present so that we can calculate distance on. And so if there is, so we are going to have the total distance which is equal to the distances of I of player ID, then frames present plus equals 1, and the last frame present is going to be I. And yeah, we can have, at the end of this, we will have the total distance that this player covered. And then we now can calculate the distance. So if frames present is greater than the window size, so now we can have at least 5 frames, then time in seconds is going to be the frames present over FPS, which is the frames per second. So if it's detected 5 frames, it's going to be over the FPS, which is going to be 5/30 of a second. Then we want to have the kilometers per hour, so we can have convert seconds into hours, and we can do that by having time in seconds over 3,600. This is how you convert seconds into hours. Then if the time in hours is greater than 0, then we can have the speed calculated. So speed in kilometer per hour is going to be equal to the total distance over 1,000, because this is going to be kilometers. This is meters, and we want it to be kilometers. So we divide by 1,000 over time in hours. We can have the speeds, which is equal to the frame index and the player ID, which is going to be the speed in kilometers per hour. Else, the speeds here is going to have the frame index of player ID and it's going to have a speed of 0. And I think the speed is not defined, so make sure to define it correctly and have here the speeds as well. And yeah, this is it. And else, if it doesn't have the enough for the window size, we can have this again. So, and then we return back the speeds. So return speeds. Now, this is how you calculate distance and speed, and then we can draw the output. So from here, just import it, go back here, copy, paste, and we are ready. Go back to your main, and from dot import speed calculator, and in here we have the speed and distance calculator right there. And after the tactical view, we can have the speed and distance calculator, speed and distance calculator, and it's going to be the speed distance calculator, and then we give it some inputs, which is the tactical view converter, dot width, then dot height. Then we can also give it the actual width in meters, and then the actual height in meters. Actual height in meters. So in here you can just calculate the distance and then calculate the speed. So player distance per frame is equal to the calculator calculate distance, and give it the tactical player positions. And then we want to also have the player speed per frame, and give it the speed and distance calculator dot calculate speed, and we give it the player distances per frame. And yeah, we are all set. We can just print them out, make sure that they are there before we start drawing the results. Save, clear, and run. Whoops. So on top here, I think I put a dot, so just save it. It doesn't require a dot. Clear it, run it again. So everything here looks good. I think saving the video got an error, so make sure to close the video before you save it. And yeah, but I think everything else looks good, so we can proceed to drawing. So go back to your drawers right there, create a new file called speed and distance drawer.py, create a class called speed and distance like this drawer, and then have an init, and inside of the init we pass it. Then we have the usual draw function, and inside of it we will take self, the video frames, the player tracks, the player distance per frame, the player speed per frame. And of course we are going to start with the output video frames as an empty list, total distances, because we calculate distance per between two frames only, and we need to also present the total distance. So we'll be doing that. Then we loop over each frame. So frame player tracks, and then player distance, and then player speed, like this, in zip, and we are going to loop over them all like that. Now we are taking the player tracks to know where to put the speed and distance. We want to put it underneath the player. So the output frame is going to be the copy. Output frame is going to be frame.copy, and this is not to contaminate the input. Then we want to loop over the player ID, then distance in player distance, like this. Then if the player ID is in the total distance already, then what we do is we take the total distance of player ID and make it equal to 0. It's make it not in, so we are going to initialize it with a 0. Else the total distance right there is going to be the player ID plus equals distance. Now this is the total distance till this frame. What we want to do is that we now want to present the total distance as well as the speed right underneath the player. So let's now loop over each player and present underneath them their speed, and so we loop over the player tracks, so player ID and bounding box in player tracks dot items, and the x1, y1, x2, y2 positions of the BB box of the bounding box is going to be the position of int, and then we are going to give it the the middle position in terms of x-axis, and then the y position is going to be underneath the player. So it's going to be x1 plus x2 over 2, and the y position is going to be the y2. And yeah, so the position of 1, we are going to make a buffer of 40 pixels right underneath the player, and we are going to extract the distance, which is the total distance dot get, and then get the player ID like this, and the default is none. We are going to get the speed, which has also the player speed dot get player ID, and it also has a default of none, like this. And if the speed is not none, we are going to put the text cv2 dot put text, and here we are going to give it the output frame. We are going to give it a string which is the speed, like this, and it's going to be only 2 decimal points, and it's going to be kilometers per hour. So this is just part of the string. We are going to give it the position. We are going to have the cv2 dot font. Actually, let's import cv2 so that I can get auto completion. Import cv2, and it's going to be the font Hershey simplex. So this one, the font scale is going to be 0.5, the color is going to be black, and the thickness is going to be 2. Now we want to do the same thing with distance, so just copy it and paste it in. We are going to put here the distance, and here we are going to put meters. And yeah, instead of just having the position like this, we are going to have the position of 0, which is the x, but the position of y, we are going to put it underneath the speed. So just add a buffer of 20, and this should be it. After we are done, we can just have the output video frames dot append of output video frame. I think I forgot an S here, so just put the S, and at the end of that we can just return back the output video frames. So this is now done. We can just copy this, go into the init from, and then import this. Make sure to copy the name as well of the file. So in here, just put dot speed distance lower, go back to your main, import it, go back here, remove the prints. So we want to initialize the speed and distance lower first. So speed and distance drawer, which is equal to the speed and distance drawer. So just copy it, come here, have the output video frames equal to the speed and distance drawer dot draw, and we give it a couple of stuff. We give it the output video frames. We give it the player tracks. We give it the player distances. So player distances per frame. We give it the player speed per frame. And now we should be done. So just save it, come back here, run it again. So there's an error, so let me go back and trace it. So this one here has a dot items. And yeah, just save it, run it again. There is an error in put text. So let me see it and get back to you. So inside here, make sure to add a bracket right there and a bracket right there so that we can int this operation all this operation and not just the x plus x2 operation. So just save it, clear, and run it again. So now it's done. We can go back again to the video. And right underneath the players, we can see that there is kilometers per hour, which is their current speed, their distance that they covered already. And yeah, we have a lot of good statistics right here. And when they're moving right now, you can see that it is 21 kilometers per hour, and they moved around 15 meters. So yeah, we have a lot of good statistics right now. The interceptions, the passes are doing good. The ball control is also doing good. And you also have a tactical view position up on the left. Now all the modules are done, and just before closing, I just want to get rid of all those hard-coded paths and put it into one configuration file, like this one and this one and this one. And also I want to be able to take an input of the video input path that I want to process, and maybe even the output video path and the stop path. But yeah, we want this to be input to the script file that we are running, so that we don't have to go and edit the script to run a different file. So we'll be doing this next. So in here, we'll create a new folder called config. And inside of the config, we can have an init and a config file. So init.py. We can also have a config.py. And let's call this, configs. And in here we can specify a stubs default path, which is going to be equal to stubs, which is this folder right there, this one right there. And we can have a player detector path, which is going to be equal to models, and then the player detector PT, which is going to be this one. So we can just copy it and paste it in here. We can also have a ball detector path, which is also going to be the same one that we're using here. So just copy paste it. Then it's court key point detector path, and then the output path. So court key point detector path. We can go ahead and copy paste the path from main, which is this one, and output video path, which is going to be equal to the output video path that we are doing at the end. So come here, paste it here. Then we can go to the init from .configs, import all the things that we just initialized. So just copy paste all of those, copy them, and then paste them right here. So stop path, then we have the player detector path, then we have the ball detector path, then we have the court key point path, which is only this one, and at the end we have the output path. So just save them, come back to your main, and we'll import the configs. So here we can have from configs import, and then we import all of them. So stop path, player path, ball detector, court detector, and the output path. So now instead of just hard coding this path right there, we can just put it in the config file. So just copy this, paste it here, and also do it for the ball detector path. Also do it for the court one. So just put it in here like that. For the input, for the stubs, and for the output, we are going to take those as arguments. So let's define the arguments when calling the function or calling the script. So we can have the define parse args, and it's going to be parser, which is going to be the arg parser, argument parser, and then we can give it the description. We can write here the basketball video analysis, basketball video. You can write whatever you want, analysis, and arg parse is not imported, so we can just import it. So just copy it, import it right here. I like to also put it at the top before the local imports. And then those are arguments that we can call and add when we're calling the script. So we can call the script like this, Python main. And now when we add any arguments, we can just write stub path, and then we define the stub path like this. So basically, we're going to have a stub path, and it's going to have a default of this stop path. So if someone didn't specify the stop path, we're going to use the default path. So it's an optional parameter basically. And we're not going to need the player or ball detector or the court key point detector, so you can just delete them all. And then we have the stop path and the output path. Now basically you have the name of the key, like this is the stop path, then you have the type of it, then you have a default value of it, and sometimes you don't need to specify the default option because it's maybe a mandatory parameter, and we're going to have a mandatory parameter for the input video path. And the last thing is that just a description of it. So this is the path for the stop directory, and this is the path for the output video. And basically both of them have defaults. So let's now add one more parameter that is not that is mandatory, and just have the input video. Basically this input video won't have a default parameter because it's mandatory, but it's going to be a type of string. So like this, and it's going to also have a help, which is the path of input video file. When we call it now, we need to provide the input like this, input videos, video1.mp4 for example, and then you can either give it the stop path and the output path, or you don't. But yeah, this is it. Now we just need to call it and use those arguments. So arguments.argparse, and then in here we replace the input video path that is hard-coded with the one that we got from the arguments. And in here we also want to use the stop path from the arguments instead of hard-coding it. So we can import OS if it's not imported. So import OS, go back here, and in here we just want to append this path to it. So os.path.join, we take the stop path and then we add the player track. We do the same thing for the ball track, we do the same thing for the court key point detection, and we do the same thing for the player assignment. And at the end of the day, we do the same, actually we don't do the same thing, but we just specify the arguments for the output video. And this is it. This is how you can package this file into a runnable application. And right now we have Python 3. We give it the video that we want to process. We can also specify whatever stop path we want. We can also specify whatever output video we want, but I'll keep them the same for now. And let's run it and see the results. So we have a small problem, is that no module is named configs. It's because here in the folder I named it config. So let's just name it to configs, and then we can clear it and run it again. So now it's finished running, and you can go ahead, you can make sure that everything is good, working fine. Then you can go ahead to your output videos, check that your output video is there, check that your stubs are there, make sure that everything is working fine. And yeah, now we are done with our code. So yeah, congratulations for staying this far. You learned a lot through this tutorial. First, you learned about object detection, and you trained your own object detection models using YOLO, and you trained to detect the players and then the balls. And then you learned about zero-shot classification, and we were able to utilize this to detect the jersey colors of the players. And from here, we detected a lot of good statistics, like passes, like interceptions, like ball acquisitions, and everything in between. And after that, we took it a step further, and we utilized a model for key point extraction that we're able to extract points from a court, a basketball court. And then we were able to convert this into a tactical view. And from the tactical view, we were able to detect like the speed and the distance covered per players. So a lot of good statistics, a lot of good sports analytics, and congratulations again for staying this far. And yeah, thanks a lot for watching, and see you in the next one. Bye.